Aloha, amigos. What's happening? Welcome, everyone, to another day of the Apply Conference. We are back in action. Thank you for joining us once again. This is something very special. We have had some incredible speakers so far. It has been one hell of a day yesterday, and today we hope to just not hit that same bar, but make it better. We're going to try and do all we can to make it the most amazing conference that you've been to this year. It doesn't matter if you're talking about ML or DevOps or whatever tech you like. So, a few things. Let's just go over some housekeeping while we're here and we're starting in case you missed it, right? Day one was a hit. I talked about that. We've got all kinds of swag that we're giving away. And I recommend that you either get into the Slack channel, which we're going to be posting in the chat right now if you're listening on Zoom or watching on Zoom, or if you are on YouTube, we're going to be posting the Slack link if you're not in there already. So get in there, be active, and yeah, use Slack. What's really cool is we've got like 3 dedicated channels for the Apply conference in that Slack. One is the funny channel. So if you're not in funny, go get in it and have some laughs at the selfies from yesterday. The other is the Apply Conference, just normal Apply Conference. And then we have Apply Conference Networking. And I have yet to see anyone do anything cool in the Apply Conference Networking besides everyone just dropping their LinkedIn. So somebody gets a big +1 if you can do something creative with the Applied Networking channel. So it's not just a bunch of LinkedIn links. That being said, I realize there are a ton of smart people that are listening and watching from all around the world today. So if you all have questions and we can like make this a community thing, ask the questions. And there have been some really helpful people in the Slack that have been just amazing. So jump in there, get involved, and you might win some swag. Who knows? We've got a lot to give away. Good news is that I accidentally did not give enough swag away yesterday. So today we're getting even more swag. All right. So the conference is being it's been pretty cool. You know, it's got like just the right amount of people trying to sell you shit and actual thought leadership, I think. And speaking of people trying to sell you shit, we got to hope we didn't just get demonetized right there because I'm cursing. I'll try and not do that anymore, but we are going to say thank you to Tecton for organizing this whole thing. And also thank you to all of the partners. You probably just saw on the video, there's been a ton of partners that are involved in this. If you'd like to see more information about them, you can check it out on the website. Now, the other thing that I want to do before we actually get jumping into the full conference with Todd, who's coming up, and I'm actually super excited for that. But hold on, Todd. I see you coming. I just want to share my screen real fast because there is one person who won some swag yesterday and he did not claim it. So Cedric, if you are out there listening, I know it was really late for you yesterday when I announced that you won. You get some swag. So contact me on Slack. The other thing is that we asked everyone to fill out this poll and the results are in. I know everyone at this conference loves to see data, and visualizing data is even more fun. We've got this poll. Should a data scientist be proficient in Kubernetes? A lot of people said, I don't care, which is surprising to me. Then 31% said no, 20 or 18%, sorry, 27% said no, and 18 said, I agree. And then there's the strongly agree, and 11 strongly disagree. So that is a really interesting one to think about. Now, is MLOps an organizational problem? I have a feeling, Todd, you might be talking about this later, but we have agree and strongly agree are the main ones on this. So yeah, We know how we stand as a group on that one. How many models are you running in prod? It looks like 2 to 5 is the meat of this one. Then you've got some people doing 5 to 10 and going up to 10 to 20, and then only a few are over 500. Wow. All right. So how long does it typically take you to deploy and build and deploy a model to production? 2 weeks, 1 month, ooh, 2 months. It just goes. It's some nice stuff. But really what I want to just show you about right here are these. Have you ever had a model go rogue? Tell us the story. This is hilarious. And I am going to figure out a way that we can share this in Slack. Hopefully nobody has a problem with us sharing that. You put it, and I told you it was going to be public. So it is all anonymous. This is it. But there's one in here. There's so many good ones. Some recommender system started recommending hunting gear to everyone, even people who are vegetarian and they don't hunt. But there's this one, trained a model on historic data, looked at every possible way it might fail. Yes, I think we can all relate to that. Calculated the benefit to business, taking into account false pros and negs. Good to know how much other stuff. We launched the model to make predictions of incoming data. Turned out our most important feature took 3 weeks to stabilize, which of course had been an issue and wasn't visible when it was on historic data. Most embarrassing. It wasn't until we used the model for several successive months predictions till we figured out what was happening. So whoever that model gone rogue story is, tell me, and you're going to win some swag. So there we go. That's it. Next up, I'm going to introduce my man Todd. I will ask you to come back on now. What's going on, Todd? Good to have you here, man.
Hey, good morning, good afternoon, good evening. Time zone appropriate greetings to everyone.
Yeah. So let me just tell everyone why they should be listening to you in case they missed it or what you're all about. So Todd's first session is probably the most clickbaity session of the conference.
Yes.
The only truly hard problem in MLOps. I love that title, man. You could be a copywriter. So if anyone doesn't know who Todd is, he leads the machine learning site reliability engineering for Google and is the site lead for Google's Pittsburgh engineering office. Prior to Google, Todd held various roles at, you're going to have to help me with this one, Renesas.
Renesas, sure.
Yeah. And so here we go. We're going to talk about why ML-centric, the only truly hard problem in MLOps is the data. I'm going to kick it off to you, Todd. And just a shameless plug before I do, if anyone wants to see more of Todd, we recorded some coffee sessions or podcasts with him on the MLOps community. So if you're not in the MLOps community, get in there and we'll leave a link to that in the chat or in the Slack too. But for now, it's all you, Todd.
Fantastic, Demetrius. Thanks a lot for the introduction. Let me just hit the present button. I'm hoping people can see that. If you can't see it, this will still be entertaining if you can't see it. So let's not fret. Yeah, as Demetrius said, I'm Todd. I do ML at Google. This is some work, as it was pointed out, quite correctly, some clickbaity work that was done with my colleague, Niall Murphy. I've been doing machine learning stuff at Google for about 12 years. Here in the Pittsburgh office. Niall has spent the last 15 years working for Amazon and Google and Microsoft and has done a bunch of machine learning stuff as well. And Niall, you may know from his role in creating and as the lead author of the SRE book. So if you don't know that, that's fine. By the end of this talk, you'll be convinced to know that. I don't know if you will. So the title was, yes, the only truly difficult problem in machine learning, but that's, of course, nonsense. Really, that's an exaggeration for effect. I want to talk about the only truly difficult problem in machine learning: reliability, operations, and production. And again, even that's an exaggeration, of course, but people only come to things that are a little bit exaggerated. But I do want to point out that there are a lot of problems that we have that are not machine learning problems. And there are already good solutions for those. And that's the punchline, is that I want to point out a bunch of problems that aren't really our problems as MLOps folks, and have already been solved pretty well by some other people, so that we can focus on the problems that are our problems. So we have many problems. We have so many problems to choose from. So MLOps generally concerns itself with producing reliable, high quality ML systems. But these are, of course, complex, interdependent, multi-stage pipelines. When you hear stories like the one that was just told about a model that has to work on a lot of data in order to stabilize, but that doesn't show up until you actually put it into production, that stuff is pretty common for us, right? So that complexity in the interdependence is really what we're looking at in these multi-stage pipelines. And so the thing I want to convince you of is that we already have techniques in computing, and in particular in site reliability engineering, for addressing these. And if you don't know what site reliability engineering is, don't worry, I'm going to explain it, or explain it sufficiently well that we can pretend we all know what it means. So let's talk about machine learning production problems, but let's express them in terms of what we would like to achieve. So for those who haven't seen this term, SLO, a service level objective, it's just something we want to be true in the world. And when you express it that way, then you can build a system that tries to accomplish it, and you can build monitoring and emergency response that tries to achieve that. So let's talk about like training pipelines. What do we want from a training pipeline? If you're sitting around, you're like, well, I want my models to finish training on time. So finish is the good part. And then on time is whatever on time means for you. It could mean a particular speed. It could mean by a particular deadline. It could just mean before you wake up the next day. But on time for you, we want our model configurations that are updatable, are durable, so we don't lose them. They're probably versioned. We can troubleshoot them, and they work. When I say like, and functional, they work. They create models that work. And we want these trained models that result from our training to be usable in some format, broadly usable. So are they correctly formatted? Will they load into the next stage of the pipeline? Do they have reasonable quality? We're coming back to quality in a minute, so keep your attention on that. What about the data ingestion system? Well, we want the data to be readable, correctly formatted, interpreted. We want data that are ingested quickly, right? We don't want to sit around waiting for the data to appear. We only want data that are accessible and only accessed by the right users in the right program. So a lot of us deal with some data that's pretty private, which is great. Like that's fine, but you need to treat it appropriately. So you need to restrict access to it, and you need to log that access. Okay, good. Sounds good, right? What else? Oh, we're going to have some sort of feature storage system, right? Here we are at this gathering. We've heard a little bit about some feature storage systems. So, but we don't just want to store features, I think. I think we want to store features. We want to store model snapshots. We want to store configs. We want metadata about all of that stuff. That doesn't have to be one system, but it certainly, all of those needs have to be met somehow. And if not, we're just slapping things in directories and hoping for the best, which is also fine. But like, you just have to acknowledge that is your storage system if that's what you're doing. We want features that can be read quickly and reliably. We want configs that can be updated and validated for all of our storage systems. And we want the data to be durable and correct. Durable for people who don't do data integrity stuff just means we don't lose it. It's a fancy way of saying data we don't lose. Okay, cool. Serving system, we want queries to be fast. If we're looking up stuff, we want them to be fast, whatever fast means, and error-free, whatever error-free is acceptable. Not error-free, but low error, really, I should have said, whatever low is acceptable for you. Models that are updated, if you have a new model, you want to replace it in serving, it should work. We want query logs because we're probably going to use whatever questions and answers we asked about the model for training the model in the future as some kind of exogenous signal of what the model's doing. So many MLOps folks claim to have or do this stuff, right? So like, we've seen a lot of systems and a lot of pitches and a lot of methodology that says, like, we're going to solve these problems in this way. We're going to have end-to-end automation of the ML lifecycle. We're going to focus on efficient sharing of compute resources, optimize your data storage, improve and standardize data ingestion, all of this stuff. Like, these are the kinds of things that many MLOps products and services claim to address. And this is the kind of work that many people who say that they are doing MLOps are doing. So that sounds fine. Like that's just, here we are, this is our community, and these are the problems we're solving. So what I want to do though is take a step back and say, actually, these are not our problems. These are somebody else's problems. We can solve them, but we shouldn't pretend that this has anything to do with ML, because most of what I just described are not MLOps problems. They're just software operations problems. They're just the kind of problems you have when you're operating large-scale distributed data store, when you're operating a web crawler or a web page that you serve, or a payment system, or any of these things. Like the ML part is not what made most of those things hard. And so as a result, I want to take a step back and say, let's be lazy here. If somebody else already solved some of these things, or at least has good approaches for ameliorating these things, we should take advantage of that, right? Like, why reinvent things? Sounds good. So who has solved some of these things? Well, I know some kids who have done so. They're called SREs. So let me pause for a second and say, well, what is SRE? SRE, site reliability engineering, is an approach to doing large-scale systems engineering at Google. Started at Google, and now it's like, a lot of different people throughout the industry have adopted this approach. And it basically treats operations problems as software problems. So apologies for that. That was terrible. Hold on. I am really so sorry. Ugh. Terrible. I've lost my window. Everything is awful. There we are. Hopefully we're sharing again. So SREs treat operations problems as software problems. And there's sort of the approach that Ben Traynor, who is an early exec at Google, approached reliability engineering. So that's fine. So let's look through what is the bag of tricks that SRE has to solve some of these operations problems as if they're software engineering problems. So what are the kinds of things that SREs do? Well, we design redundant infrastructure. And I say we because like I am, in fact, do SRE work for ML. So we design redundant infrastructure. We treat configuration as if it's code, because it is code. It determines the functioning of software. We use distributed consensus. Not enough people really take that seriously, and it's really the only way to have sane distributed computation. Lots of focus on security controls and how those work. Enormous amount of focus on monitoring and observability. Lots of techniques for thinking about whole collections of computers as if they're one fleet rather than individual computers. These are all pretty straightforward approaches. Sounds good, right? So let's take a look quickly at how these map onto the problems that I just said were MLOps problems. Well, we see training pipelines. Those are the service level objectives we were trying to achieve. So how do we get models to train on time? Well, we monitor model completion and progress at various stages throughout the pipeline, and we alert when it's not. It's not magic. And that actually has nothing to do with machine learning. If you're processing a bunch of payments or you're indexing a bunch of data, you have exactly the same problem. Similarly, how do we check our configs are any good? Well, we validate the configs. We write validations against them, and we make sure that those validations pass. Similar, like if I have a trained model and I want to make sure it's correctly formatted and will load, well, I have a staging system where I try to load the model. And if it doesn't load, it is not valid. And so you might see the word model and think, what is that? Like, why isn't that the machine learning part of this whole system? But in this case, a model is just a bundle of software that needs to load into another piece of software, and it's either correctly formatted or it's not. So again, none of these problems is a machine learning problem. Similarly, data ingestion stuff. I won't go through all of these, and we will share the presentation. But the point I want to try to make here is that as you walk through this, you'll see each of these, like, are the data readable? Are they correctly formatted? Not a machine learning problem. We should monitor that data ingestion is succeeding, that we're not throwing errors as we try to read it. We can, test load some of the data. We can run assertions on the data ingestion and validate that the formats are correct. We can check the access controls on the data to validate that we have restricted it. And we can do so periodically, like once a minute, once an hour, et cetera. We can log access, and we can monitor those access logs. So again, no ML here. What about the storage system stuff? Same, right? Like none of this is about like is a storage system working? Now, the distinction I want people to think through is the requirements we have for these systems are in fact machine learning requirements. Like, why do we want these things? We want these things because we're trying to build production-ready machine learning systems. That's great. But how we solve those problems now has nothing to do with machine learning. And that's an important distinction and an interesting one. Similarly, serving system, I mean, to be honest, the serving system is probably the least machine learning part of it. Like, it's a distributed serving system, similar to a distributed web serving system or many distributed application serving systems. The constraints that it has come from an environment of machine learning, but the way to solve those constraints, again, is by running a high quality, well-monitored distributed serving system. So nothing to see here. So here's an observation I'll make, and then we'll talk about what's left. So the observation that I'll make is that all of these solutions are context-free solutions. So they do not depend upon the fact that the work that we're doing is machine learning, and the machine learning that we're doing is for some particular purpose. We don't need to know that to monitor the completion of our training pipeline. We do not need to know that to make sure that our models are correctly formatted and will load into our serving system, right? We just need to know we have a process that is finishing, it is producing a binary artifact, and it needs to get to the next stage, and the next stage needs to start. And the fact that it is about targeting an advertisement, or about predicting a purchase, or about the objects that are in a photo, that's irrelevant to the kind of work that is done to make that production. So that's, I mean, I've mentioned this to other people, and sometimes people get annoyed or frustrated. They're like, you're trying to take away something from me. I'm like, no, I'm excited that we don't have to work on this stuff. I'm not saying no one has to work on this stuff, but when we work on this stuff, we are not doing MLOps, we're doing ops. We are not doing, machine learning reliability engineering. We're doing regular systems and site reliability engineering, which is great because there's a ton of people who know how to do that and they're good at it. And we should borrow from their skills. And we should actually have them on our teams. And one thing I'll say honestly, and we can talk about that, I know it's a question that Demetrius brought up with me when we spoke. Most of the people who work on SRE for machine learning at Google do not have a background in machine learning, and it's not a problem. In fact, it's not even vaguely necessary. It's not to say they don't need to learn some of that along the way for useful context, but most of the problems are not machine learning problems. Okay, so wait, so are we done? Like, is that it? Do we solve all the problems? Unfortunately, no. The whole point of this is not what is not MLOps, but what is. So what's left? So where's the machine learning and machine learning operations? I want to make an argument. It's mostly hidden in the data, and this is the problem. So subtle changes in the distribution of data, both in positive and negative sense, can have enormous impacts on the quality of our models. And the quality of our models is in fact what we're trying to do. So one of the themes that I've heard as people discuss these things is like, oh, like MLOps should really focus on the business value, the organizational value. Yes, right. Again, we're not here to train models. We're here to accomplish some higher goal, which could be, sell more widgets, or it could be predict more weather, and it can be identify more oranges in pictures. But whatever thing we're trying to do, that's the thing that is the point of the whole thing, right? That is why we're here. So what happens if we have subtle changes in the data is that they're very difficult to detect from a systems level, but have profound implications on a modeling and quality level. So in order to do that successfully, in order to mitigate those problems successfully, it is often necessary to have the whole picture sort of in focus in your monitoring, in your application, and that's very expensive. So let me motivate this with a little example, and then talk about what I think we can do, and then I'll wrap up. So here's an example. Consider some hypothetical machine learning system that we run on a website that sells yarn. Right, sells yarn for people who knit and crochet. Okay, so people search for things on this website, and we track the things that we show them and which ones they click on. And we use that as a signal to a model that tries to produce ranked results for a search engine as people are shopping for yarn. And maybe we use clicks, but we also use profit margin, right? Because we might choose to show something that isn't quite as popular for people to click on, but makes us a lot more money. I know that is base to say, but as a yarn seller, we might really want to make some money and want to cover our costs. And so we might do that. So now imagine that our app, like we are a global yarn seller, right? Like we are across the world. And for whatever reason, we have a system failure and we drop all of the logs from all of our Spanish language users. So we are no longer updating our model with the clicks that people whose browsers are set to Spanish are clicking on. So for our particular set, consider the possibility that this is only about 7% of our data. So if you're monitoring across your data, you might not notice it. Like that's well within the fluctuation of a normal daily cycle, right? You have these diurnal cycles and it would be difficult to detect that even. Okay. So what happens when we train the version of our model for the next day or the next hour or the next whatever, like we're going to update this model, our system will incorrectly learn that all results in Spanish are bad. That's not good at all, right? Like that's terrible. So as a result, our system will stop recommending Spanish language results, even for Spanish language users. This is really not good. So this is a common kind of a problem. It's not even a very interesting problem in some ways, but it is interesting to me because it motivates the question, if you didn't know this was a machine learning set of models, how would you detect that kind of an outage? And you say like, oh, well, I would monitor all the data arriving and make sure I had data. You're like, well, you would only know to look for data in Spanish if you knew Spanish was a valuable feature of the machine learning system, if you knew that was relevant. Similarly, if you knew that geography was relevant, you would look across geography. If you think time of day is relevant, you can look across time of day. But in each case, you have to know the machine learning purpose of the model in order to try to solve it. So note that this is a problem that is a modeling problem that's caused by an infrastructure failure. Okay, well, so now we know model quality can be impacted by making bad models. Lots of us have made bad models, and that'll continue, presumably. We're all trying to make better models, but usually start with the bad model. So we can have bad models made by modelers who have made bad models, but we can also have models that are made bad by infrastructure failures. And that's the class of problems I'm particularly interested in. So some infrastructure failures really will only easily or sometimes at all show up as model quality failures. I've listed a few examples of these, and most of you are familiar with some of them, so I won't go through them. But most of them have to do with cases where we have the data, but the mapping of the data to the meaning of the data, so the semantics have changed. Simple examples like I can change quantization of, if I have an integer for age and I quantize it on decade and somebody else quantizes it on 5-year boundaries, well then those just mean really different things. Like an index of 4 in that quantization is completely different and addresses a very, very different age for whatever that record is. And so whatever that example is. So you can imagine all kinds of things like this that are not, they're essentially invisible at an infrastructure level, but clearly visible at a model quality level. And so what I want to point out is that this leaves us with model quality monitoring is the only real end-to-end integration test of a machine learning system. And that is actually a little bit of a disappointing and terrifying result, because what it means is, as machine learning infrastructure engineers, we're not actually capable of building a system that is reliable in the true sense, because to be reliable in the true sense would be this system trains good models and puts them into production reliably. That is a wonderful thing to aspire to. That is not a thing we can achieve. And that's disappointing. And so the next step is, well, what can we achieve? Well, here are some best practices for model stability and monitoring. Most of these come from a paper that some colleagues of mine at Google, including the inimitable and well-known Dee Scully, produced, along with Eric Breck and a couple of other collaborators in the Cambridge office on the ML test score. And these are just straightforward ML test recommendations that they had. What I will say about these, I won't go through them all in detail because I'll leave time for a couple of questions. But what I will say about these is each of these is easier said than done. I included that note on the first one, but none of these is easy to do. So notify and dependency change. Sure, that's great. But what's a change in a dependency? Like, how do I know if some data I'm consuming changed the meaning of one part of one column of data that I consume for my model? How would I even know that? But there are things that you can do that are relatively simple. So, you can look that you're not using massively more compute than you were using to do the same thing previously. You can keep track of how old your models are and that they're not older than you expect. So this set of solutions has a wide range, ranging from very easy and very straightforward, like keeping track of your model age is trivial. Useful invariants that hold across training and serving, that's quite a bit harder, because what is a useful invariant? And it's very context sensitive. So I think so what I'd like to leave you with, and then I'm happy to take a couple of questions, and I will also be on the Slack channel after this to answer other questions. But what I'd like to leave people with is a sense of sort of hope and dread. So the hope is that many of the problems that we think are really big problems, other people are already working on and have some good approaches to. Not to say like, I am not saying like, oh, these are easy. They're not easy, but they're hard in a way that has attracted thousands and thousands of other people who actually don't know that much about machine learning and don't care about it to work on. And we should take advantage of their skills. So that's the hope, is like, oh, we can probably do a lot better with a lot of the things we're doing by following best practices for distributed systems and by hiring some of the people who already know how to do that and getting them to help us. That sounds great. The dread part is, and then what's left is model quality and the intersection between model quality and infrastructure. And that is just, there is not an easy way for that. So thanks very much.
That was awesome, man. That was exactly what I was looking for. Thank you, Mr. Todd Underwood. We've got some questions coming through in the chat. How do you visually monitor model quality?
Yeah, so I think again, it's super context dependent. So if you have a model that's trying to make money, you graph how much money it's making. I mean, it sounds really straightforward, but like, what's the model trying to do? If you have a model that's trying to sell things, how much of what kinds of things is it selling? So you really basically determine the slices, so the subdivisions of significance for that model, and you graph it out on that. So if you have a global service that's trying to translate things, graph how many translations people are saying are bad around the world, et cetera. So this is the sad part, is every question like that is going to have the form, well, it depends. What are you trying to do? Sorry for that, but that's where we are.
The nature of the beast.
Yeah, what else?
That's what you get. There's one about how you, Mr. Underwood, are implementing some of these best practices you speak of.
Yeah, so I think, so what we have done is, like, we grew machine learning SRE at Google out of SRE. It is not an outgrowth of Google Research. It is not an outgrowth of core systems. It's an outgrowth of SRE. And so in my organizations, I preferentially hire people who are good at distributed systems and interested in machine learning versus people who are interested in machine learning and willing to do some distributed systems. So that is one of the things I do. And I would encourage other people to do that, because I think it's a little bit offensive to us, but like, we just have to acknowledge you don't actually need to know as much about machine learning to do the production engineering of machine learning as people keep saying. Not to say it's not fun, it's not sexy, it's something we can do if we want to, but like the machine learning part, and part of this is being at Google, like the people who do that are so much smarter than me that I have no illusions that I'm going to be like that. Like, those kids know what they're doing. I'm just over here. I'm just the machine learning infrastructure plumber, and I'm connecting up the pipes and I'm making sure that the bits are flowing through those pipes. And it just happens to be ML bits.
I love that outlook on it. Any thoughts on approximating model performance when you do not have ground truth labels or they are received on a delay? Best practices around that?
Yeah, so I think the important part of that question is the cheating easy best way is if you can get a golden set or you can get some ground truth. And so like, when you don't have it, I do want to say like there's a couple things you can do, but man, if you can get a golden set, you can run your golden set through your model and say like, how's it doing? How's it doing for the new one versus the old one? If you don't have that, then I think in my experience, you take a big step back and you say, well, we do have one set of ground truth, which is what were we trying to do with the model? And there's only two answers. We don't know, or we know and it's X. If we don't know, it actually doesn't matter if your model's any good because like it's fine for no particular purpose. Like not having a model is also fine. So you should probably close up your ML shop. But if you know what your model was supposed to be doing, go look at that, whatever that is. If it's supposed to make your factory run faster, is your factory running faster? If it's supposed to like schedule your meetings in the morning, how are your meetings scheduled? I know that seems glib, but that's actually like go back to what you were trying to achieve and find that exogenous signal from that and make it as close to real time as you can. And then beyond that, just compare the new one to the old one. Like once you have a little bit of confidence that you're not doing terribly, you can bootstrap quite a bit from that.
All right, last one, then we'll
Yep.
wrap it up. This one is, what level of infrastructure details do you expect from a data scientist to be able to know?
I think, it's difficult to answer that with precision, but what I love about that question is the implicit understanding that you don't get to be a data scientist without caring about the infrastructure. So I won't actually answer that question. What I'll say is I'm really excited that somebody asked that question because what I'm hoping for is that more people acknowledge that they get to do the fun algorithm work and building the models, and they get to do the fun data analytics work, but they also have to care about how well it runs. And if they do, they're going to have a lot more fun, right? So what I would say is the more you care about production engineering as a data scientist, the more progress you will make in your data science work.
Todd, always a pleasure.
So good. Thanks for having me.
Muchas gracias. And
Claro, claro que sí.
Also, I love that you have the creativity on the yarn piece is amazing to me. I was laughing when I was watching that.
All right, so little plug. That is one of the examples that we are weaving through the book that we're writing for O'Reilly. So you will see, I won't say the URL yet, but you will see that is an example that we use throughout the book. So that's why it was on my mind.
It's great, man. I really appreciate that. And I thought it was hilarious. Like, well, you might want to actually suggest something that makes you money because you're you're a yarn seller, and who knows? It's tough out there for the yarn sellers.
Tough out there for yarn sellers.
Great, man. Well, I appreciate it. And yeah, you'll be in Slack. So keep the questions coming. He's in Slack. Get in there, ask questions. There are a few more that I don't think I got to fully. So that's that. Now we will be right back with the next talk. I think we got like a 2-minute break, and then we're getting right back at it with the folks from Etsy. Speaking of yarn sellers, oh, wow. All right, that's it. Here comes the hold slide. Talk to you all later. Oh. All right, all right. So we are back. What's up, Akash? How you doing? And Sheila is here too with us. Let me give you all a brief intro of Akash and Sheila, and then we can go ahead and hear their session. It is shaping up to be an awesome one. So, this is a talk that is led by Etsy, and Akash is a senior engineering manager, and Sheila is a senior machine learning engineer. Akash has extensive experience with startup companies, including Uyala, acquired by Telestra, Platfora, acquired by Workday, and Quantified, and also Blackbird, which was acquired by Etsy. Sheila, who has been working on Etsy's feature stores and data pipelines at Etsy, completed her graduate studies in operational research at Columbia University. In this talk, you'll hear how Etsy uses real-time feature logging to capture in-session / trending activities, build a tight, unified feature store for sharing features across models from different domains, and serve featured data at scale with the eventual goal of powering a reactive system. Wow, that was a mouthful. I hope you guys can articulate it better than me. That's awesome. I'll leave it for you, Akash and Sheila. Thank you for joining us. I'm looking forward to this.
Great, thank you. So hi, my name is Akash. I'm here from Etsy, and here's Sheila. We both are here to talk about our unified real-time ML data pipeline and how that helps us in training and serving of machine learning models. So what's on the agenda today? We're gonna start with an introduction to ML at Etsy and what are some of the unique challenges facing us. We're going to talk about our unified feature store and how that's enabling a lot of interesting work. And then we're going to go into the details of how a feature logging pipeline helps with training and serving of models. And finally, some of the real-time ML applications that are enabled because of it. So Etsy's mission is to keep commerce human, and we're a global marketplace for unique and creative goods. We're a home to a universe of special items, from like unique handcrafted items to vintage treasures. So we're essentially a global marketplace, and just to give a sense of scale, we're about 82 million active buyers and 4.5 million active sellers, and about $10 billion of transactions took place on Etsy in 2020. So I hope that gives a sense of what we're dealing with. And our job at Etsy is to connect the sellers and the buyers, so who have different passions and creativity. So buyers are coming to Etsy with a particular vision in mind, and sellers are using their creativity to provide products for that. And the question is, where is machine learning in that? And actually in a lot of places, as we will find out. As an example, if you search for planters on Etsy, you get about 300,000 results. And there's no correct answer, right? So there's a huge diversity in not only the functional aspects, so like the color or like the price or where this listing is from or when is it going to ship, but even in things that are not as discrete and cannot be described in a concrete, discrete label. So these could be aesthetic, style, many latent features, and we'll see how a feature pipeline needs to account for that. The second point I'll make is that when you come to Etsy, I might like the Pokemon planter, Sheila might like the llama one. So our individual preferences are truly what need to be taken into account. So there's a big need for a personalized shopping experience. So overall, what's so unique about the ML challenges here? We have about 85 million items, which are ever changing. We're driven by personalization. As I mentioned earlier, our items are not just different in functional characteristics, but also in the latent and the non-discrete space. And that's where personalization helps us show the users the most relevant items. A key piece on all of this is real-time machine learning, because a user's preferences also change in real time. I might come to Etsy looking for a particular item and then be inspired by what's shown to me and start looking for something else. So, overall, we're saying that real-time machine learning and personalization, these two are the keys in surfacing relevant content. And our models have to be personalized, so take into account user preferences that are changing, and real-time adapt to real-time preferences as well as aggregate trends. So we're gonna discuss how we've designed a real-time data pipeline to achieve that. And over to Sheila now.
Hi, thank you, Akash. So hi everyone, my name is Sheila. I'm the tech lead for ML Pipeline at Etsy, and I'll be going into details about our real-time machine learning pipeline solution. Well, first, I'll be talking about the feature store, which is a central part of our solution. It's implemented with a columnar structure for easy scalability, enforced with a type schema, which we'll talk about in just a bit. The goal of the feature store is to provide us a centralized way of storing and accessing features for training and serving purposes. There are many designs that go into this to make it easy to work with while maximizing the feature freshness and the quality, which is really important for model training. Well, it all starts with storing various types of features. Could you go back to the previous slide? There are two major types that we consider. One is called batch features, which is generated and updated daily. And the other one is called real-time features, which gets constantly updated throughout the day with often sub-second latency. Both batch features and real-time features can be aggregated over some time window, like the last 30 days or the last 30 minutes. And they can also be characteristic features, for example, the status of a listing, which can get constantly changing. So for those, we stream update into our feature store once detecting a change on that information. We made our feature store a centralized place for all features so that it can be shared across products, such as recommendations and search, and many duplicated efforts can therefore be avoided. When designing the table, we put different types of entities. For example, we have user entities, we have listing entities, and we put them in separate tables. We chose a NoSQL database for its dynamic schema and horizontal scaling. We apply the database with a logical structure so that each feature source is mapped to exactly one column family, as you can see from the graph. Each column family can house several features coming from that same feature source. This design will benefit us in many ways. The major benefit is the asynchronous feature update. Since each feature source is grouped into a single family, updating a particular feature source is made much easier to our feature store. From the diagram on the upper right, you can see that different feature sources can get ready at various different times. Once a feature source is ready, we immediately start the asynchronous upload to update the associate family in the database. This would optimize for feature freshness and also make the on-call process easier, since each feature source can now have a direct owner for contact. The other benefit from the columnar structure is its ability to follow the typed schema we use for our features. So, well, first of all, why do we need a schema? A schema can help us in many ways, and in particular, help us automate a lot of processes and validate data for quality control. This schema we created was shared across all applications so that we were able to read and send data between different applications smoothly. On the right-hand side, we show a simplified example of our schema for a simple feature family. So the family name would be basic, and there's two features housing under the family, title and price. And from the graph, you can see how that's related with the database structure in our feature store. Adding and testing new features are also easier with the help of the schema. So to do that, we start with updating our schema with a new feature family called new family here. An automated process will then pick up the schema change and register a new family in the database sandbox for testing. Before a new feature source is uploaded, it would also be validated against the schema to avoid sending bad requests to the database. Another important automation triggered by the schema update is the feature metadata template. So this contains important information about what that feature is, what's the source of the features, name, type, the status, etc. And the developer of this feature is responsible for filling them out before officially adding the features to the store. We also expose these metadata files to a web page for increased visibility and readability for customers. As a result, our schema plays an important role to connect multiple applications and processes together. It helps make our life easier in many different ways, from database control, like the one I talk about, registering new columns in the database, to data validation, like how we are validating our data against our schema, and from facilitating feature access, some of the schema generates automatically some functions to fetch the features, and all the way to promoting documentations like the metadata files I mentioned. Now that we've talked about the feature store, let's dive into training and surveying using the feature store. Specifically, we'll be touching on feature logging, which is a solution we implemented to overcome a lot of challenges we faced in the traditional development environment. So first of all, training data is formed with two major parts: attribution labels, which can be like a purchase or a click action at Etsy. And there are also features associated with the attributions. For example, user features and listing features. So user feature in this case can be like a contextual features, and listing will be our candidate. So listing would be the candidate features. Traditionally, there are two ways to generate training data. One way is to do multiple feature source join from different places and join that together with the attribution label so that we can generate the training data. And the other one is to join with a daily snapshot feature store, which already contains those multiple feature sources, and join that with the attribution labels. So both of them are completed offline in a batch job fashion. Although it may sound flexible for the development, it actually poses some major challenges when it comes to model training. So first of all, it creates a training serving skew due to the often inconsistent feature processing between training and serving. And secondly, it's not possible to access real-time features easily, while being more real-time is our goal. And finally, either method also poses some unique challenges like high cost for multi-joins, adding new features are difficult, like it just makes them not so ideal to solve our ML problems that we are interested in. So we introduced feature logging as a solution to overcome those challenges. The goal of feature logging is to log the exact features that are available at the inference time to train our models. By logging features in real time, we brought this offline process, like this offline batch joining fashion stuff, to online key value fetching. Moving it online makes it possible to access real-time features. This ensures us to record the most accurate real-time information available at the time of inference. Being able to generate this process on real time also enable us to get real-time training data, which Akash will talk about the applications later. The diagram shows when a request comes in, the reactive system will talk with the feature service and then pass the features to model layer. So that's the inference process. And it will simultaneously trigger a request to the feature logger so that it's able to log features through Kafka and then save it. Here comes the important part of how feature logging helps us solve the problem. So feature logging happens asynchronously right after the inference. So it's able to capture the same feature used for the inference with minimal discrepancies. Therefore, minimizing the training skew that we talk about is one of the major challenges we had. Not only can it record features used in inference, it can log basically any other features available during the time of the request. For example, a user's recent actions for personalization needs. Because feature logger lives inside the reactive system, which talks with all essential services other than the feature store as shown in this graph, like candidate service, model layer, it can also log information from those services. So for example, it can log candidate information such as candidate scores, candidate sources. It can log models information like the model scores and stuff. If you have an ensemble model, it can even log the intermediate model scores and things. Plus, it has access to the request itself, so it can log request metadata for debugging purposes. So all of those informations would help with downstream analysis, and it can power many, many explainable ML applications. So both feature logger and the inferencer needs to talk to the feature store at request time. So for that purposes, we use a smart feature selector to determine the exact list of features we want from the database. The feature selector is automatically generated based on a model config or a logging allow list. The right-hand side shows an example of our allow list, where features are represented in a way very similar to our schema and to how our database is constructed. The feature selector then simply extracts this information to build a database filter shown on the right-hand side of the arrow. Schema also plays an important role in the inference and logging process. It guards against bad data when we attempt to log features to Kafka. It also generates deserialization functions and many other functions that get shared between the inference and logging process to ensure consistent data processing to further minimize the skew. Now I'll pass back to Akash to talk about real-time and personalization applications that can be implemented with our pipeline.
Thank you so much, Sheila, for that great overview. I'm gonna dive into what this enables, particularly in terms of real-time and personalized machine learning applications. So the first one is that in-session personalization with feature chaining. So initially in my talk, I talked about how user preferences are changing in real time, and they're changing very quickly when they're on the site browsing through items, whereas listing content is relatively static. That's not changing as frequently. But there is a need to match these two, right? And we incorporate users' recent interaction and compose or combine them with pre-computed static features. And this helps us better capture what the user's shopping mission is. So we'll dive into an example of that. So an example of this is a feature where, say, we want an average embedding of the last 5 items a user has clicked. So let's first see what all is involved here. So the embeddings could be pre-computed. They could have been generated by any different algorithm and could represent a particular listing, right? So there are 80, like I mentioned, there are 85 million listings. Each has an embedding. We've generated that. We've stored that somewhere. For a user, we need their last 5 clicks. And we can collect that. We're collecting event data, and we need to combine those two now. And the aggregation function is how we help combine that. Now, why are we doing this? Traditionally, the listings, the embeddings only represent the listing, but we would like to incorporate users' recent information to also represent the user in the same embedding space. And this is extremely powerful because then you can better match the users and the listings that best serve their needs. So an example architecture is that users' clicks are coming into the site. We have a streaming service that's ingesting all those events. We're chaining or we're composing those with pre-computed listing features, and then we're getting chained features. So more concretely, we get the last 5 items of a user. we combine those with the embeddings to get the average, embedding of the last 5 items. And that becomes an input into our personalized ranking model. And of course, we're using the other, features from the user feature store or the query or listing feature store that we've talked about. But by doing this training, we're able to incorporate the composed features and combine real time with pre-computed features. Moving on to the second application of real-time feature logging is drift monitoring as well as validation. So because we're logging our features from the reactive system in real time, as Sheila mentioned, we have built a simple Kafka Stream application which can ingest these feature logs. And this is extremely powerful for validation purposes. So by logging these features in real time, we can see, is there any error in those feature logs? Are we adding some, are we missing any values? Are the feature values out of range? So we can catch these bugs or errors, any distribution outliers very quickly. Our teams can react and we can fix the pipelines very quickly. But one of the applications which we're starting out with and which we're very excited about is this feature data monitoring and drift monitoring. So understanding the feature distribution and how they're changing on a day-to-day, and being able to explain our models with it, that's like a key here. And that's where I think a lot of explainable AI systems can also plug in, and they can ingest this real-time data stream. Cool. Okay, and moving on to one of the actually my favorite application of the whole real-time ML pipeline, which we've started on, is a bandit application. So traditionally, multi-arm bandits are used to dynamically allocate site traffic to different variants. So what do I mean by that? I basically mean users are coming into the site, and we can use static A/B tests traditionally to figure out, oh, do we show them bucket A or bucket B features? But in a multi-arm bandit, we can dynamically adjust it. We can say today 40% will see this, tomorrow 50% will see this, and we can adapt to their needs over time. These bandit applications are very useful and powerful for in search and recommendations land. Particularly in candidate selection and ranker model selection. We'll talk about candidate selection just now. A key thing here is that contextual bandits are even more powerful because they take into account the real-time context. They're not learning a context-free. They're not learning a global setting, but they're able to incorporate what this user wants, what's available in real time. And that really helps us, serve them even better. So we'll see that in an application. Okay, so diving in. So the problem is for candidate selection for recommendations. So on the right side, we have a first pass candidate selection. So we have different candidates. So we have visually similar listings that have been purchased together, or TF-IDF listings. So these could have been generated with different algorithms. So like visually similar listings have been generated with embeddings. Co-purchase listings have been generated through, co-purchase matrix or count. TF-IDF, traditional information retrieval. So these are candidate sets, and concretely, they are a pre-computed list, right? So you're saying for user A, these are the top 100 candidates. For the user B, these are the top 100 candidates. So you have these candidates pre-computed. You have a second pass ranking model, and this ranking model can rank these listings. So it can tell you, hey, if I give you top 100 listings, which ones to show to the user. Now, what we would like to do is figure out what is the combination of this candidate set that we need to surface to our users. And specifically, we don't want to just come up with one global combination. We want to be able to do it at the user level. And that's where contextual information comes in. So this is where a contextual bandit system helps us, where we're going to fetch the user features from the feature store, which becomes a source of contextual information. We're going to fetch real-time streaming features, which also becomes a source of contextual features. So that's similar to the chained features I just talked about. And how are we learning this bandit? So if you look on the left, we're getting the attribution events, which are the clicks, cart ad, or purchases. And then we're getting our users' queries, which are the ranking models. And so based on those, we're able to log our features, we're able to get our attribution events, and we're able to learn this mandate to best learn the, what are the candidate set combinations. So yeah, that's a simplified view or a high-level view of how we're using contextual bandits for candidate selection problems. So to summarize, there are many applications of our pipeline, starting from sharing of features between different teams and models, real-time data validation, which I talked about, like especially explainable AI as being one promising one, in-session personalization being like, personalized features such as change features, training models across products. So that's something which I didn't dive into, which is that you can share, because we have a standardized schema, we can share our training data between different models. And the two of the future applications, one of which we dived into was contextual bandits. So how we're using contextual features to serve, personalized candidate sets. And one really promising one in the future is online learning. So because we're logging our features and our attribution data in real time, we can now update our models more frequently. So hope this was a great summary and this helps folks, get a sense for how real-time and personalization is key at Etsy, what our feature store structure is like, how we're using feature logging to train and serve models, and some of the applications. So if you're interested to learn more, please check out our blog at etsy.com and code as craft.
Excellent. Thank you, Akash and Sheila. You all got time for a few questions? I think we still got a few minutes on the clock.
Sure.
Sure.
Yeah. All right, let's do it. There's some good ones coming through. And I must say, you took some seriously complex subjects and you were able to distill them down into very understandable bite-sized ways. So props to whoever was doing the design on this. That was very well done. First question coming through is for Sheila. How do you store on disk the flat view of all features coming from the same family? Or sorry, do you store on disk the flat view?
Cool. I'm happy it's a yes or no question. So when we have like single feature family, that basically means the single feature source. So that means like all the features from that source is generated under one job. So yeah, short answer, yes. After one feature source is generated, those are saved on disk in some format before we can upload that to our feature store. And afterwards, we can delete it once we get a snapshot of the whole feature store. Well, we still keep a snapshot of the feature store just for some of the offline analysis purposes and stuff. But yeah, they did get stored on disk in some format and then get deleted once the TTL is passed.
Excellent. So another one for you, Sheila. So the stream and batch jobs load the data into a single database that users read from to retrieve their features for both online and offline workloads. What database are you using?
Okay, interesting question. So the database definitely gets both real-time features and batch job uploads, but the way to access those features currently are only online, like through online inference or online feature logging. In terms of the database that we're using, I don't know if I can say it, but currently we use Google Cloud Bigtable. Yeah.
All right. And if you can't say it, we can edit that out later. Don't worry. Just tell us. No problem. So there's one more. Maybe Akash, you want to give it a go. Have you observed any correlation between model performance and the freshness of features derived from real-time data?
Yes, we definitely have. I don't know how much I can review, explain without revealing actual results. Well, we've definitely seen, okay, let me just leave it at that, that there are definitely some aspects of the site where this matters more. So there are some models. So if you've like added an item to your cart and then you're doing it, then it's like, hey, we really know what you're looking for. So then it matters more. So there are definitely some models where it matters more, some portions of the site where it matters more. And yes, we've seen the real-time features as well as fresher features matter more. Yes.
All right, last one, and then we'll go to the break. Is there any limitations you have experienced due to computational complexity of contextual bandits in real time?
I mean, definitely, it's a very big task to monitor them, and that's what we're like excited about. Like, you know, it's just the replayability of this is actually a really big challenge. That how will you? It's an online system which is going to learn in real time, but you also, how are you going to learn the policy per se offline? That's where a lot of the challenge is. So it's not just as much about like enabling it in production, but also like being able to learn that and observe that. That's where a lot of the investment goes in.
Excellent. Okay, I lied. There's one more, and we still got a minute, so I'm going to ask it because people have been loving this talk, as of course they would. This has been super informational. Mike's asking, how do you manage cost attribution, and or do you do that at all?
We definitely are managing. So one of the things about having a centralized feature store is that we have individual feature owners. So that's on the feature generation side, where we can see like which team is generating the features. But I think the question, if I'm understanding the question, the real point of the question is that, you know, you're building a lot of these things once, and then you're trying to add, you know, you utilize them in different models. So the cost is then shared across those applications. We've made some efforts on attributing and, you know, understanding it fine-grained. I would say that we're not as fine-grained as we would like to be, but we're definitely on that path. Yeah.
Yeah. Asking about the dollar cost.
Yes, exactly.
So excellent. This has been amazing. And Akash and Sheila are both in Slack. So if you have more questions for them and this incredible talk, go ahead, get over there, get into Slack and ask them. Thank you both for this. This was awesome. All right. Now we are going to have the next talk. Well, yeah, we can share the slide right now because we have about 4 minutes until our next talk, and there are a ton of people coming for the next talk. So get ready. Hold on to your seats. We'll be right back. right, everyone. Well, that was fast, huh? We are back for the next session. Gonna be having a lot of people in this session. Exciting to present it. The team from Deloitte and Diego from Algorithmia are teaming up. Diego is here, and actually, I have one of the swag bottles that Diego gave, but now I just realized I left it in the kitchen when I was refilling my bottle of water. But Diego, I will say thank you for donating some swag. And to the rest of the speakers here, let me give them a little intro while we are. Oh, I just got it brought to me. There we go. Take a picture of that. Diego, you're awesome, man, except it broke. I'm looking for another one. I need to I need to talk to you about that. Don't expect every one of them will break, but you know, mine, I still need my replacement, Diego. This is not how this is supposed to work. Anyway, we've got Diego, Julian, and Paul all going to be talking to us today about how this building a best-in-class customer experience platform goes. I'm pretty excited for it. I hope you all are too. And my time's up. I'm going to get out of the way and let you all take over.
Awesome, thanks, Demetrius, and we'll see what we can do about the bottle. But thanks for the product placement, always appreciated. So let me go share my screen here real quick, and let's start up. Really excited to be talking to everybody today. Can I get a thumbs up for anybody? See my screen? Make sure we're all good here. Great, excellent. Oh, yeah. So super exciting talk, today. Really excited to introduce Julian and Paul. They've been doing some really, really interesting stuff in the machine learning space, especially when it comes to customer experience. And in particular, one of the things that I'm, particularly excited about what we're talking about today is a really interesting methodology on how to actually build out a platform, what to optimize from kind of like cost and thinking, and the importance of operationalizing ML, but not just operationalizing it, but actually making it sense from a cost per action perspective, and tying it together to how do you actually go and build these platforms, operationalize them, run them at scale. So with that said, I'm going to pass this on to Paul, who can lead us off here.
Thank you very much, Diego. That's fantastic. And, big welcome to everybody. And thank you for attending our presentation. I am the CTO of a team in Deloitte that is responsible for building a CX platform to sell to large enterprises. The mission is to deliver an end-to-end capability to large enterprises, which offers very short time to value, low total cost of ownership, and high performance. And it's probably not even clear to quite a few people why Deloitte would actually be engaged in hardcore engineering. So I think that's an interesting, part of this, presentation in its own right, because there are lots of things going on in the market that are actually forcing us to engage in, hardcore engineering now in a way that perhaps, as a firm, we might have been slightly less interested in the past. But, I'm just going to set the scene. I'm going to talk a little bit about what an end-to-end CX platform looks like, go into some of the components, how we go about choosing technology components that we're going to put in that platform. And then I'm going to pass to Julian, who is our lead on decision automation, and he can talk more about some of the challenges that he's faced. But just as a backdrop, if you consider our large clients, we're in a very interesting time now. There are, technology continues to advance particularly quickly, but I think in the place of, or in the domain of machine learning, some of those advances over the last even 5 years offer potentially very large performance and efficiency gains. And what we see is that large enterprises are really just struggling to implement those things. And why is that? Of course, it isn't anybody's fault. It's the fact that those large those large tech stacks, so those enterprises, they've evolved organically over many years. They are trying to service large numbers of teams with different applications. You have individual teams making their own choices about such technologies, though they're often duplication and overlap, trying to deliver those services across a wide range of devices. And unfortunately, it just means that those stacks, they have a lot of undocumented dependencies, and it's just hard to swap out any component that you may want to swap out. The result then is that those enterprises are finding it hard to keep up with the latest technology changes. And they're kind of sitting there seeing some of these really potentially dramatic improvements in performance, offered by these technology components kind of disappearing over the horizon. So how do you address that problem? And that's what I'm going to talk about. And this is really what we have been building internally. But before I do that, I just want to look at, what is an enterprise CX stack, and, what are the pieces we care about? I'm going to focus on, the part here that we most care about here, this audience, but I think it's just good to put it in context. So just looking at the left-hand side here, basically we want to connect with as low friction as possible to any and all data sources that we believe are going to help us characterize the relationship between a consumer and a brand. And that's going to be everything that you might expect, like campaign history, any interaction from a consumer to the brand, whether that's web, whether it's an app, whether it's through the store, call center, whatever it may be. And we may also want to connect to external data sources. And increasingly, it may be things like we want to supplement our ID graph with an external party. We may want to get, for example, brand market share in a DMA or a market area, because that helps us characterize a context with which a consumer may be interacting with a brand. We then want to bring that together in some kind of customer data structure. We, in fact, use a Snowflake, and have been on Snowflake for a couple of years now, and I think it's turned out to be a really good choice. One of the big themes inside that customer data management structure has been ID resolution, in significant part driven by machine learning requirements, where we want to make decisions at individual consumer level, typically or often in real time, taking into account particular contexts. So ID resolution has become a particular theme. If we just move to that middle section, which is possibly the most interesting for this audience, a very significant theme here has been, if we look at historically how customer data has been structured, it's been primarily structured to support human decision-making. And really no surprises here in that large enterprises, 99% of operational IP in large enterprises, so the people that are pulling the levers to change things, resides in the minds of humans. And so not surprisingly, being considered the primary use case for customer data up until relatively recently. What we're now seeing is a requirement or a desire of large enterprises to move that operational IP from effectively the minds of humans or the control of humans to automated processes using machines. And so suddenly we have this requirement where we need to structure data natively to support machine learning in ways that people never really conceived. A lot of the requirements for machine learning then are being pushed back on legacy infrastructure that was never designed to actually support it efficiently. So now consider we have that block here that I've called MLOps, so where we've got some kind of native preparation of data for machine learning, which is of course feature stores. And we want to create development environments and production environments so we can develop our models with the same tooling and data environment as we have for production. And obviously that then allows us to use traditional CI/CD mechanisms where we can promote models and pipelines that have been created in dev straight into production, and we know that they're going to work. The next section is that marketing orchestration. We want to then get that intelligence into orchestration systems, interact with consumers, and we want to feed that background on the left-hand side. One of the themes there is latency. So just consider that we want to take into account data and interactions that may have occurred with that consumer on the left-hand side, and change the way we interact with consumers on the right-hand side, perhaps with a latency of less than 50 milliseconds. So this is a real end-to-end architecture we have to think about here. Thanks, Diego. So, other things to consider as a backdrop, which make it very hard for CMOs, who are the typical owners of customer experience, to put this in place. They have a very low tenure. They have the shortest tenure of the C-suite. There was a report in May of last year in Wall Street Journal saying actually that the median tenure of a CMO was unfortunately only 30 months. If you consider the breadth and complexity of putting in place CX changes with technology, 30 months isn't very long. And then to compound that, there was actually an interesting marketing report by the Forney's marketing group, which said that 80% of CEOs didn't trust their CMO, or thought that their CMOs were not performing well. That's a horrendous statistic, which tells you really they probably don't even have the authority often inside the enterprise to really enact what they need to do. So look, it's a very challenging space. Just a couple of other things I would say there. Obviously, interactions with consumers, the number of channels, it's exploding, becoming more complex every day. Along with that, tracking complexity is being made more difficult across especially third-party tracking. So attribution of value is becoming harder, and it's very hard for our large enterprises often to actually recruit top engineering talent. The digital hyperscalers, of course, and often West Coast startups and other technology startups are more attractive often, so they may not have the resources either. Thanks, Diego. So, if we just, another backdrop here, there's this slide from chiefmartech.com just showing that the marketing technology landscape. So if an enterprise is to go about trying to select a piece of technology, this is just showing that in 2014, there were less than 1,000 marketing solution providers out there. Now there's over 8,000. And in fact, if we go back 25 years, there are probably only 20 or 30 we cared about. The fact that there are 8,000, how does an enterprise go about selecting which solution provider they should select? It's incredibly challenging. And actually, I was talking to the CIO at one of the top 10 retailers in the world 2 or 3 months ago, and he was telling me just the time for his team interacting with these solution providers, who unfortunately, of course, they are pitching their solution, which then the CIO or whoever it is has to put in context of their operation. It's just a very time-consuming effort. So incredibly challenging. Just go to the next one, Diego. So one of the privileges, if you like, of where we are, and we've reflected very carefully here, is we are delivering a lot of these solutions for large enterprise clients. So it really is worth the effort for us as a large consulting and implementation, and in fact now a development firm, to select best-in-class components, do all of the due diligence and research to make sure we really are identifying these best-in-class components. And Snowflake would have been an example of that, a couple of years ago. And then pre-configure an architecture and engineer it to deliver what we need for CX. And that is, of course, short time to value, low total cost of ownership, and high performance. And we can drill in and look at and qualify these vendors. But one of the big deals there, thank you, Diego, leave it there, is interoperability. How can you judge whether a piece of technology really is going to work with other pieces of technology in a seamless way? And of course, inevitably, the latest technology, if you want to use some of the highest performing technology, it's going to be newer. And so there are often going to be interoperability issues that need to be addressed. And so one of the things actually we consider very carefully is the culture of the team with which we're selecting as one of those best-in-class components, because we're almost certainly going to have to work closely with them to make sure we are very efficient on the interoperability side. Thank you, Diego. Just one more. So the last two from me are going to be, how do we judge then, where we should invest our effort? And again, one of the privileges for us is, what we would have done and what we still do with large enterprises when we're looking at workflows that we need to support for CX. We're very careful at looking at, where is all the friction in that workflow and where is the cost? And we're looking at human resource costs, machine costs, and direct software costs. And we're trying to calculate, given where that enterprise is today, what is the fully loaded cost per action? And if we do it using the best technology, and in this case, a pre-built architecture, what do we believe we can get that down to? So a lot of the focus of development for us has been, how do we take cost out of these decisioning activities? And you can do that fully loaded cost at a higher level. So for example, how much does it cost to build, deploy, maintain, and govern a particular machine learning pipeline for a year? That is an action, but you can also calculate it at the individual action level. and then compare that, if you like, to the revenue performance lift that you get by taking that action. And of course, we want to have a nice positive outcome there. Thank you, Diego.
And I think that this is super interesting because in the crowd here there's a bunch of ML engineers, and so optimizing functions is probably exciting to pretty much anybody involved. This is one of the first times that I've seen kind of thinking from an architecture perspective and a deployment, like how to bring this into that equation, right? In terms of like, so usually people think about, okay, how do I actually get this done? How do I deploy the model? How do I get the data? But really focusing on kind of like that optimization of like, hey, what we're trying to do is build automation here. And when we're building automation, we're really trying to like reduce the cost function of every single step to, the minimum necessary. Like, I think it's a really interesting approach to like kind of like large scale ML system building that not a lot of people have been thinking about. It's usually let's piece together these components, but not think holistically cost per action through the whole thing. So I know I got really excited when you were sharing how you and Julian kind of had to piece this together.
Yeah, again, Diego, you raise a great point. One of the things that we'll find is the financial systems and the tracking systems of activities are insufficient to track this in large enterprises today. So that's another theme that we're actually looking at internally, is making sure we have the financial and activity tracking metrics that allow us to get to those numbers on an ongoing basis. Yes, I know that's another background theme. We're not there yet, but it's coming. Next slide. Thanks. So look, the last thing is, we're saying we're kind of mapping, the impact of certain types of technology. And I'm sure many people here will have seen surveys, and this one is actually, Algorithmia did a great survey to look at how long on average does it take an enterprise to create and deploy a new machine learning pipeline. And the average in that report, and Diego can give us a reference to it, I'm sure, it was about 3 months. So with some enterprises saying, as much as a year. And this is absolutely validated by what we see. And so what we're looking at is, okay, where is all the time being spent in that 3 months? And how can we compress that most efficiently? So what are the technology pieces we need to get in place? And again, we don't have time to go in the details here, but just as an example, the use of feature stores, where we now have a set of features that are, nicely organized for native, machine learning activities, where we can expose those features both in the dev environment and the production environment, and where we can use the same tooling in the dev environment and production environment. We can hugely reduce the times for deploying a new model. And of course, maintaining it doesn't actually need a human in the loop there, provided we have effective governance, checks and balances in that pipeline as well. So thank you. At this time, I'm going to pass over to Julian. Julian leads our decisioning development, and he is the guy who has to face all of the headaches of actually making it perform from an engineering perspective in terms of throughput, latency, and performance. Thank you.
Yeah, so I'm going to touch on a number of the alluded technical challenges. As everyone I'm sure can imagine, a full list of said technical challenges would not fit on one slide, probably wouldn't fit in a half hour either, but I'm going to touch on a couple, and I'm of course more than happy to discuss them more. So I'm going to start with the first two technical challenges that we really face, which come straight out of kind of typical software world, which is we're trying to help companies build a nucleus for their machine learning, for their customer experience activities. And there's really two choices anytime you're doing that from a software architecture perspective. You can buy in heavy on these kind of platform-wide machine learning vendors or software components, doesn't really matter, who essentially want the entirety of your machine learning activities essentially to flow through some kind of very large central system. It doesn't have to be just one component, it can be a collection of components. But essentially that's building your machine learning stack on top of a kind of very central, very pervasive piece of machine learning technology. Or you can go the other way, you can build a kind of componentized software architecture stack where each of the pieces in that architecture are kind of the best individual piece, but they haven't necessarily been exactly designed to work with each other. And as I say, I think this really comes straight out of kind of normal software world. I mean, if you go to the web application community and you ask them, should I use a giant web framework that covers all the parts of the web of serving a web page, or do I use one routing engine, it's the same sort of story on a larger scale in our domain, I think, where we really have to deal with these two different ends. And of course, each of them have their own technical advantages. On the kind of platform side, obviously things fit better together to start, but in one particular aspect of that platform, things may not be as easy. So if you want to plug in a feature store to a platform that doesn't necessarily offer full-fledged feature management capabilities, doing so is not necessarily as easy as if you were assembling said platform out of components. Whereas on the other side, if you're assembling sort of component-based architectures, and now you experience a gap even within a particular component. So you've chosen, I'll use the feature store example again, you've chosen a feature store is missing some particular functionality. You may be right back in a situation where you need to deploy a large amount of infrastructure to fill in that gap in that part of the architecture. So just right off the bat, for us, really kind of balancing this kind of, this kind of spectrum of how you assemble an architecture out of the best components. Secondly is or thirdly, I guess, going to the third one here, I think a lot of folks in the software community and of course in the machine learning community, we're all still struggling with how do we deploy diverse infrastructure. So even things like I want to deploy a particular machine learning system into multiple clouds, perhaps for different companies. So this comes up for Deloitte, obviously, because we're working with different enterprises, each of which may be in one cloud. But these days, there are enterprises who are in multiple clouds at the same time, and managing infrastructure automation, infrastructure as code, DevOps lifecycle stuff, all of these technologies on the infrastructure side are still maturing, and they're kind of light years beyond where they were. But I think on the machine learning side, we still experience lots of challenges in infrastructure automation, and particularly when there are vendors or software components in your machine learning stack that you didn't write, that you pulled off the shelf, in how you take those components and integrate them with the rest of your infrastructure that you did build. These are kind of large, non-trivial problems for many enterprises to solve, which of course are more difficult the more kind of distinct components or distinct vendors might be in a particular stack. Kind of fourthly here, Paul mentioned all of these kind of nice latency constraints that everyone wants. Everyone wants the most up-to-date view of their customers, or in any machine learning system, the most up-to-date view of whatever it is that you're modeling. In many worlds, you can be extremely fast at, I can have models that are giving me answers up to the moment. But if in the marketing or advertising world, if you're ultimately using those models to drive some sort of platform that can only cope with daily updates, or some sort of platform that can only act on some much less granular timescale, then you're at the mercy of whatever's ultimately performing the orchestration for you. And so from a technical perspective, we all like to kind of focus on optimizing the kind of internal end-to-end latency within the platform itself. But ultimately, it's up to us not to forget that once stuff kind of leaves any platform that we're deploying, it may not be able to potentially keep up with whatever it is that we're outputting. And that can be from a latency standpoint, but it can also be just entirely from a, if you're outputting for individual consumers, and then you need to talk to a platform that only deals in way coarser segments, so kind of collections of customers, then making sure that those interfaces fit well to each other is, again, kind of a non-trivial technical problem. And the last thing I guess I'll say on the technical side or kind of technical challenge side is, I think the software ecosystem or the machine learning ecosystem is very strong when it comes to generic machine learning technology. So, go on GitHub, start Googling around for machine learning software technologies, and you're going to find 50 of them that look interesting to deploy into such a platform. But when it comes to particular domain or industry solutions, so I'm in credit or risk, and I'm trying to evaluate the particular risk that my customers have for my business, things get way less. The sort of ecosystem gets way less crowded when you restrict yourself to proper business problems or proper industry specific business problems. And so on the technology side, that puts the pressure back on us to kind of tailor those generic software libraries or solutions to hit the actual business problems, which basically means take software you pulled off the shelf potentially and need to add layers on top of it or tune it in the way someone might expect for the particular business domain. I think we can move to the next slide.
One of the things interesting, Julian, that I really like how you talked about it, but like, we can learn a lot from traditional software architectures, especially from kind of like service-oriented architectures where you're kind of building it as plug and play, right? You kind of look at every single component and think about it, hey, this component's good today, the component might need to be removed tomorrow, and this is kind of like one of the reasons where it becomes so hard to do things in like the platform-wide things, because those plug and play, I mean, like we've seen it over and over in traditional software, it is playing out in the same way in machine learning, where I am going to have to, when I think about architecture for the long term, it's particularly important, which kind of goes us to the next one, which is recipes for successful AI initiatives.
Yes, yeah, totally agree. Maybe to summarize here on the recipe for successful initiatives. So we want to automate as much as possible. We don't. Certainly from a technology standpoint, I don't want to be solving the same technology problems this year as last year. But even for customers who are paying, clients who are putting these machine learning solutions in place, the amount of time spent automating is well worth the return on not having to think about a particular model or machine learning problem again. So that we can move on to the next one, having automated the last one, kind of continuously moving forward in the level of sophistication is a big key. Overhead, we talked about the equation for cost before, but if we're spending a ton of money in overhead and driving very thin margins for a client, that's not efficient, and ultimately they'll go with something other than machine learning in that case if the overhead is too high. Shorter time to value, again, so if things are too expensive, it's less attractive. If things are take too long to get up and running, if there's too high of an initial cost for a client that isn't driving their marketing or decision making in this way, if it takes too long to get that up and running, also less attractive. So we need to find ways in the machine learning ecosystem to quickly get someone up and running using what they have without asking for a heavy lift. Lower total cost of ownership, again, over the lifetime of when someone's running this platform, that we want that cost curve trending down, and then reducing risk, particularly outside of the architecture itself. So we hope that the things on the top of this list ultimately help reduce risk. But that's always our goal, is to reduce the amount of uncertainty and ultimately reduce the amount of manual intervention required in any of these environments or systems. So I think that might be it. If we move to the next.
So that's been awesome. Thank you so much, Paul and Julian. I know both the Tekton and Algorithmia team feel extremely honored and grateful to working on the optimization of the machine learning architecture problem with you, which I think is a fascinating thing. And I think we probably have some time for some questions. We'd love to go ahead and answer those.
Does that mean I get to come back? I get to ask you questions?
Not about the bottle, though.
No, I caused quite a ruckus with that bottle comment. Sorry about that, but it is the swag that will be given away. Now, I want to know on this for Paul and Julian, when you're choosing stuff, how do you evaluate like if you're going into a company, how are you evaluating the maturity of the company when you start working with them?
It's a great question. So I think you can imagine, there's a variety of means. So we'd obviously look at the analyst publications, for example, as a starting point, look at all of the published materials, quality of those materials, then we'll engage directly with the party, ask questions, even in some cases interact with, if they're funded, the VCs, see what level of commitment and excitement they're seeing, try to gauge market traction, try and look at things like number of employees on LinkedIn, validate things that you're told, possibly take references from clients. And one of the things I was saying that maybe less obvious is actually the culture of the team with which we're engaging is really important, because it's a journey. And if you're trying to use often the very latest tech, guess what? It sometimes has sharp corners. And we need to know that we can go to that product owner and basically, we know those things will be prioritized and they will be fixed. So that's an important part for us as well. But interoperability, in the end, there was a question in the Slack channel there actually on how do you evaluate costs associated with deployments? And it's a very good question. There's huge variance in deployment efficiency and ease across these components. And inefficient deployment, where it looks like it's going to be very hard for us to automate, guess what? That impacts cost per action. Straight away, it hits your, hits your cost equation. So we do factor those things in, yeah.
Excellent. So another one coming through is, could you share some of the most typical use cases and pains of your customers that are looking to, and what they are looking to solve with the solutions you provide?
Yes, totally. One of the things that's going on out there right now is an increasing value being attached to first-party customer data. Why? A lot of, because of the challenges faced by CMOs in the last kind of 20 years, they outsourced a lot of their customer analytic capabilities. And now they're finding that actually outsourcing it like that, they aren't getting the kind of value out of the data that they need, and that they need to pay more attention to all components of first-party data that they collect through their own interactions. So they're trying to bring it in-house. So bringing that capability in-house is a big theme. And how do you maximize the value that you can realize from your own data assets? So I'd say that's a very big theme out there right now.
Excellent. And last one from me, I see there's some people typing in Slack, so we might get one more, but for me, I wonder about how you walk the line and you balance bringing on more complexity or just going with a simple solution.
It depends very much on the client, and that is a great question. So there are a spectrum of clients. Remarkably, some huge enterprises have no data science activities or decisioning automation at all, which is quite shocking. And so, yeah, we have a bit of a crawl, walk, run. So there is a light flavor of what we're talking about, which, if you like, is a stepping stone to take you to a full-blown enterprise architecture, which is what we're discussing. So absolutely. Sometimes you need to go in with something super light tooling, super easy and fast to deploy, and then use that as a stepping stone. So yeah, good question.
Excellent. Well, I think that's all the time we got for you all. Thank you to you three. That was awesome stuff. I really like this, the math you put up there. It was very cool to see the money that is being involved in this and the actual formula. So that's it. Thanks all. And if anyone has any more questions for these three, you can find them in Slack. Go ahead and just hit them up on there, and I'm sure they'll be happy to answer your questions.
Thanks very much.
Thank you so much.
Cheers, y'all. All right. So now we've got a little bit of a break, and then we're going to be hearing from Lack. Oh, man, Lack, I'm excited to have you come on here. But before you jump on, Lack, we've got 5 minutes, I think, and I'm going to explain how people can win some of these flashy algorithmia bottles, or some of the I think there's a Tecton bottle and a Fiddler AI bottle, and there's also a Monte Carlo hat going around. So all kinds of good swag that we're creating a swag bag of everything and then sending it to you wherever you may be. This is the new thing. All right. We had the applied selfie yesterday, which was awesome. And there's still some people throwing some selfies in there. Very cool. Let's see it. But in the funny channel or on Twitter, I'm going to ask you to put hashtag applied meme or hashtag applied GIF. And today we are going to use this as inspiration. I shared, I think, when was it? Like a month ago, I shared this on, hopefully you're seeing my GIF screen. I shared this on Twitter and we got some incredible results. Describe the machine learning tooling ecosystem in a GIF. Please, this is what some of us were born for. Here is the MLOps tooling system in a GIF. And so if you would like to win some swag, come share your GIFs with us or your memes. We are going to be asking you for memes and GIFs, and you can put them on Twitter, or if you are, and I'll put a link to this in case you want some inspiration. You can put them on Twitter or you can put them in the funny channel. It is excellent to see. So that is how you're going to win some swag today. As always, if you're super helpful in Slack or if you're asking questions, that will also get you some brownie points and some +1. If you share some selfies of yourself in costumes or with animals, pets, furry animals, then you will also get entered to win some swag. And the poll is still going. So I threw the link to the poll that we showed the results of earlier. That is still happening. We got day 1 results in, but if you want to give your results and talk to us about a model gone rogue, tell us in that poll. Now, I think that's it. That's all the updates that I got for now. Just come up with your own memes. There's already some memes happening. Come up with your own. Explain the MLOps tooling system in a GIF. And now in about 4 minutes, we're going to hear from Lack. I'm going to be right back to introduce Lack. And I think we got a hold slide that's coming up. So let's get that hold slide up. And then I'll kick it off to Lack in 4 minutes. Here we go. Lack. Paging Lack to the stage. We have got an incredible talk coming from a man, Lack Shmanan. So while we're waiting for Lack to jump on here, I'm going to give a little intro. And, oh, actually, I have Lack's book here. Hold on. I don't know if anyone can see me because there's a screen being shared here, but Lack and a few other bright folks at Google wrote this incredible book, which I never let get too far away from my desk. It is called Machine Learning Design Patterns. I highly recommend that you check that out if you have not. It is an awesome read, great to just familiarize yourself with everything that's going on. They talk a lot about feature stores in this, and go into a deep dive on Feast too. So, Lack, are you around? I hear you. I think.
Yep, I'm here.
There he is. All right, cool. Let me introduce you to real fast for everybody that doesn't know, the two people out there that do not know you and have not read your book. Let's go. Lack is the director for data analytics and AI solutions on Google Cloud, where his team builds software solutions for problems across industries. He also founded Google's Advanced Solutions Lab, ML Immersion Program, and is a published author, as I mentioned before. Get this book. Before Google, Lack was a director of data science at Climate Corporation and a research scientist at NOAA. Today, he's going to cover 3 patterns that are useful in creating large-scale and resilient data and ML pipelines. These patterns provide you a way to apply hard-won knowledge from hundreds of ML experts to your own projects. Lack, I'm handing it over to you. I'm excited for this, and I still don't think I can see you, so you might have to turn on your camera if it's possible.
Okay, I am, but the host has stopped it. So waiting for the host to let me start my video.
we cut you off, Lack. I'm sorry, man.
Yes.
Uh-oh. There
Absolutely.
he is.
Now I'm here.
There he is. And if anyone really wants to hear...
Demetrius, I love your new look, by the way.
Thanks, man. That's great. I was going to tell people too, because we were asking the question in the poll, should a data scientist learn Kubernetes? And if you really want a good answer on whether or not a data scientist should learn Kubernetes, go check out the video Lack and I did for the MLOps community. That is a brilliant reason why a data scientist should not learn Kubernetes. And I'll leave it for you, Lack. Take it over.
And it was so funny, right? So it was like, you're saying, we're going to have this next talk in Kubernetes, and I just had to jump in and tell you what my opinion was on the whole Kubernetes thing around data science. But today, I'm not going to be talking about Kubernetes. I'm going to be talking about machine learning design patterns that are useful for data engineers. Okay? So what exactly are design patterns? These are things that are pretty familiar to software engineers, right? These are formalized best practices for problems that happen over and over again. And now that we've been doing machine learning in production for several years now, we have built as a community a lot of experience in terms of what actually works in terms of machine learning. And we thought that this was a good time to basically start recording some of these best practices, because if you're new to the field, you don't know that this is the right, these are things that people have tried before, and here are the trade-offs, and this is why you use what you're using, the things that some of the names might appear in the APIs, but you might not realize the reason why you're doing things in a certain way. So knowing the design patterns, having names for them, really helps you become a much better machine learning engineer, because much better data engineer. So what we did was that we captured 30 of these design patterns in this book. And what I'm going to be doing in this talk is that I'm going to be talking about 3 of them: transform, stateless serving function, and continuous evaluation. Now, in addition to the book, there are example implementations of all of these design patterns in this GitHub repository. And so I really encourage you to go look at the code to give you an idea that this is how people actually implement this in real life. So what I'll be talking about here are primarily about the concepts, but these are all very real and implemented and part of many production ML projects and things that are used by a lot of teams. So let's start off talking about the transform design pattern. This is design pattern number 21 in the book, 21 out of 30. Okay? And let's kind of frame why we need this in the first place. So imagine that we have a machine learning model and it's going to predict the length of time that somebody is going to keep a rented bicycle. So they rent the bicycle at some particular station, let's say King's Cross Station in London, and they rent it on a specific date. And we want to be able to predict that if they rent this bicycle on April 22nd, 2021, right, and they rent it at King's Cross, how long are they likely to keep this bicycle around? This is going to be important because we want to stock bicycles. We want to know when to do maintenance on the bicycles, et cetera, et cetera. So in order to do that, we train an ML model. And the ML model basically takes a station name, it uses it as an input, and when we give it April 22nd, 2021, it pulls out Thursday and it pulls out the hour of the day, pulls out, let's say it pulls out 18Z, right? In London. That's the time that it pulls out. And it goes ahead and trains an ML model to predict the duration. Okay? So that's basically what we have. We have two inputs, station name and start date. We have three features that we have into the ML model. Right? We've pulled out the day of the week and the hour of the day from the inputs, and we use it to train an ML model. So this is great. We trained the ML model. The model now basically works, and it's basically, we take that model, we deploy it, and now we want to run this model in production. What inputs does the model want? Does the model take the station name and the start date? Or does the model require station name, day of the week, and hour of the day? It's pretty clear the model was trained on three inputs. So it's going to need three things, which means that this poor client here has to somehow know what the model developer did in pre-processing and feature creation in order to call this model. And this is a huge problem. This is what leads to training serving skew, because the model developer might have done everything in Python, and now we have to basically go find the equivalent thing in Java or JavaScript or whatever it is that we're going to be doing on the prediction system side to pull out the day of the week and the hour of the day, right? So the problem here is we've trained a model with the duration, we've extracted out the day of the week and the hour of the day from the data, and we've trained the model with three inputs, which means that whenever somebody calls this model, they have to know, okay, King's Cross is a station name, but they have to know that in the training system, Thursday was represented as 3, right, in quotes, as a string. How do I know that? How do I get a library that gives me that? And that is a huge, huge problem, right? And it's a leading cause of training serving skew. What we really want to be able to do is what we can do and say, this is BigQuery ML that I'm showing you. It's a SQL way of doing ML models. And the idea is that even though you pulled out the duration, which is the label, the start station name, and the start date, those are the inputs, you now basically say that the model needs to transform. And what it needs to do is to take the start date and extract out the day of the week and the hour of the day, and then train the model with the duration as the label and 3 inputs. And now that the model is trained in this way, we've kind of kept the inputs and the features separate. And that means that when we go ahead and do a prediction, it's as easy as saying King's Cross and the current timestamp. And the model, internal to the model, it has captured all the pre-processing and feature engineering that has to be done on the input data to get to the model. So as you can see, this becomes a lot simpler from a productionization standpoint if we take the transforms and we put them into the model graph. Now, what I showed you was BigQuery, ML, and SQL, but you can do the same thing in TensorFlow and Keras. So the basic idea is pre-processing that you're doing, put those transformations in Lambda layers in Keras. Because if you do it in your Lambda layer in Keras, now when you do a model.save, the Lambda layer also gets saved with the model, which now means that your model works on the raw input data. And therefore, it becomes much easier to productionize. So in this case, we're just showing you an example of, let's say that we want to take latitude values and basically do x plus 78 divided by 8. Well, normally you might do it in pandas and then save out the transform data and train your model on the transform data. And what I'm saying is like, that's a bad idea, because now you have to basically remember in every production system that you need to add 78 to latitude and divide by 8. I mean, who's going to remember that? How are you going to keep that up to date, etc.? So much simpler if you have these kind of simple scaling, formatting, clipping, all of these kinds of things. Throw them into a Lambda layer in Keras, make it part of your model. So this way, now your model, right? You have three things. You have inputs, which is the raw data, you have the features that you've created, and you basically go from inputs to features using these transformation layers. And this is the way, when you keep them separate, it basically becomes productionization become easier. So the basic transform pattern is that the model graph includes the transformations that you do to go from the inputs to the actual data that you use in your ML model to train the ML model. The model still uses three features, but the key thing is that the transforms are layers in your model graph. And because they're layers in your model graph, it becomes so much easier to productionize. Now, is this the only way to do it? Absolutely not. There are lots of trade-offs here. And in the book, we talk about two other patterns. We talk about TensorFlow transform, which is a way of basically making things more efficient so that you're not doing it in Lambda layers. We talk about feature store, which is another way of making things more efficient so that you pre-compute these things beforehand. But transform is the simplest pattern that allows you to limit training serving skew. So it's worth knowing, and it's worth implementing in a lot of your projects. The next pattern that I want to talk about today is a stateless serving function pattern. Okay? So why does this come about, right? Imagine that you've trained an ML model, right? You've trained a model that you basically pass in some text, and it basically gives you a classification, some kind of logics. Maybe it's sentiment, maybe it's topic modeling, it's something. Now, in order to basically call this method in, like when you want to predict with it, you would just call model.predict and pass in a tensor corresponding to the sentences for which you want the sentiment or topics or whatever. Now, this is problematic because what? You need the model in your prediction system. So you have to load and retain this entire model into memory. And that's pretty wasteful because a model contains things like the epochs, contains dropout nodes. It has a whole bunch of state that you don't really need for predictions. Secondly, the model typically is not thread safe. So you're going to have latency limits. You cannot basically just call this all the time. You cannot thread it, right? You cannot do things in parallel. And also, just as with the transform that I just talked about, you will often need to support a different input than what was used in training. So when you're doing training, maybe you just train it on a single sentence at a time, but in your prediction system, you want to take a paragraph and you want to split it into sentences and then call the predict on all of those sentences. And that's what your API needs to be. Your API that you're using for prediction may not be the API that you use for training. And so, relying on model.predict is problematic. So what do we do? Well, one way to do this is to export the model. So you basically take your model and you basically say, okay, I've written this model out, And now I can just load the model. And when I load the model, I just retain what are called signatures in the model, right? And the signature basically is the thing that you call, and the signature matches the input layer of the Keras model. So now you basically get a function, and you can basically call that function, passing in the whatever data is needed by that function. And now this function is something that you implement to invoke the model. So this is great, right? So prediction signature, you have this idea of a function that is separate from, right, the input layer, but the prediction signature matches the input layer. Okay, but if the prediction signature and the input layer are the same, then you still have abstraction problems because, hey, remember, you're still loading the model. So that all of those problems exist still now, and it only works in Python, right? So you still have your abstraction problems. So what's the solution here? The solution here is to use a stateless serving function. The idea is that you take this model and its serving function, you wrap it up in a web serving infrastructure, a web serving infrastructure that is capable of accelerating and running on like accelerated hardware like GPUs or TPUs. And you put that into a managed platform, a managed cloud provider like Cloud AI platform or SageMaker or one of those like services. And now basically this entire thing becomes a web microservice. So you still have your model, but you've wrapped up your model into a framework that's capable of being accelerated in another framework that gives you managed services that automatically scale up and down, right? Depending on the amount of traffic, they do load balancing and all of those things that you would expect of a web microservice. So now, as far as a client is concerned, they just need to give you a JSON and you will give back them a JSON. It's now a REST API. And they can forget that they're calling a machine learning model with tensors and all of that stuff. They're just sending you a JSON request and getting back a JSON response. So why does this work? It works because this ability to scale web endpoints, and remember, this is what TensorFlow serving does. It gives you a web endpoint. Auto-scaling a web endpoint is a well-understood engineering problem, right? All of your cloud providers know how to do that. No big deal. It's fully managed. The cloud platforms abstract away the managing and installation of like TensorFlow and all of that stuff. They basically give you, if you use AI platform, you use SageMaker, you use Azure, right? You basically get this, all the installation stuff out of the way. You don't have to worry about it. The prediction system is already done. Now, because you're sending back and forth REST APIs, it's language neutral, right? You can do this from Python, you can do this from Java. You can even do this from PHP if you want, right? Everybody knows how to speak HTTP. And because these are web applications, you have a really powerful monitoring system, right? So all of your MLOps become a lot easier because MLOps is now just DevOps. You're monitoring and throttling your tools, and your SREs know how to do it, your IT admins know how to do it, your DevOps people know how to do it. So this is why you basically have these three layers of the onion, and it's super useful to be able to do that. Okay. Now, how does it matter to us as data engineers? Well, remember I started out by saying you need abstraction, and the serving API, the default one, basically gives you the same inputs as the Keras model, but you don't have to live with that. You can change the input signature. So what you can do, for example, and I'm showing you a very simple example. Let's say that every time somebody gives you a file name, they also give you a sequence number. And when you return the result for that file, right, you also need to provide the sequence number that they gave you with the file. You need a pass-through. Well, the sequence number was not an input to the Keras model, so it will not normally be present, but it's very easy to add it. This is what you do. You write a function, you add a TensorFlow, you say that this is a TensorFlow function, you get the original serving default, you make the original call, you get your result, but this result is a Python dictionary. So go ahead and add in right? Here are the file names you gave me. Here's a sequence number you gave me, and there is your result. So now you basically get back a JSON that has what the model would have normally provided as output, but also some input pass-throughs. So now when you export the model, when you save the model, you can save it with two signatures, one with the original serving default and another one with an input pass-through. And then when somebody calls your model, they can choose whether they just want the bare bones functionality or they want this additional functionality. And obviously, as you can see, now it's just basically based on the JSON request, and you can do anything that you want in here. You can call your backend database, you can enrich the data, you can do all kinds of amazing things in this prediction signature, because this prediction signature is separate from your ML model. So this gives you a lot of abstraction and a lot of like new capabilities that you can add to your ML model. So that's why you have this concept of a serving function and this idea of having it be stateless so that it auto-scales. The third pattern that I want to talk about is that of continuous model evaluation. If as a data engineer, one of the things that we often want to put in place is a way to detect things like data drift and concept drift, right? So continuous evaluation is well after the normal parts of your ML lifecycle, where you're basically exploring data, building an ML model, and you're deploying the ML model. At some point, you will want to start monitoring a model that you put into production to see if it is still performing as you would like it to perform. Okay, why? Because models become stale over time, right? For example, right, when the credit card started to have chip-in-pin technology, right, it became really hard to fake a credit card in the physical world. So many more fraudulent transactions start to move online, which means that any fraud detection model that you trained is going to be very, very, very sensitive to the fraction of chip and pin transactions in that data set. So over time, this probability distribution is going to keep shifting, and you have to keep retraining the model every time the performance drops. Okay. Another reason for concept drift is that, like, if you have a word model, the meanings of words changes over time. Well, when people talked about trolls, right, they were talking about dolls before, but now they're talking about annoying people online. When people talked about cells, they were talking about prison, but now they're talking about mobile phones. We talked about cloud, they were talking about meteorology, and now we're talking about data centers, right? So these words acquire new meanings. So you have to retrain models that are reliant on language. Okay, so the other thing that can happen is that the probability distribution of data itself can change over time, and that basically causes models to become stale. So how do you do this? You need a way to compare a model prediction with ground truth after the model has been deployed. So the way we do this, right, is how do we do this? Well, because we have a model already deployed, it is receiving new data all the time. That's a key thing to realize. It's receiving new data all the time, and it's making predictions on that data. And in many cases, we can go find the ground truth. The ground truth might be delayed. So imagine that you are basically training an ML model to predict whether somebody's going to abandon a shopping cart. Well, 24 hours from now, you know if the shopping cart was abandoned or not. It's just delayed, right? Other ways is you might have to basically save your part of your input data, send it to human labelers, and have them label that input data, and that way you get your ground truth. So the idea is that you save the predictions, not all your predictions, because that will slow things down, but a fraction of your predictions, usually like 0.5% or 0.1%, 1 in 1,000 predictions, so that you can basically compare it with the ground truth. And so what you will then get is a table that looks like this. Here's the model, here's the version number. At this time, you basically go ahead and you had your this is the text that you passed as input. This was the output that it provided, the probability, the output thing that now the actual. Then you have to fill in the actual ground truth when you do have it, right? And you might have it through human labeling. You might have it because later on, right, you basically have a better way of finding what that actual answer is. And now you go through your sampled predictions, and now you have a new data set. And what you do is that you compare this data set over time. You say, okay, let me go ahead and find the evaluations for more than a month ago, more than a week ago, etc. And you start comparing it. And what you will start to see is that as time goes on, performance will start to dip. And you might set a threshold and you say, every time the performance goes below a threshold, go ahead and retrain. We can, once we do this, it also allows us to compare performance across model versions, right? We have a new model. We can basically take the same input and split it. And we have this new model running in the shadows. So the first V1 is what is being used in production. We have a shadow model, which is V2. That is, all of the traffic is being sent to it. And we're saving the results of both V1 and V2, a sample of them, into our evaluation database. And then once we get the ground truth, we compare against that ground truth. And then we basically see when do we switch over from V1 to V2, right? So how do you get that? Oftentimes, it's just a matter of time, right? A month later, you know which transactions are fraudulent, right? When somebody basically comes and complains about it to you. Now, a few days later, you know which shopping carts were abandoned, okay? Other times, you may have to actually do human labeling. Okay, or you might, if it's a medical situation, you might know if this patient had to be readmitted, etc. So you basically use that. You look at how the performance changes over time. You retrain, and what you basically get is a performance curve that looks sort of like this. Okay, and the idea is that if you can do this much more often, now you basically get the ability to maintain a much higher performance, right? So the idea is you start setting this up so that as you get new data, you take that new data with the ground truth, you throw it into your training data set, you retrain automatically, and you set this up as an automated process. Okay, so if you don't do this, what else are you doing? Well, what you might be doing is that you might be doing things in an offline environment. So you train a model on some data, you basically put it into production. 6 months later, you take that old model, you now have new data that you've collected over the last 6 months, you evaluate on that data, and if it's not good enough, you start doing the retraining. What we are doing with continuous evaluation is that by saving this sample of predictions and over time, we basically get the ability to continuously improve it. So with that, like I'll come to the end of my talk. We talked about 3 patterns here. Again, 3 of the 30 ones that we cover in the book. So there's the link to purchase the book. You can get a free trial to read the book online. That's the code for that trial, MLDP, Machine Learning Design Patterns 20, because the book came out in 2020. My co-authors, Sarah Robinson and Michael Munn, you see them on the slide here. Follow me or Sarah on Twitter. Michael has a life, so he's not on social media, but both Sarah and I are. So you can follow us on Twitter. You can read our blogs, and again, all of the code to illustrate how this all works is on GitHub. Thank you.
Michael has a life, so he's not on Twitter or social media. I love that, man. I love your presentation. That was great seeing you again present. You got a minute to answer some questions?
Absolutely, absolutely.
Awesome, awesome. So, of course, I asked you all the questions I could ever ask in the hour that we spent together, and I highly encourage everyone to get this book. Definitely, I got it. We've been talking about it in Slack. It is very cool. The question coming up, is there going to be a new edition of your book?
Is there going to be a new edition of the book? I mean, there over time, I'm pretty sure that we will identify newer design patterns, and some of these design patterns will become obsolete. And so I imagine that we might want to do a new edition of the book. We're not ready to think about it yet, right? Writing a book is a largely thankless job. It takes a lot of time away from doing the things that Google pays me to do. So yes, maybe. At this point, I've only identified one idea that I might want to include, which is about how to represent geospatial data. So maybe I might just do blogs instead. And once we have enough material in blogs and articles, we might consider basically doing a book. But I mean, and the other thing about doing a book is that you always have to drop things. I think 30 is about the limit. So we'll have to go back and take a hard-nosed look at the ones that stop being relevant over time. At this point, the book is only about 6 months old. It's all pretty relevant, so I don't see a need to change it immediately.
Yeah, and they're already asking for the new updated version. Oh man, it's ruthless out there, Lack. And I think it's funny
tough room, man. Tough
say,
room.
Yeah, exactly. It's also very funny that you say that it takes you away from doing the stuff that Google pays you to do. So I can understand. Now, keeping with the book theme, what is that bird on the front cover?
This bird is called a sunbittern. It's kind of like a wild turkey from South America. And those, it has this, it's like a peacock. When it spreads its feathers, you basically get these huge eyes. So it makes the bird look like it is much larger than it is. So when it sees this predator, it basically spreads its wings, and then you get those red spots. They look like huge eyes. You should go look at a photograph online, right? It's amazing. And it basically looks like it's a scary thing. And no, I did not get to choose the bird. I just love the bird. I had not heard about the bird before. O'Reilly assigned the bird to our cover, right? We authors don't get to choose the animals on our covers.
All right, so people are getting pissed at me that I'm not asking any machine learning related questions here. Here we go. What are the cons of putting feature engineering as a layer instead of doing it outside?
Yeah, absolutely. And this is something that we get into quite a bit in the book, but let me kind of summarize. Number one, training a model is an iterative process, which means that if you train the model for 100 epochs, there's 100 epochs times that you're basically doing this pre-processing over and over again. So the more expensive your pre-processing is, the more computationally expensive your training process becomes. And the way to address that, that's what TF transform does. TensorFlow transform basically figures out a way to do this only once rather than all the time, but still have the stuff be part of the model graph. The con is now your architecture is a lot more complex. You now have to have TensorFlow transform. You need to have a Apache Beam. You need to have these artifacts in your model pipeline, right? Your setup becomes more complex. The nice thing with the transform pattern is that it's simple. The trade-off is you're going to be doing these computations many, many times. Your computations are cheap. Your time is more valuable than the computer time. And I strongly recommend that you let the computer work a little bit harder so that you don't have to be up at night answering pagers.
Incredible. I love the way that you put things, man. All right, you got to come back on the MLOps community meetup, because having you on here just inspired me. There's so many questions. There are a bunch left in Slack. We have probably time for one or two more, maybe, depending on how short-winded or long-winded the answer is. So if you're building a batch system, is it still advised to host the model as a separate web service?
If you're building batch systems, that's a great question, right? And again, there's an entire pattern called batch serving that we get into many of the trade-offs here. So I'll kind of summarize a little bit here. In some cases, you want it to be a separate service. In some cases, it is a good idea to load it internally, but when you load it internally, you have to be very careful to basically take into account things like state management and things like distribution of model state. So it is not, so there are times in which you will want to keep it as an API, and times in which you want to keep it as a shared model handle, and times when you want to load it as not a shared model handle. So all of these possibilities, there are instances in which they're the right approach, right? So it's not like you do one always, but there are certain classes of problems for which you want an API, certain classes of problems for which you want to load the model into the pipeline, certain class of models where you want a shared handle in an Apache Beam pipeline, and we talk about those.
Nice. All right, last one, and then we really got to go. So, could you just? Oh no, wait. Sorry. Is there any study that shows that overfitting decreases or increases as we do continuous model evaluation?
Is there a study that talks about overfitting and continuous model evaluation? Well, whether you do continuous model evaluation or not, right, you do need to train on a representative sample of data. And all we are saying with continuous evaluation is that the world is dynamic and the representative sample of data will change over time. So I don't know. You are not training exclusively on new data. If that's what you got out of it, I'm sorry. That's not what I'm talking about. You're continuing to train on a representative sample of data, and you're hoping that if over time, if the probability distribution of your features change, that you're dropping the older bits and you're replacing the older data with the newer data. So think of it as training on a moving window of data. But that moving window of data is still a representative sample. It's very important that it is representative.
Excellent. For any more questions, go read the book. I got an affiliate link that I can make $5 off of. I'll share it with you. All right, Lack, man, this was awesome.
Absolutely, and yeah, all the royalties from the book go to Girls Who Code, by the way. So you're always nice. Also supporting a good cause.
Oh, you're making me feel bad with my affiliate link. All my affiliate link royalties go into my pocket.
No, that's fine. That's fine. Yeah.
I'm joking with you, but thank you, man. This was awesome as always. I really appreciate it.
You're welcome. I'm sorry, I cannot see Slack, the comments, but if any of you have questions or anything, I'm available on Twitter. Just feel free to tweet at me.
There we go.
Thank you.
Hit him up on Twitter. All right. Thanks, Lack. We'll see you later. Next up, we are going to be hearing from the folks at Intuit. We've got Ian and Simarpal. And you would think I knew how to pronounce that word or that name a little better because I've had him actually on a meetup of ours, but it's a bit of a tongue twister. So Ian is a product manager on the Intuit machine learning platform, and Simarpal is the product manager driving product strategy for feature engineering and storage at Intuit. Ian previously worked as a software engineer, both in the enterprise security space and consumer mobile app space. And Simarpal was previously at Ayasdi, a machine learning startup. And before that, he worked at Adobe as a product manager. Welcome to the both of you. And I think we're ready to get it rolling.
Hello, welcome everyone. Thank you for joining us today. My name is Simarpal. I'm a product manager at Intuit. I'm joined with my colleague Ian, who will introduce himself today. But today we are planning to share with you an overview of our machine learning platform and how it powers the real-time personalization of Intuit QuickBooks using clickstream data. Ian.
Hi, my name is Ian. I am excited to be here to share with you the Intuit ML platform and personalization. Thank you.
Okay. Thank you, Ian. So with that, as an agenda for today, I would briefly mention about Intuit and where machine learning is used in its product. Then at a high level, I will talk about the components of the platform. Uh, and after that, we'll go into details about the featureization and model inference pipeline. And we'll end up with a demo clip to show how the pipeline actually powers the in-product experience today. So at Intuit, we serve consumers through products such as TurboTax and Mint, and also small businesses and self-employed through our products such as QuickBooks. And in terms of where ML is used in product, a few examples mentioned are the search relevance for TurboTax, QuickBooks, and cash flow forecasting for QuickBooks, uh, and then providing proactive help within product and doing automatic transaction categorization, for example, in Mint. Now, if you read the mission statement of Intuit, then it says that the mission is to power prosperity around the world with AI-driven expert platform. Keeping that in mind, ML platform vision is to democratize AI ML development for anyone in Intuit by simplifying all the parts of the MDLC that you see over here through automation and self-serve user experience. Now, if we look at a high level, there are different types of technology used in each phase of model development within the platform today at Intuit. So on the feature engineering side, we provide Apache Beam, Spark, and Flink as a compute a framework running on Kubernetes infrastructure. And for feature storage, we use DynamoDB and S3. For model training and inference, we have AWS SageMaker. And for model monitoring and anomaly detection, we have in-house capabilities built. For the purpose of today's talk, we wanted to use case and walk you through the platform capabilities. At a high level, the user, whether they are using QuickBooks or a TurboTax, interacts with the product, and a series of events, which we call clickstream, is sent to the Kafka-based event bus, now which are then persisted also into the S3 data lake. Then these events are used to do real-time personalization, real-time featureization. For prediction, features are fetched from the feature store and combined with the request payload to deliver the customer experience within the product. And we also have the, as I said, model monitoring and the feedback loop to further improve on the product experience and model performance over time. So now next I will gonna go deeper into how the featureization pipeline is built. So as a platform, so for the purpose of this talk, as we said, we will be focusing on the real-time personalization pipeline. So as a platform, we provide choice to the data scientist and machine learning engineers to use different combination of distributed processing frameworks like Spark, Flink, and programming languages such as Python, Java, and Scala. So in this case, the clickstream pipeline to do featureization is built using PySpark framework running on Kubernetes-based infrastructure. The key components of the pipeline, starting from the left-hand side of what you see in the diagram over here. So we have a Kafka-based, real-time messaging system where all the clickstream events, what the user is interacting with the product, they come into it. And there are several thousand TPS of clickstream events that come in, and they are processed by highly scalable and distributed compute running on Kubernetes infrastructure. So in this case, the feature processor is written using PySpark. And for that, we also provide programming interface for developers to easily operate on data frame objects to apply their transformation and produce features. Once the features are produced, they are sent to another Kafka topic from where, what we call as the ingestion topic. And this acts as a shared message queue for both the stream writer that writes to what we call as the online store and a batch writer that writes to the offline store. And the reason for this is to ensure there is consistency in feature values that are used at the time of inference and training to avoid training serving skew. The data scientists use the feature values stored in the online store, which is backed by S3 and Hive table to do their model training. And at the time of inference, the feature values are fetched from the online store for in the real-time fashion to provide low latency response to the application. The low latency store that is built using DynamoDB, where is built using that, and where we had taken several design consideration to support different types of feature values and associated queries. For example, few feature values could be like a profile information about a user, but then there are also features, which are tracked on certain dimensions, say time, for which some aggregations are applied, and then those values are actually fed into the model. Some of the other design consideration we have to do is around the compliance needs, such as GDPR and CCPA, where these feature values could be deleted if a specific user makes a request to be forgotten and removed from our databases. The last piece of the component that you see over here is the data serving layer. So this is a GraphQL-based web service. Using this, the data scientists and engineers can fetch features as needed, and they can combine features across different feature set. In case of training, what this does is basically generate transpiled query that could be run on distributed compute to create training set that can then be fed into the model training process. And in case of real-time inference, it can directly return feature values from the store. In addition to what you see over here, we also provide users the backfill capability in order to backfill historical value of the feature. Backfill is another key capability and not an easy one, as we have to do some orchestration between the backfill job and automatically transition to process stream events which are coming live. To make it easier for our data scientists and machine learning engineers, we have provided this capability as part of the platform, out of the box. And if you look at this whole pipeline, the end-to-end latency is actually in a very low single-digit seconds, and which worked for this specific use case around real-time personalization that we spoke about. So next, I wanted to talk to you about the development experience, what the development experience is like for our data scientists and engineer. Uh, to build the feature engineering pieces, we provide self-serve experience on a developer portal where within few clicks the users are able to provision GitHub repository to write their processor code. Inside this repository, there are actually boilerplate code with simple examples for user to quickly get started and customize the code as per their needs. We also provide feature store SDK, using which the users can easily serialize the data and store those values in the feature store. In addition, we provide Jenkins build job to build the code and also a namespace on Kubernetes cluster where pipelines are run. Now, in order to make sure that the features get properly stored with proper metadata, because this helps with the feature discovery, we have a feature set registration process also, where we actually capture the descriptive information about the feature and also other information such as compliance related to CCPA and GDPR. And as I showed in the previous diagram, there is an ingestion topic that could be used in a self-serve manner to basically process the features into the online and offline store. And one last step is to create the schema for the GraphQL query for downstream consumption for model training and inference. And this is also provided as part of the onboarding process onto the feature management and the feature store. Another important aspect of these pipeline is to provide visibility to our user into the operational metrics and cost considerations. So we provide these out of the box Wavefront dashboard to track metrics around Kafka to see how many messages are getting processed and investigate if there are any consumer lags or not. So all these abilities are provided in a much more seamless manner. As soon as they onboard their use cases, they are able to view through these Wavefront dashboard. And the cost dashboard basically helps the users to look at the ROI of their investment as to how much are they spending in running these pipelines, to what value are these pipelines generating through customers in terms of providing benefit. And the last, importantly, like we provide the complete lineage tracking also for our users. Again, this happens through the metadata registry MDR component that I talked about earlier to see how the pipelines are built, what are the components across the board, connecting through different components as the pipeline goes from processing the data to storing the data and then making it available for downstream model consumption. Next, I would hand it over to Ian, who will walk you through the inference pipeline building experience and and how does the model consume these features for inference?
All right, thank you for that, Simar. So today I'll talk about the inference pipeline that relies on the feature store in order to get the features and personalize the models. So what is model inference? As part of model inference, it covers deploying and hosting of the model, getting the features from the feature store, giving them to the model and getting a prediction. And last but not least, monitoring the model to make sure that it's producing the right results from a model efficacy, and also operational monitoring to make sure that the model is up, it's giving the response time in the expected SLAs. That way the customer is getting really a personalized experience, and there is no lag between what the predictions are producing and what the customer is experiencing. So as part of the model deployment, what happens is there's an interface. It's self-serve for the users, in this case, the data scientists and machine learning engineers. Everything is in a central dashboard that can be accessed through our developer portal. There is container orchestration, which the platform handles. Everything is running in containers. We make sure that it's meeting SLAs, it meets the security standards. And of course, you have the dashboards for monitoring, and you also have a status to know is the model up or down. And I'll go into the dashboards at the end of this presentation when it comes to monitoring. So that is deploying and hosting. The next part is around feature fetching and orchestration. So for the feature fetching and orchestration, the way we've done this is that the data scientist is the author of a contract. We call this an escrow contract. The escrow contract specifies that these are the features I want to get. This is how I want to manipulate these features. And on top of that, it also specifies which model these features are supposed to go to. The contract is authored by the data scientist. It's abstracted away from where the data lives. So they just specify this is the data I need. We on the ML platform side will go ahead and connect to the feature store, get the data they need, send it to the model, and then send the predictions back. So we've abstracted this so that there is a simple interface between the data scientists and the client teams, and that simple interface is just a REST endpoint that the client teams call. Next, I'll go a little bit into the details of the feature fetching because this has a lot of patterns. And given that we are talking about real-time personalization, I'll talk a bit about what are the different patterns. So first of all, this is for the real-time inference, even though we can handle offline, but because of this talk, we are talking about the real-time aspects of it. It's based on a DAG, and I'll show you how that is materialized via the different nodes. And I'll go into details of the different feature fetching mechanisms and orchestration. We have model/data dependencies, parallel execution, data transformation, or what we call last mile transformation, and also asynchronous execution. All these are the different ways we can get features from the feature store and feed them to the model. So for the feature orchestration, I'll start with the model and data dependency. The way you read this is you read it from the bottom going up. The one at the top, model 2, that is what will finally be executed. So for the data, assume that all this data is coming from the feature store. So you can see that you can have the data come from the feature store, and then the different nodes can manipulate the data in order to get it into a certain format and then move this data to the upper nodes. In this case, you can see that model 1 gets the data from the feature store, which is data 4. It gets the output of that, and then that will feed into another model. So you can see model 2 depends on model 1. At the same time, it also gets the data from the feature store via feature 4, and all of these will feed into model 2. That is for model and data dependencies. The second one is parallel execution. And what this means is that if you see features 1 and features 4, these will be retrieved from the feature store at the same time, and then they'll feed back into the different aspects. In this case, feature 1 will be used by another processor to generate feature 2 and feature 3, whereas feature 4 will be used by model 1, and then model 2 will also use the same feature. But when we get the features from the feature store, we'll get features 1 and 4 at the same time. And we can get up to n features from the feature store at the same time. We have some models that actually rely on 300 features. And then the other part that I want to talk about is you can also get features after you've done the parallel fetch. You can also do some light aggregation, as Sima talked about, and then the aggregation of that data will be sent to the other upper nodes, in this case, model 2. Now, how does this affect the personalization? For example, if we take features 1, 2, and 3, it could be that the features that go into model 2, it's an average or a summation of these, and depending on the average, the experience will be different for the user. So the red arrow indicates a point within the node that is doing some feature processing. Now, all of this that I'm talking about happens on the model serving layer, and we on the ML platform, we handle that. Last but not least, I want to talk about the asynchronous nature. What this means is that you can have two models, even though there's an intermodal dependency, they can send their own predictions independently of another. What this means is that model 1, after it has done its processing, it can send its output to the calling service. At the same time, model 2, even though it's depending on model 1, it will independently send the output of the predictions to the upstream services. They do not have to wait for each other in order to materialize the final predictions to the upper layer. So all of these different patterns are handled by the ML platform, with the user just specifying that I want these features to be gotten from the feature store. Now, last but not least, I'll talk about the monitoring. In this case, you have the monitoring of the model predictions on the operational side. What this means is that, one, the user can specify, I need to get these requests per second, and I need to monitor them on a percentile basis, on a mean basis, so that if there's anything that goes wrong, they can take some action. And this is provided by the platform right out of the box. The user does not need to do anything. And one of the things that also we take care of is to make sure that we are monitoring the feature orchestration processing time, because of the online nature of these models, we need to make sure that the predictions or the feature fetch are produced in a timely manner. So we always monitor that. And if the orchestration is taking long, we can have an alerting and have users take a look. The other part, when it comes to the model monitoring, is monitoring the predictions themselves. This is the actual predictions that are coming out of the model. In this case, you're monitoring them on a statistical basis. The table on the left shows you some of the statistical metrics that we are looking at: mean, max. You can look at the number of null values. Anything that is anomalous is monitored, and the user can set the threshold of alerting so that downstream systems can do the featureization, to do retraining, or the users can take some other kind of action. The other part is we also have the ability for users to specify different kinds of monitoring depending on the model itself. For example, for binary classification, you can have confusion metrics, accuracy, precision, recall, all sorts of things. So this is also provided by the platform out of the box, with the user specifying the alert levels and the thresholds, and also which teams to contact. So what does this all mean? For the real-time personalization pipeline, We talked about the featureization, whereby you have your clickstream events, you're doing the online featureization on the streaming data, you're storing the features in an online store. On the inference side, the model is deployed, it's up and running. The ML platform is getting the features from the feature store. It's handling the orchestration of various features, combining them and doing monitoring. All this ends up providing a personalized experience for our users based on the data that is unique to them, while ensuring that we are, powering prosperity for our customers. And now I'll go ahead and show you how this looks like from a user perspective, and you'll see how this is actually realized for our users. So as this is loading up, I'll show you what this looks like. So in this case, give me a second. So what you're going to see here is a self-help customer. They are going to be within QuickBooks product. They want to log transactions because they want to keep track of the miles they've driven so that they can get reimbursed when it comes to tax time. So the user is going to go to the transaction tab, and they are going to choose to enter their transactions manually. And part of that, entering the transactions, they're going to log their miles. So you'll see them going to the miles tab on the left-hand side here. They'll log in, they'll put in the address of the starting point, and you'll see that it's not clear what exactly they need to do. And finally, they'll go to the tab here for an assistant, and you see that the data that is presented to them will be dependent on the data or on the previous actions that they have taken. So now you see the user, they are logging a transaction. They're adding the transaction within QuickBooks. They try to connect to their bank, but then they decide not to. They go to the Mile tab, and they're going to record a trip. So as they're recording, they're putting in the starting address. And now they don't know why they can't save, and they realize they have to put in the trip purpose. So now they want to add another transaction, and they're selecting what kind of category this transaction falls into, but they are not really sure. Is it insurance? Is it vehicle? They save that. Now you'll notice that here, once they've clicked the help tab, I'll take a pause here and I'll show you. You'll see that based on the transactions that they have, the help tab here, it's going to show them information based on the previous screens that they have seen. So in this case, there's a help tab for transactions. There's a help tab for trip. There's also another one for the categories that, because they're trying to categorize some transactions, and also they're showing for the business miles. Now I've gone to some websites and they have a self-help bot, and what it will do sometimes, it will just show you need help. But in this case, as you can see, that this help is really personalized for them in order to show them the relevant help topics. And of course, when the user takes action here, the information that is provided is really relevant to the transaction. And of course, you can see that these other subsequent help tabs, they're also dependent on the previous clickstream data or actions that the user has taken. And that marks the end of of the presentation. Thank you very much. Sima and I will be available via Slack to answer any questions that you might have, and we look forward to the discussion that this is going to elicit.
Yes, thank you very much, guys. It was great sharing our platform and information regarding our personalization pipeline. Feel free to reach out, as Ian said, on Slack.
Excellent. Thank you, fellas. That's very cool to see. I appreciate the transparency and how you show us all of the details on all of that. So, as always, ask them questions in Slack. I'm just here to add a few updates before we get cracking. We're going to be going at 10 past the hour. A few updates. If you haven't heard already, there is a meme competition going on. Give us your best meme, and we want to see that in the funny channel or on Twitter, hashtag applied meme, or show us a GIF and explain the MLOps tooling ecosystem in a GIF. I want to see some of that. It looks like it's shaping up to be pretty funny. So we've got those two things happening. Also, it is worth mentioning that Tecton is hiring. So in case anyone wants to work for them, reach out in Slack. They are hiring fast. Lots of good stuff, lots of good people working there. So last but not least, if you haven't filled out the poll, go ahead and fill that out. We have that in Slack too. The poll is going to be on a few random questions and then asking you if you have any stories about a model gone rogue. And we're giving out some swag to the best model gone rogue stories. And we're going to share all of those stories, all of those war stories, which we all love hearing. We're going to share those at the end of the day for anyone who would like to see it. And that's all, of course, happening, you know where, on Slack. That's right. Little quick plug for myself and the MLOps community. So we've got an incredible, it's actually a panel discussion next up. And after that, we'll start with the lightning talks. I'm going to be giving a lightning talk, if you can believe it or not. I'll be with my man, Ivan, aka Leonardo, and we're going to be talking about what the MLOps community is. So jump into that and you can hear all about what we're doing in the MLOps community and specifically around some of the initiatives and the engineering labs that we've got going on. We just kicked them off this week. And speaking of people that are helping out with the engineering labs, we have Simar Paul, who is giving a talk to people in the engineering labs, but we're going to talk all about that in my lightning talk. I'm getting slacked. Why am I talking about this? Forgive me, people. And also, okay, this is the last thing, and then I'll let the hold slide come up. I keep blabbing on. I'm going to be playing that guitar over there, right there, in the next break. So after this panel discussion, I'm going to be asking people in Slack to put some random things that we can sing about in Slack. All right. So in the Apply Conference channel, we can start a thread. I'll start it off right now and just throw some random stuff. Maybe it's about machine learning. Maybe it's not about it. It's about mustaches or whatever. And I'll make a song about it. I cannot promise the quality of that song, but I can promise that I will play that guitar and we will be singing Kumbaya in the next break after the panel. So it's a great way to transition out of the panel. So you never know what we could sing about, but you get to choose. So put whatever you want to sing about in Slack, training serving SKUs, feature freshness or data freshness, feature latency. I'm getting pinged right now. People are asking if I can just start singing the intros. That is, yeah, that's possible. I could do that for the lightning talks. All right. So Jupyter Notebooks, you want to hear a song about it, I will give it to you next talk. Now, I might as well just start introducing people because we're 7 minutes in and I think we can introduce them. I'll let them start filtering onto the stage as I am introducing them. And this is how you know that the Tecton folks had a lot of faith in me. They didn't let me organize and lead the panel. They said, we're going to get somebody that actually knows how to do this stuff. So they got the founder and editor-in-chief of the New Stack, Alex Williams, to come and put this panel on. If it was anybody else, I may have been a little bit angry, but considering the clout that Alex Williams has, just got to let him do it. And there he is. What's happening, Alex? It's good to have you here. And I think
thanks, man. I'm looking forward to hearing all these songs. I want to hear one about, ops is like kind of on my mind, that maybe that's a song. Ops is kind of on my mind.
Ooh, there we go. There's the title. That's easy enough. All right. So we got a few people here that are coming up. Do you want to intro them or you want me to?
Why don't you introduce everyone?
I'll sing the intro for them.
Nice.
No, that's next up. So
that's
stay
next
tuned.
up.
This is how we can keep the YouTube algorithm pinned on us. Engagement. We're keeping the eyeballs on. So we have, how many people are here now? There are 3 more people that are coming up. Next, we have Bar Moses, who you may or may not have seen yesterday in her lightning talk, talking about data downtime, data observability. We've got Kevin Stump, who you may or may not know, the co-founder and CTO of Tecton. Again, Tecton is hiring. They want to make it very clear that they are hiring, so reach out to them. And last but not least, we have Aparna, who is the co-founder and CPO at Arise. What's happening, Aparna? Welcome, everyone. And now is when I get to hand it off to you. Next time you see me, I'll have a guitar in hand. Take it away, Alex.
All right. Well, thanks, everyone, for being here for this session. I'm very excited about the discussion. One of the discussions that we are having more often is not just about DevOps, but how is DevOps evolving? And one of the foremost themes that we found in our research on cloud native DevOps is this idea of how these feedback loops are getting tighter and tighter. And we're starting to see more and more organizations use these micro feedback loops. I was reading a story on martinfowler.com about this and about great developer experiences versus not so great developer experiences. And so that brings us to this question about, what is MLOps for a DevOps team and how does it help improve that feedback loop that you're getting? And maybe Aparna, you can get started and help us kind of get your thoughts on this and perspectives.
Yeah, absolutely. Hey, everyone. So good to be here. I feel like I'm going to start this off a little controversial already, but I think MLOps is not the same as DevOps. They're, fundamentally, MLOps is a fundamentally different problem than DevOps. It's operationalizing models, which is different than operationalizing software or data pipelines. I think, sure, there's some overlap, but it would be wrong to see them as the same. And just a little bit of background on myself. So previously I was an ML engineer over at Uber. Little ex Uber mafia over here with Kevin on the panel as well. But at Uber, when we had this role of kind of an ML engineer, who is the person who really operationalized those models, put them into production, and they were fundamentally different than the people who actually did DevOps. And my opinion on this is that the person who should do DevOps for models is really, someone who's trained to understand that model, understand how it's built, and more importantly, know what the definition of good is for that model. Is a DevOps person going to know, is this model good or not good? Models are fundamentally, it's not 0 or 1. It's not, is the system broken? Is it working? They're statistical. So having someone who was involved in building that model be the person who runs operations for that is where I think we should go with MLOps. Would love to hear Kevin, your thoughts on this, Kevin and Bar.
Yeah, I'd love to add to that. So I definitely agree that DevOps and MLOps is not the same thing. In my mind, though, MLOps can learn a ton from DevOps, and it's the DevOps tooling, the DevOps platforms, and most importantly, the DevOps best practices that we need to bring over to MLOps. And maybe we can just recap those really quick. Like at the end of the day, the DevOps practices and tooling allows a software engineer to make a change to a line of code of a microservice that's currently running in production. I check this change into a Git branch. I get my pull request reviewed. And afterwards, once it's reviewed, there's automation happening behind the scenes, which is now going to build my container. It's going to test my container, and it's going to deploy my container to the production system. And I monitor in real time the health of the system. And what that allows folks to do is engineers are now really empowered. They own the system that's running in production. They're fully unblocked. There's automation in place that allows you to push a change to the production system within literally minutes. And with machine learning today, that's completely not the case. Like we all here know how long it takes to productionize machine learning. And we can take many, many pages out of the DevOps playbook to bring the exact same excellent experience and delightful experience that software developers have to data engineers and data scientists and ML engineers who are working together to productionize machine learning. And for me here, it's really about how do we make it as easy as possible if you change the script that's defining your training code, or if you change the code of your feature transformation, to then automatically train a model and deploy it into production after you've tested it and really safely roll it out to production so that you can squash this iteration loop and make it super quick for somebody to deploy an updated model, an updated feature to production.
Absolutely. I think what you hit on over there, which is like, what are the best practices that you can pull from the DevOps world into the MLOps world? I feel like there needs to be like a diagram that's like, okay, you check in your code in the DevOps world. Like, what does that mean? Is that registering your model in the machine learning world? You know, if you're running CI/CD checks in the software world, is that proper automated model validation? You know, like these one-to-one mappings between the DevOps world and the MLOps world. And I think that would make, you know, the things you might be doing might be different, but the fundamental kind of steps might be the same.
Yep.
Feel the need, you know, the urge to disagree with you all, but I'll just add to that. You know, I think you know, we've certainly seen sort of the DevOps practice emerge in the last sort of decade or so, or a couple of decades, and, you know, become prevalent. And I think we're seeing the same thing happen with MLOps now. To your sort of point around what are the best practices and methodology that we can adopt, if you think about sort of the core concept or what is DevOps or what's the goal of DevOps, right? It's to help build, you know, the best sort of software applications or best software services that you can. And adopting that mindset, bringing that to machine learning is exactly what I think MLOps is about. And that means, you know, delivering high quality products, those that are sort of secure and compliant and scalable, and allow us to have the fast feedback cycles and loops that we talked about. I think the main differences are, first and foremost, that there's very different stakeholders. So very different types of people with different backgrounds and different skill sets. And also obviously a very different stack, right? So different programming languages. And so there needs to be a significant adoption or significant thoughtfulness and intention when we're making that adoption. But there's certainly a lot that we can learn. And I think we'll also see the emergence of sort of new roles as a result. Interestingly, like DevOps has brought on the role of SREs, right? Site reliability engineers. And I'm really curious to see what are the new roles that MLOps will bring in the next couple of years as well.
Yeah, but you know, I feel like one trend that I've noticed, at least on LinkedIn and how people hire, is really ML engineers. I feel like there's a little bit of like championing for the person who actually, you know, takes that model and puts it in the real world. That's a hard job. You know, it's you know, it's almost like you got to know how the model's built, what it's trying to optimize for. And then you also got to know all of this software infrastructure to go make that successful in the real world. And I feel like when I remember when we were, you know, we had ML engineers at Uber, and, you know, that was kind of felt like a new role. It was like, you know, maybe one of the first couple of companies to actually do it. And now you go look on LinkedIn and like every fintech has ML engineers. Every company that's sort of building towards an ML platform has an ML engineer. And I think this role is actually going to get really big. And I'm excited for that. I'm excited to see kind of what this role's, this person, are they responsible? Where does that line, that handoff go? Are they the persons who are actually doing the automated validation? Are they monitoring it in production? Like, what is this person's role and definition as we kind of go into this next era?
And how does it change too? Because I think ML engineers are extremely important and necessary today to get ML into production, specifically because there's so much tooling and so much of the platforms are missing today. So they have to do a lot of hands-on manual work to implement your, say, feature pipelines that turn your raw data into feature values, or that hand implement a productionized version of your model training script so that you now have a production-ready ML model. And they're the ones who then build a microservice that actually hosts the ML model and then puts it in production. There's a lot of stuff that actually can, to a large extent, be automated. Of course, not everything, but a lot of stuff can be automated to make things faster, safer, more secure, etc.
Yep, and not to forget once the model's in production and then someone goes, hey, it doesn't look like it's working anymore, and then this person's got to go sift through Hive tables and figure out, why is my model not working? And that managing it once it's in, there's a journey of getting it into production, and then I would argue even a harder job of maintaining it in production. Because I think one of the differences, and maybe this is just my opinion, but I feel like code doesn't fundamentally degrade in production, right? There's bugs, but with models, there's kind of this concept of it degrades over time. And so you put something into production, the data, the world around you might change. And now, this person needs to make a decision of, when do I go update it? Is this still even relevant to the world that I live in today? And so that's one of, I feel like, a big difference between, I guess, the data ops, DevOps world and maybe the MLOps world is, it's really the data going into the model could be changing, which in then impacts the model's response to that data.
Yeah, I agree with that. I think that is a big difference. Maybe the closest analog I can see in typical DevOps and software engineering is that you look at some health metrics, like how is my memory consumption looking? Like, how high is the load on my microservices? Maybe things are still changing in the world because there's now more load on the system, so I need to increase my provisioning. But you're right, there's many more additional failure modes with models around, are my feature distributions drifting? Do I need to retrain my model, or is there an upstream data outage that I need to fix and I'll backfill in order to get my model back into the green zone again?
Yep.
I would like to challenge what you're saying about the degradation issue. Maybe the code doesn't necessarily degrade, but the processes do, don't they? Bar?
Yeah, I'd say, well, I think the process may degrade, and also the data itself, right? So to the point of the question, when does the ML engineer know whether to check whether the Hive tables, are up to date or not? Whether you're using the right tables, right? Whether you're relying on the right data set. So I think because the one constant thing in the data space is change, everyone's like adding more data sources. You mentioned fintech, and that's a great example of an industry where typical companies can rely on thousands of sources, oftentimes third-party data. And when you rely on that kind of data, changes are just part of your day-to-day. And in addition, you have sort of, many more people relying on this data. And with many more people relying on this data and using it, there could be changes all the time. And so, sort of assuming that the data that your machine learning model relies on is not a safe bet anymore. And because of that, you need to develop best practices and methodologies to make sure that you're doing what you can to deliver strong products. And that certainly can include sort of degradation and other sort of risks to your business, for sure. I don't think there's a single person, in data that has not encountered some horror stories. I heard there was a great panel about this yesterday. So I think, we all have those. And I think, solutions like Tecton and many others help us bring some best practices to making sure that we're staying on top of this as teams, as an industry.
One of the questions that I have then is about that data itself. And it's almost reminded me of, of reading I've done and, some writing on the topic where it sometimes feels like data is like treated like, it's almost like the procession in a royal court. I mean, there are so many different ways to respect the data and treat the data and how you present it. And there's just so many different aspects to it because the data is not like code. It's really just everywhere. And so how do you think about that whole data operation in itself and how that fits with, the concepts of MLOps and that issue about degradation with the models themselves over time?
Yeah. So in my mind, and this brings me to like a lot of people are often asking like, how do you even compare DevOps to data ops? And then how does it relate again to MLOps here? And the way I always think about that is that at the end of the day, like your DevOps system, your DevOps pipeline, it is concerned with one type of artifact, and that's the service, that's the microservice or the container that at the end of the day gets created and put into production. If you look at the data ops world, it's not that simple anymore. Now you're suddenly dealing with two different classes of artifacts. You've got on the one side, the data pipeline artifact, which turns inputs into outputs. And then you've got the second category, the second class, which are the data assets themselves that are produced and consumed too. And you need to monitor and version and make it easy to develop both of these artifacts. Like, how do I make it super easy to develop a new data pipeline? How do I make it super easy to monitor it? And how do I make it super easy to version and monitor even the data sets that are being generated by these pipelines? And then you bring, of course, MLOps into the whole story. Now it becomes even more complicated because now you're not just dealing with data pipelines and data assets, but now you're also dealing with model training code, and you're dealing with the model assets themselves that you need to generate, version, control, monitor, and everything else.
I guess one way I think about this is kind of, there's kind of different needs for observability for all of these different categories. There's kind of the, what Bar's team's done an incredible job on, which is kind of data observability, which is working on top of looking at the data lineage, what, data freshness, schema changes. And then there's kind of ML observability, which also has things like model lineage. So it's like, there's like these parallel concepts of like model lineage. There's, in the ML world, you might want to do, cross model, cross feature analysis, looking at training versus production for a feature. And so it almost feels like, the requirements for what you need to kind of safely automate away a lot of these processes is really good kind of observability, and the needs for them are different across DevOps, data ops, and ML ops.
Bar, so observability is back at center stage in some respects, isn't it?
Yeah, it's the new hot topic, observability for sure. And again, like all credit goes to DevOps, right? So we didn't make this up. And this is like tried, proven in DevOps, and we now need to implement this in new areas. I think that, there was, just for folks sort of not familiar, kind of with the concepts of observability, observability is basically sort of the ability to observe the health of a system based on its outputs. And so the idea is that, things can break in distributed environments, and obviously there's lots of change introduced in complex environments. And one way to measure the health of that system is by observing it. And so in DevOps, it's very well understood what you actually need to observe, right? And observability typically includes things like both monitoring, but also troubleshooting, tracing, et cetera. And so what do you actually monitor an instrument for is pretty clear in DevOps, right? There's things like performance and latency and CPU and, all these like best practices and best in class tools that we have for observability. And when it comes to data observability, to ML observability, those are all new territories for us. And so it's, up to us to define what is best in class observability, and also make it easier for all of us to be able to actually build data products with observability from day one. Oftentimes we see, folks who want to get started and all the sort of good stuff and exciting sort of advances, but end up sort of struggling with some of the fundamentals around like, where did this data even come from, and can I even use it? How old is this data? And so getting those best practices in place is, I think, something that's just fundamental for anyone kind of in ML, data engineering.
Curious how you think.
Go ahead. Go ahead.
I'll let you go.
Okay, I guess I'll go. I guess the one point, because Bar and I kind of both work in the observability space. I think one of the things our teams have actually talked about is, plug, we're kind of writing a new piece together, so I'm excited for that. It's kind of observability in the data space versus observability in the ML space. But one of the things that I think both of us kind of agree on is, what is the difference between monitoring and observability? And we kind of fundamentally see, observability is kind of really the whole health of the system, being able to not only pinpoint like red light, green light, something's gone down, but why? Like, why did it go down? And tell me how to go fix it. Like, that's the hard part. And there's some really good practices from DevOps that I think these new spaces are actually learning from and trying to pull from, so that we can try to create those flows that DevOps have to fixing and remediating the problem. And we can do that in the ML and data categories too.
One thing that I'd be curious to get your opinion on is, when I look at what do I wish the future looks like when it comes to data processing, model predictions, model developing, et cetera, is that at some point we're going to have a world where an organization can just look at one gigantic DAG in their organization that defines what are all my data inputs, what are all my feature transformations, what are all my otherwise data transformations, what are all my ML models, what are all the predictions they generate. And you've got this gigantic web basically that shows you exactly what's going on anywhere in the organization of any system that touches anything with data. And you just see red and green and yellow, and then you can zoom in and maybe retry some things, but you get the central aggregated view of what's going on with my data and ML health in the system. And I'm curious how you view that, and to what extent do you think observability is going to become consolidated or aggregated, where companies and the individual stakeholders are going to have a unified view somewhere where they do see everything around observability and what's going on, actually from software and DevOps to data ops to MLOps, and how you fast forward that and what your vision there is.
Yeah, I mean, if there's one thing that we can all agree on, is I just can't imagine a world where that isn't a part of the story, right? Like, and isn't like a huge part of the story. It's mind blowing to me that we don't even have that today, right? If you think about, any engineering organization, sort of working without DevOps or without observability, or kind of without this like holistic view, it kind of seems like a joke to us, right? Or sort of laughing. But for some reason, we've gotten away with like not doing that in data. Like, God help us, right? I don't actually know how we've been like survived to date. But when I think about, 5 to 10 years from now, it's clear to me that the future that you're describing is just inevitable, right? Especially since literally every company is becoming a data company. I know sounds like a cliche, and I think we've said it for decades, but I can think that we can more genuinely, the numbers and the data actually back us to say that today, that more and more more and more organizations are turning to data as a competitive advantage. And we see that with sort of, more and more folks in ML engineering roles, and, obviously sort of the market, the data market, how it's evolved in the last, honestly, 12 to 18 months has been sort of just, palpable speed. And so I just can't envision a world where this doesn't exist. Now, to the point of like, how do we get there? What does that look like? I think there's lots of challenges to figure out on that path, right? So I'll start even with sort of the easiest one. When you think about that sort of like centralized view, it looks very different in the world of like, an ML engineer, a data engineer, a data scientist, a data analyst, and a software engineer, right? They might have very different interactions with data. They might have very different interaction with that overall view. And so, I think some of the sort of burden of proof on us and some of the challenges that we face is, how do we make these interfaces something that people can interact with and use with? How do we make the communication between these groups work? Those are all challenges that we are not close to figuring it out. And I'm really excited to see what we come up with. But I feel very, very confident that that's where we're heading. And the faster we can figure it out, the better.
I think, Barry, that's exactly the point I was going to make, is that flow that Kevin described, there's different people across that flow. Like the person who actually looks at all of my tables is going to be different than the person who looks at all of my models. And then the individual person who might care about a specific model and how that specific model is performing. Like there might be different stakeholders across or engineers that are across that flow. I guess the way there's a lot of concepts, a lot of words. MLOps is growing at like this incredibly fast pace. I feel like the way that I kind of, segment the world, so I can at least try to box it. And like, these are the 3 core areas that I think we're going to see a lot of movement in, at least on the ML infrastructure side is, first, there's getting from all of your data down to I think what your team's doing over at Tecton, which is really the feature store, that central spot where all of the inputs for your models are coming from, is the central repository for how you handle different transformations. And then there's kind of the model store, which is the registry for models, tracks things like what's your latest version, which models are actually deployed in production. And then I think, Josh Tobin actually meant this word, but, I love this word. It's kind of the evaluation store, which is really down to capturing the individual predictions and managing things like the actual, drift, data quality, performance of each individual model. And so I think broadly segmenting into the feature store, the model store, the evaluation store kind of helps me at least kind of see that flow down of, what should each parts of those platform do. Feature store handles certain aspects, model store does different, evaluation store does different, and there's different users of all 3 of those platforms.
So when you think of all that, and then you think about differential management of the models themselves, and it goes back to that topic of decay, how are you seeing it visualized? How are you seeing that, those three boxes essentially kind of viewed and being able to represented so they could be standardized and used by, people to scale out their models themselves without them degrading?
For me, I can take this one. So there's kind of, that's a great question. And so I think that the interfaces between those 3 platforms that I described is something that I feel like the industry is still kind of getting the protocols on. How should the feature store integrate with the model store? Should the model store say, link back to the feature store and say these features are used in these models, and there's an overlap, if you have a model deployed in every single state or city, for instance, should there be some connection to the feature store and the model store that shows all of those groups of features that are used in the models? And then between the model store and the evaluation store, there's this exchange between what's my latest model? How do I store all of the different evaluation metrics across different versions, different environments? Like there's an interface that needs to be figured out between those 2. And then I feel like there's an interface between the evaluation store and the feature store, which is kind of as features start to degrade in production, or you start to notice data quality issues, do you do things like, pull the most latest refresh of, do you go trigger a retrain on your model? Do you go and decide to use your offline features? Do you decide to at least, call out that there's bugs in your feature transformation layer? Like there's these feedback loops and interfaces that need to occur between all 3 of these platforms for, I think, machine learning to really be this truly automated vision that Kevin was kind of highlighting, where click button, things deploy, things work great. When things have a problem, automatically go fix yourself, and then go fix yourself and kind of auto learn where you need to go improve. Like that's the vision that I have for the future. And these systems need to work together. And I think the defining the interfaces between the platforms is probably where I feel the biggest conversation is going to happen in the next year or so.
Yeah, I agree that it's super important to nail those interfaces so that the different systems really neatly integrate with each other, because at the end of the day, this would then also allow companies to purchase best-in-class tools for the different components of this workflow. And then they know, given that they're all hopefully implementing very similar identical interfaces, that you can package it all up together. And now you've got one nicely integrated platform. And then ideally there's this additional interface to the end user who then doesn't even have to necessarily know anymore, hey, there's like 5 different systems, 5 different platforms under the hood, because it's so neatly integrated with each other, where it just feels like an end-to-end platform that solves my entire problem end-to-end, even though under the hood, it's different best-in-class tools and platforms that the company was able to purchase and then stitch together.
So there, oh, go ahead.
Go ahead. I just wanted to mention one, a paper, recent work that Andrew Ng released a few months ago that I thought was really interesting in terms of some research that he did around, when there's a problem with a model, there's, to Aparna's point, there's a lot of different things that could go wrong, and where do you actually sort of start and how do you troubleshoot? And in some ideal world, there's also some, self troubleshooting and, self-healing way to do that. Until we get there, where do you actually start? And some of his results actually speak to whether, the issue is in the model itself or in the data itself, and sort of advocates for thinking about being data-centric and model-centric. And I think that's, pretty controversial, definitely not something that's sort of well accepted in the industry today. And I just thought that it was a really interesting take, and perhaps, one of the very first discussions on this in a data-driven way. So actually being able to prove, how does a model improve based on the data-centric versus the model-centric way is quite interesting. So I thought that was, a new take on this problem.
Yeah, no, I think that that's a really good point, because so much, it's like garbage in, garbage out. So much of this depends on, are you getting good data to even go into your models? And maybe I'd even add one more, which is like just tying back into the DevOps world. Some parts of it could be just, service health, kind of like there's like the model, which is core algorithm, and then data-centric metrics, which is kind of the data, data quality issues, drift, you could even say is perhaps, could come back to a data quality issue. And then there's really kind of service health metrics. What if the microservice that was serving your model goes down? Like that's another, or doesn't scale up. Like that's might be even a whole nother category of failure modes for a model.
We have one question we should ask it just before we finish up. Should there not be a way for new improved model to supersede the older model in identical interfaces? Who'd like to take a crack at that? Bar?
I'll let Aparna, did you want to go? Go ahead.
Oh no, I feel like my answer is obvious. Yes. Like I think that in an ideal world where these systems are automated, if you have a better version of your model, or we used to have some of these systems in some of the older teams that I worked on. It's kind of like a rollback. You could roll back to older versions of your models that you knew performed well if your performance got to a certain, started to degrade. But if you do, have a new version of the model and you're trying to, you've properly A/B tested it, that this one's better, and you run it on Shadow, when it starts to perform better than your existing model, it should supersede and start to take over. I guess, there's a lot of steps, I guess, in getting to that journey, starting from, what Bar was heading out, which is you need to have really good data observability to even know that the data is in a good spot. You need to have really good feature transformations. It kind of, you want that whole system lined up in place. And of course, observability in the ML context to be able to automatically, trigger actions if you know what it's going to do. But it's a journey and we're going to get there. But I'm excited for kind of the all of these systems to kind of work together and get to a spot where we can automate these.
Yeah, I think that's right. And I think that's sort of one sort of tactic and kind of a toolbox that teams need to have in order to kind of, have these best practices in place. And for each team and organization, there might be different tactics that you deploy earlier versus later. It's helpful to think a little bit about like where you are in sort of maturity curve in terms of ML and production and what's your path to getting there. Tools is certainly one part of the solution, but it's probably not the only one. Like thinking about, who are the different people involved, how the organization work together, getting support for that and maybe most importantly, like making sure that there's value to the work that you're doing, that people are actually benefiting from it. So whether it's sort of internal consumers or external customers, making sure that you're making a real impact with your work is probably sort of the best way, I think, for us to get a hold on all of these.
Kevin, why don't you take it out? I think we're coming up to our end of our time. I believe that we're coming pretty close. So Kevin, why don't you help us finish this up?
Sure. I mean, I'd love to just go back to this question really quick that was posed, and I'd say like in DevOps, you've got canary deployments, which we can learn from, which is a page out of the playbook we can definitely bring over here, where you put something, you develop a new service, you put it partially into production, you throw some shadow traffic at it, you monitor the health of it, and then you roll it out or you roll it back. That's the exact same thing that we need with models, where you have a new challenger model, you put it out there, you put some shadow traffic against it, maybe even some real traffic against it, you see how the model performs, and then you execute the full rollout or you roll it back. And so that's exactly the type of tooling that we need in order to make it easier for folks to develop new models, better models, try out things without having to be scared about putting potentially a worse version of a model out into production.
Well, excellent. I want to thank everyone for their time. I know, Bar, are you speaking later today as well on data observability?
Actually spoke about it yesterday, so you can watch the recording.
Okay.
It was right after the meditation, which was a great session too.
Oh, really? Gosh, well, I missed that, unfortunately. Awesome. Well, thank you, everyone. This has been really, I guess, illuminating for me. I'm learning a lot about how MLOps really does, play a role for this new generation of ML engineers and people in this space. So thank you all for your time.
Absolutely. Thanks for being a great host.
Thank you
so much, Alex, Kevin, Bar.
Great stuff. Appreciate that, everyone. So, as we mentioned, we're going to be having some music session. I know there's some cool conversations happening in the Apply Conference Slack channel, but if you want some songs about your training servants queue, tell me what I should sing about right now. I'm going to share my music, or should I say computer sound, so that everyone can hear my guitar. Let me see if I figured this out yet, and you all can tell me if it sounds really weird or not. There might be.
We actually can't hear you, Dee.
You can't hear me?
No, we can.
Now you can, but you couldn't before. Uh-oh. Let me see if I can figure this out. We've got a few minutes. So now you get to put what you want me to sing about on the Slack. And while I'm figuring this out, yeah, I should just strum it really loud. I had it all hooked up and was ready. It's all cool. Like it's and now it's not working. I can't believe it. We may have to postpone this one while I get it working, and we do it for the next break. Oh man, I was so excited too. I was so ready for this. Well, I give you all a lot more time to put what you want us to sing about. Can you hear the guitar if I do this? Can you hear that?
Yes, we can hear.
You hear that? Oh, well, maybe we just do that. All right. I'm seeing absolutely nothing in Slack about what I should be singing about. I'm gonna have to start it off with you hear that guitar, right? Or is it just coming through in the from my mic?
Yep, we can hear you.
All right. So I guess that's a success. There's first step is looking good. Now, what should I sing about? Train and serve and skew? Who's looking after the features? Uh-oh, I got one coming through, broken data pipelines. Inspired by the last talk. Broken data pipelines, don't fail me now. I've been up all night trying to figure out what the hell you're broken for. I need some observability in my pipeline today. There's just too many gigabytes coming through these broken data pipelines. And I see some random people jumping on screen and they're like, what? Michelle, hello? Probably wondering, what is going on?
I'm loving this.
So what should we sing about? More. Oh, data, data everywhere. Where's it coming from? Data, data everywhere. If I knew where this data was coming from, I could go to sleep. Put that data in a feature store. I gotta serve it up so fresh. We're living in the clouds. Hold on. This needs a little more groove. Oh, I read that wrong. Acid databases, acid compliant, accidental drop on the database. Ooh, yeah. Oh, oh. Give me my features in a feature store. I'm looking for, oh, 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 oh. No more bias. I want slices. I want fair and accurate transparency. Oh, clean those data sets. Clean those data sets. Clean those data sets. Clean those data sets. And we're out of time. You guys are awesome. All right, this could go on all day. So, wading into the lake before the Texas flood. We've got 2 new speakers coming on right now, Michelle and Matthew. Excited to hear all about Notable. In case you didn't know, they are one of the partners, and they're happily giving away a little swag for us. All right, Michelle and Matthew, I am going to just let you take it away because I went a little bit over and now we're in lightning talk. So every minute is worth it. I will let you go for it. And then, yeah, I'll see you in 10 minutes.
That's a hard act to follow, though.
Thanks. Awesome. Let me get the share screen going. How's that looking? All right. I think I accidentally muted Michelle as well.
Nope, I'm here.
Great. Perfect. Hi. Thanks for joining. We're going to talk about productionizing data and ML projects. I'm here with Michelle, and my name is Matthew Seal. I'm the CTO and co-founder here at Notable. And my background overlaps with Michelle back at Netflix, where we both worked on the big data team, working on different data problems, and overlapped a lot on the intersection where notebooks helped advance that. And on that note, I'm deeply involved in the Jupyter community space. I'm a distributed contributor there, and I've been working in the open source as much as I can.
Hey everyone, my name is Michelle Ufford and I'm the CEO and co-founder of Notable. My background is all things data. I've been working with data for the last 20 plus years. And right before launching this startup, I was at Netflix where I led the big data tools team, which was really focused on innovations to improve the usability of the overall Netflix data platform. So like I said, I've been doing this for a little while, and I thought it might be helpful just to take a quick look at how data lifecycles have looked traditionally. So I'm assuming that you've all seen something that looks very similar to this. It's largely unchanged for the last decade plus. And it doesn't really matter what your role is or what your specific data project is. Most data projects will follow a very similar path, which is that you start off with your data discovery, trying to understand what data is available and what does it mean. And then you get to your data prep phase. And this is the point at which you do any sort of integrations, denormalizations, transformations, all of that work takes place here. And you often spend a lot of time in this phase. Then once you have your data available, you're ready to go on to your model definition phase. So you get to your model planning, you iterate back and forth between the data and the design until you're happy with what you have. And now you're ready to get to the building phase. And so the building phase is where you do the core of your development. Now, this is a very generalized view. Obviously, if we're talking about machine learning, you need to have training in there. And when you're talking about machine learning, you've got this highly iterative loop that actually goes from the definition phase to the building phase to that model training phase, rinse and repeat as many times as you need to. But we're going to go back to that other view just because it's a little bit simpler for us to work from. And so once you're done with your development phase, now you're ready to communicate those results out. So you've done your analysis, you think things look good. You're going to probably put together maybe a memo or a Tableau report, and you really want to communicate out to your business partners and stakeholders what you've created and get the go ahead to deploy this to production. And so once you do get that go ahead, now you're ready to operationalize. And this is the point in the process where you will do all of the transformations you need to get this really ready for production. So when you're doing development, oftentimes you're doing an ad hoc or a one-off type of development process. Now you need to make this entire thing repeatable. You also might have to change the language from maybe like a SQL or an R to something like a Python or a Scala. So all of that takes place there. And then now you're ready to deploy this to production. And so once we're ready to get to production, we need to both ensure that what gets deployed is what we think is deployed, and we need to make sure that it continues to stay good. So we're going to put any sort of quality checks in place, canary test, all of that's going to take place as part of this productionalization. So this works pretty well. We've been doing this for a while now, but what happens when there's a problem, right? It gets pretty painful pretty quickly. Because now you're dealing with, let's say that you did have to do some sort of language transformation. Now you're dealing with multiple artifacts, with multiple people. You've got your model owner who is writing the code in R or Python. You've got to involve your data engineer who is probably working in Scala or Python. If you have a DevOps person, you might need to involve them too because they're helping with the deployment. And so this is a really slow and tedious and painful process. And it can take hours just to figure out what's going on, what went wrong, let alone not even get a chance to fix it. So if you're feeling this pain, rest assured you are not alone. We've all been feeling this pain. And so we've started to see this life cycle evolve. All right, Matt, you want to take it from here?
Yeah, thanks. So largely, the data lifecycle as you see it really hasn't changed in shape in terms of what your process is that you need to go through, walking from discovery through operationalization. What's really actually changed is the fact that the friction points of moving from each of these steps has become a bottleneck to be able to do more work in data space. In today's world, you might have more bubbles here. These bubbles might be expanded. You might add stages to this process. But at the end of the day, you're still doing a development feedback loop cycle that you go through. And what we found was that the place where you really helped solve the friction points that were coming from the traditional cycle was around finding a unifying tool or interface that really brings what's in production to be closer to what you do in dev. So the further your development process is from what actually is going to run in production, the harder it is to respond to issues, come back to problems after they've sat outside of your development cycle for a while, and the harder it is to start the next project. You really run into all sorts of friction points around the time to resolve and iterate being a function of each of these stages having different tool chains, even different languages or different systems under the hood. So we go back to that problem Michelle described. You have a problem in production. Well, if you have a unifying tool, you can actually take what was in production, feed in the original inputs that actually caused that problem, and then have an end resolution where you can, in development, reproduce the problem right away, identify where the actual issue is, and then get the right people focused on fixing it. And if you do this well, you can even have people who weren't involved in the original development know how to fix it because you have a similar interface, a similar tool chain, and everything looks the same. So take, for example, what we did at Netflix, which we use notebooks for this use case a lot. You take that problem statement you have, and this is a Jupyter notebook. And if you have that kind of production flow run as a notebook, when it fails, you can actually see the notebook with the given inputs, with the given logs, the given visualizations, all there, and it's reproducible. So I can right away take the outcome result that failed or had a problem, rerun that locally or rerun a subset of the data locally against that, and identify exactly what I need to do. Also, if the problem is somewhere else along your development lifecycle chain, even all the way to communicating results, it's really easy to share the same document, the same interface to solve for the same problems. And we found this greatly reduced the friction on having smaller teams able to support more data pipelines. You could have one person who supported many more pipelines, so when something went wrong, other people could lean in and help, and also that one person could be more effective. So I talked about different unifying tools. Notebooks is the one that we've used a lot, but there are other ones out there too, especially in the ML space. You have something like Metaflow, which is an open source library out of Netflix, or MLflow, or some of the others. A lot of them all have the flow phrase in them because they're really talking about how you need to flow from each stage of your production cycle and bring the tool along as you go. And what this really does is it flips the focus of what you need to work on to productionize your work. Before, you would always productionize the last stage because that was the closest to production. But now in your development is close to production pattern, you can actually focus on standard software development best practices that will improve both the dev and production's life cycles. So you can do things like unit testing, code cleanup, documentation, those types of things now benefit both halves of that equation if you have a tool in the interface that keeps those two locations similar. Stepping to that notebook example where we really had a lot of success in bringing that together for all data users was, I wanted to talk some about the tools that are available in that space. What does productionization with a notebook look like? Well, beyond the standard kind of code cleanup and documentation paths you would do with code that you can do with the notebook, there's also some newer things like Testbook, which I'll talk about in a minute, as well as lots and lots of options for documentation and other testing and parameterization controls. Papermill was something we worked on at Netflix in the open source, and that had a lot of success for helping with the integration parameterization aspect of it. But there's lots of other tools here that you can use to kind of promote a notebook beyond the development cycle. I wanted to talk briefly about Testbook. This is a project that I worked on with Rohit and a Google Summer of Code last year. And this came out really great. It's a tool that allows you to write unit tests against IPMYB notebook files, just like they were .py files. So you can see from the document page snapshot here that you can write a simple test against a notebook and actually unit test the contents within a notebook rather than the full notebook end to end. And this unlocks some of the use cases where you have more complicated notebooks and you need to figure out how to split them up or test them better. And that's a really handy library if you haven't seen it.
So that's our talk. Thanks everybody for watching. I know it was a lot of content really quick. Myself and members of the Notable team are going to be on the conference Slack and on Twitter if you have any questions about any of this or anything that we can do to help.
And if you want to find out more about how we're using notebooks to help with data and ML workflows, sign up for our beta. That's going to be launching soon, and we'll talk to you afterwards.
Thanks, everyone.
Awesome. Thank you so much. Appreciate that, Michelle and Matthew. And I appreciate you being good sports about me introing you with a song. Now, guess who gets to have their 15 minutes of fame? That is right. Yours truly. I get to talk. That is what I get to do for the next 10 minutes. I've got my man Ilnardo, aka Ivan, who is jumping on stage with me, and he's going to be here. We're going to talk about the MLOps community. A lot of people have been wondering what exactly it is and what we're doing with the MLOps community. So feel free to ask us any questions right now. We wanted to do it a little bit different, where it's just going to be Yvonne and I asking each other questions, and then you all can see what our goals are for the community. And if anyone wants to get involved and they're not involved yet, you can jump in Slack. We've also got all kinds of good stuff that we're going to talk about right now. So Ilnardo, paging Ilnardo to the stage. I think you got to turn on your video, Yvonne.
Yep.
There he is.
There we go.
There he is. What's happening, man? It's good to have you.
I'm fine. And you? I see you're having fun. I see you having fun. So
I am. I totally am. So let's start it off. You want to ask me questions first, or you want me to start?
No. I can start actually. So let me say, I would like to know more about the what is MLOps community. So what is the goal? So if you could spend some words about the community itself and the initiative that we are going to plan.
So great question. I like where your head's at. I'll try and answer that to the best of my ability. The MLOps community is a place where all of this stuff that we've been talking about over the last 2 days, we are talking about it every day, 24/7. And we have all kinds of different initiatives that I'll get into in a minute. But the main place where people can come and they can ask questions is in our Slack. Then we've also got meetups every week. And this is really like, what I feel like is that there's a lot of emphasis right now in machine learning that's being put on the model building. And we've all seen that famous Google photo that shows how important model building is, and then how there's all those other pieces of the puzzle that go with it. And that's really what we're trying to do, is really demystify the space, because I think there's a lot of hype around MLOps right now. And so helping people navigate this space, and it's not just me, luckily, because if it was just me, I don't think there would be that much value besides like a few little guitar playing. But we've got smart people like you, Yvonne, that are in it, and you're able to share your wisdom. You're somebody that, you have a long history of working with MLOps, and then there's thousands of other people like you that are in there, and they're very, very kind with their time and their knowledge. So yeah, that's it.
So it sounds to me that you are working on something that allow people to access a kind of knowledge hub on MLOps, because as you mentioned, there are a lot of information up there. Maybe it could be tricky to navigate about this topic. Have you planned it?
Yeah, that's definitely what we're trying to do. Knowledge hub, and just help people like have a place to land and have a place to go more in depth, from like the beginner to the most advanced. I will say that it's a community, and these things take work. So we are trying to work on that. We're trying to create places that people can come and learn about their specific problems, but also learn about the general trends in this space. So you want me to ask you one now?
Yeah, sure. Go ahead.
All right, cool. So, well, maybe I should explain, before I even ask you one, I should talk about these different initiatives that we have and what we're doing in the community. And then I'll ask you about the engineering labs, which is a specific initiative. The initiatives that we have right now, like I mentioned, we have like Slack, which is probably very, very popular among all the community members. We've also got the meetups, which are happening every week on Wednesday. And we get people that you've seen on here, like a lot of people that I've been talking to and that we've had come on to this conference. They've come on to the MLOps community meetup and they've talked to us, which is incredible to have like legends like Lack or Todd who have been on the meetup, or we also have a podcast. And so we've got the podcast. We'll put all the links to all of this into Slack in a minute, into the Apply Slack. And then we've got reading groups. So there's some really cool people. What I think is really cool is that people started just suggesting, hey, I want to do this with the community. Hey, I want to do that. And then it just snowballed and it took a little bit of like, it has a mind of its own now. And you were one of those people that suggested you wanted to do the engineering labs. So we'll get to the engineering labs in a minute, but right now we've got reading groups. We've got like Women of MLOps, which Aparna is kind of leading on that, who was just on here. And then we've got open office hours. We've also got the engineering labs. So let's talk about the engineering labs. What exactly, Ilnardo, are the engineering labs?
Yeah, I'll try to explain in few words. So essentially, Engineering Labs is a community project where each people has the opportunity to join a team and work together on solving a particular machine learning engineering challenge. So actually, I started this initiative because when I joined the MLOps community, as you remember, I was thinking about how I can contribute in MLOps community, just you mentioned so far. So I asked myself, what another way to support people? So if, for example, if a new person joined the community, how can I turn all this knowledge that we start to share in the community in something that can help the people itself to solve most common MLOps challenges and in a concrete way. And so I find this answer in the Engineering Lab initiative.
Yeah, I love that the engineering labs are a way for people to get hands-on experience with stuff that they're not necessarily working on at work, or if they are just coming out of school, right? They get a chance to practice with teams that are based all over the world. But don't let me steal your thunder. I'm going to ask you more questions. There's just so much stuff I love about what you are doing with the engineering labs. I think it's awesome, and I really appreciate that you're doing it. So we've done 2 engineering labs so far, right? The first one,
correct.
And now we're on the second one. Can you explain the 2 of them and what each of them are?
Yeah, sure. So let me say, the first one, the first engineering lab was a kind of a starting point. So we just let me say, ask people to build machine learning pipeline using just 2 tools, MLflow and PyTorch serve, because actually this topic came out during several conversations that we have in the community. People just ask, okay, I know that MLflow and PyTorch now can let me say, they can create this end-to-end. So I would like to know more how to deploy a PyTorch model using MLflow framework. And so that's how the first engineering labs starts. But then when we end the first engineering lab, we work hard to collect feedback from the people that join the first lab. And so we learn a lot from this feedback. And this is a point that I would like to highlight, because it's a kind of learning process. And so based on their feedback, we structured the new engineering labs in 6 steps. So maybe I can explain a word, because essentially now it's really simple to join the initiative. We provide a subscription form that we use to collect information about the people that want to join, their background, and everything is useful for us to create teams. And then we let the community vote ML engineering content to, let's say, to use in the lab. And so once we know the results of the vote, we have this process of onboarding calls with teams, where we share the content, the goal of the lab, we provide metrics and the scope of the lab. And also, because it's important to mention the prize that the team that is going to win the contest will receive. And so then you have 6 weeks to solve the ML challenge that we propose you in the lab, and building your own engineering lab solution. As I mentioned at the end, you're going to have a context, and the team that wins get the opportunity to present in one of the MLOps conference that, thanks for the MLOps community, we are able to join. So, for example, in this, the engineering lab we have in now, the team that is going to win is going to be on the stage of MLOps World Conference. So that's something that, it's amazing, because you work to have fun, you collaborate on a really interesting topics, and then at the end you get this great opportunity to present what you are going to do.
Yep, and I think that's all the time we got, because I blabbed on a little bit too much at the beginning, but I will mention too, we also took feedback from people from the first labs, and we have like experts that are coming in and they're giving talks. So some of the people that you've seen in this conference are going to be giving talks to the teams to help them. How do they structure? How do they create data products? How are they looking at like the different, this actually just randomly, this one that we're doing right now is all about feature stores. So we're going to have people come in and talk about feature stores. Now that's it. Ivan, I got to kick you off, man, because we just went over time, but thank you for coming on here and explaining about the engineering labs. If anyone wants to get involved in the engineering labs, I encourage you to do so. Like, just reach out to Ivan or I. In his name on Slack is Ilnardo, and we'll give you all the information. So that's that. Now, up next, we've got Atlassian, right? Is it true? Do we have Jeff? Yes. You guys are up early, huh?
Yeah, it's pretty early here. Just like last time we chatted.
I know, man. So Jeff has been on the MLOps podcast, and that's how we know each other. I'm going to just let you guys go because I went over. So sorry for going over, but these two coming at you from Atlassian, they're going to give us a lightning talk. Let's hear it.
Okay. All right. So hi, I'm Joshua Hansen, tech lead on Atlassian's ML platform team. And with me is Jeff Sims, principal data scientist at Atlassian. Now, for the past few years, we've been working on building out Atlassian's machine learning capabilities and shipping smarter experiences for users of our products. Today, we're going to be talking about a problem that I'm sure many people have encountered, which is that machine learning is expensive. There are all kinds of costs associated with training and deploying a machine learning model. And with so many different interacting systems involved, it can often be difficult to make intelligent decisions on how to design your ML solutions in a cost-effective manner. In this talk, we'll go through a real machine learning use case that we dealt with at Atlassian, where our costs were getting out of hand. Using this as an example, we'll discuss how to quantify the underlying costs of calculating and serving machine learning features, and some techniques for choosing the most cost-effective features for a model. Now, first of all, I'll introduce the use case, which we call Smart Mentions. In this use case, we have a user picker that lists recommended users whom you might want to mention in a particular context, such as a Jira issue or a Confluence page. If we select a certain user, they'll receive a notification to draw their attention to the comment. Now, this is driven by a fairly simple logistic regression model that predicts the likelihood you'll want to mention any given user at request time based on a number of signals expressed as machine learning features. A backend service then re-ranks the users in the list as appropriate. For this use case, it's important that the features that are used to make these predictions are very up to date. For example, it may be that the right person to recommend is someone who mentioned you 5 minutes ago, and so the model needs that information reflected in its features as soon as possible. As such, we're calculating the features constantly via streaming using Tecton as our feature store. Tecton writes these features out to an AWS DynamoDB store where they can be fetched at request time at low latency. Now, with thousands of user interactions resulting in features being updated every second, a real-time system like this comes at a price. There came a point where this model was costing more to run than we were happy with, and so we started considering ways to reduce the cost without compromising the user experience. Now, to change something, you first need to be able to measure it. So the first step was to properly quantify exactly how much each feature was costing us to run. Since we have streaming feature updates, the primary driver of our costs is writes to DynamoDB. DynamoDB offers two different pricing modes, and Tecton uses the on-demand pricing mode, which means you effectively pay a fixed price for each individual write. There is some nuance to this depending on the size of your writes or factors like replication to other regions, but this gives us a straightforward means of calculating our feature cost. Now, this table shows some examples of features we performed this analysis on. Using an SQL query against our data source, we're able to easily do a count of how many event updates there are for each feature over any given time period, which roughly corresponds to Dynamo writes. By looking at historical cost data provided by AWS, you can also see the average write cost per day. You can see from the table that the number of writes varies a lot from feature to feature, and the update count corresponds with the write cost. Calculating this out gives us a fairly consistent price of $12.48 per million writes, which is about what we'd expect given we replicate these features across 6 regions. This ultimately gives us the equation: cost of features equals update count times a fraction of a cent being the cost per write. The advantage of having this equation is that we can use it as a heuristic to estimate the cost of any potential feature, even before we define it in Tecton. Of course, there are other costs associated with using the feature, such as compute or storage, but we know from going through this exercise that in our use case at least, write costs are so dominant that they can be more or less ignored. So at this point, we understand what our features cost, and we have a few obvious courses of action to try to reduce those costs. We could try to reduce the feature cost by reducing the cost per update. And this might mean changing the way we serve the feature, or if you've built your own custom serving solution, you could optimize the way it works. In our case, we had limited control over the way features were served, so this wasn't really an option. And in general, these kinds of optimizations often involve making some difficult trade-offs that might compromise some aspect of the user experience, such as latency or reliability. Alternatively, we know that the number of updates is the main driver of costs, so we could simply reduce the number of updates, perhaps by having these features update less often. This would be easy to do and would lower the cost, but it's likely going to have a negative impact on the feature's usefulness and ultimately the model's accuracy. Instead, the approach we actually took was to consider which features are providing the most value and figure out which were the most cost efficient. And I'll now hand it over to Jeff to describe this in more detail.
Thanks, Josh. So if we begin by making a basic assumption that each feature has equal cost, then the first obvious adjustment we can make is to limit the number of features used in any given model. We typically start with one feature and incrementally add more. And we monitor the accuracy as we do so. So from this perspective, it's easy to see when adding more features is giving diminishing returns in terms of accuracy, and we're able to make a very simple trade-off between cost and accuracy. In this case, we can see the accuracy stops improving after around 7 features. So by using 7 rather than 10, for example, we're effectively running at 70% cost. But of course, as we've seen from Josh, some features can be much more expensive than others. So a more cunning but equally simple method we use to observe accuracy charts for different sets of features. So usually with and without the most expensive ones. In a similar vein, we're able to quantify the difference in accuracy and make a judgment call. So in this example, there's about a 4% accuracy drop using the cheaper set of features. Now, when you start having multiple models in production, you're able to be even more strategic about which features you use in a model. In this case, we're deploying a new model into production and we're able to reuse some existing features. These are the ones highlighted here in yellow. So in this case, by forcefully reusing features we knew already existed, it effectively saved us around $15,000 a year. Now, equivalently, because these features are used twice, to a first approximation, we could say that their effective cost is halved. Of course, the more times a feature is called upon, which depends on the use case, the better value you're actually getting from it. In other words, a feature which serves 1,000 users is much less cost effective than one which serves millions of users, but still cost the same. Now, in general, we typically approach this by looking at both dimensions in parallel. We observe how the accuracy changes as both features are added and as expensive features are removed. So if we look at the chart on the right, the red outlined area shows a clear step change in weekly cost from around $20 per week to $80 per week. And we can see that the corresponding accuracy changes on the left-hand chart, in this case, are minimal, which demonstrates an easy feature space that we should stick to. This can have a huge impact. Adopting these simple methods here has helped us save around $400,000 per year across just 2 models. Now, this is all made possible by both the empirical verification of cost estimates, which Josh showed earlier, as well as the detailed logging and diagnostics provided by the Tekton platform. We're happy to chat more on this topic in Slack, so please reach out if you have any questions. Thank you.
Excellent, guys. I appreciate that. Now, we've got next up, my man. Is it, am I correct in saying this name? Nayur Khan? Nayur to the stage. We're going to be talking about some reusability and machine learning. Did I totally butcher your name?
No, I think you did fantastic. I was waiting for it, but it was good. It was good.
Right. Excellent. Well, I'm just going to let you get cracking. It looks like you already are sharing your screen. So go for it, man. Thank you.
Thank you. All right. As I've just been introduced, and thank you for getting my name right as well. Reusability and machine learning. Is a short talk. So we're going to try and cover 2 things. We're going to set a bit of context around some of the challenges with machine learning. And everyone here probably in this conference has probably heard so many different things. I don't think we'll spend a lot of time on that. And then the second, we'll actually dive into an approach to reusability. Before we do that, let me just do a brief introduction of myself. Who am I? Nayur Khan. I work for a company called Quantum Black, which is part of McKinsey. For those that don't know, Quantum Black is the center of excellence for artificial intelligence within McKinsey. It came out of Formula One, which is why there's a picture of a Formula One car. I have a software engineering background, 20 odd years in the industry, working in various different verticals and organizations. I've run large-scale engineering teams, and now I help my clients scale AI. And what do I mean by scaling AI? I mean moving my clients from single-digit kind of pilots and into production to tens or hundreds of models running in production. And I'm fortunate to be able to do that in various different industries with clients all over the world. You could also find me on LinkedIn. Okay, so with that intro out the way, let's do a brief recap with some of the challenges of machine learning. Usually we find 2 different things. One, messy data, and it's interesting on this one. We won't have time to go into this, and I would love to have done a deep dive talk on this in itself. There's a lot of comments on Slack around this. Messy data causes a lot of problems, and there's ways of actually handling that. We're actually going to focus on the code aspect. And when I talk code, lots and lots of code in notebooks, code in monolithic code bases, in hacky kind of scripts, all over the place. This kind of leads to general problems that we see with a lot of our practitioners. Data scientists have to learn lots of different tools, especially to get something to be high quality code that actually makes it into production and is maintainable. Everyone works in a different way. No matter who you speak to, they have got their own ways of working. It works on my machine is always the excuse we've always heard. Code doesn't run on another person's machine. Different levels of exposure to software engineering concepts. And general, the general trend, it takes a very long time to actually build something reliable that actually goes into production without having to rewrite it again and again and again. And I think some of the earlier talks talked about ways of handling the process. But we also find this scenario where we have several different teams within organizations sitting side by side, sometimes in the same offices or sometimes geographically dispersed. Combinations of data engineering and data science, along with some kind of product manager, writing lots of different these types of monolithic type code bases, notebooks, etc., etc. Now that leads to the general premise that there are lots of problems that come out of that. One, a huge amount of lack of reuse, which is going to be our focus, but lack of collaboration even within the same team, or sharing of knowledge or sharing of libraries. The second around duplication, like reinventing the wheel. I've seen this in teams that sit side by side, not just in different locations, but literally solving the same problem again and again. However, solving the same problem again and again, but doing it in an inconsistent way. And we talked earlier briefly about the messy data, which causes different problems. What is the source of data? What is the source of truth? Using different algorithms, leading to lack of trust in the eventual AI models that make it into production. That causes huge amounts of maintenance problems, especially if you have a kind of a very small team that are building these models, but then trying to hand it over to some kind of support team to kind of maintain and nurse it in production. And the final point, which is one that's close to my heart, but is the huge amount of tech debt that's left behind, with huge swathes of monolithic code. No one understands what's going on, how to reproduce these pipelines or these models, and how to maintain it. Okay, so with all of that context set, I'm going to now whiz a little bit through the reusability aspect. Like, is there a really simple way of looking at what this code is doing? And here I'm trying to illustrate, look, it connects to some data. It does some cleaning, joining, transforming, aggregating of that data. It's building features, it's building models and training models, and then there's some kind of visualization at the end. The overarching question I'm asking is, could we somehow package this up for some reuse? And I think we can. So let me just introduce you briefly to something called Kedro. So Kedro is an open source framework that we built at Quantum Black. Initially, we had this problems ourselves. We wanted, we noticed within our own teams, different teams were actually developing in different ways, and that was causing us problems in terms of maintainability. So we built Kedro to solve that problem. But then we realized it has a benefit for our clients, but also for the wider good. So hence why we built this framework for data scientists, for data engineers, for machine learning engineers, and we made it open source. And really trying to set a foundation of creating repeatable data science code and providing an easy way to transition from development to production without having to rewrite your code. And just borrowing and applying software engineering concepts to do this, but applying that to data science. Why I think we've covered this, but really there are lots of shortcomings of doing things with Jupyter. I've seen on the Slack channel, I've seen in various different threads and conversations, we're not trying to put notebooks into production. And the same thing, it's not really a good idea to do one-off scripts or monolithic type code bases. It becomes really difficult over time to actually get this right. Our focus is on creating maintainable data science code, applying those software engineering concepts such as modularity, separation of concerns, testability, and really driving into like reusable analytic code. There's also another benefit too, which I really want to touch on, which is around enhancing team collaboration. And this is not just within members within the same team, but also between different teams within the same organization, really trying to address some of the problems we talked about earlier. So briefly, where does Kedro sit in the ecosystem? So if I start on the extreme right, it does not try and solve deployment or pipelines or models or orchestration of that. There are other frameworks out there which are fantastic and good to look at. What it does do is the initial parts, especially if we're talking that code base around ingesting of data, cleaning, joining, wrangling type data, building engineering features, and training and validating and building models. So back to what we started earlier. We said there was here are some of what those code bases are doing. They try to connect to data, they try to clean, transform, they try to build features, and they try to build models. Could we use Kedro? And there's a really nice feature within Kedro around something called reusable pipelines. Think of it such as Lego blocks. Is there a way to actually use Kedro and use these Lego blocks and have them used by different teams? Different teams, so team one might be looking at some kind of sales data, cleaning, transforming, building features, and then eventually building a model. Team two might say, look, I want to use some of those building blocks off the shelf, these Lego blocks, but maybe I want to use some marketing data. Maybe I want to join those two together and do something different, but then use the other standard stuff, including the models itself. Really trying to address the lack of reuse we talked about earlier, the duplication, this inconsistency, make maintenance far more easier and reduce tech debt. Now, this is a really short talk, and we're not going to get time to drive into each one of these concepts, but I'll touch a little bit on some of the software engineering concepts of using Kedro and designing, well-maintained Kedro pipelines. And here is where I go back to some of the software engineering principles. And there are lots and lots of material on this. I wish we could have done a longer talk on this, but I'll rattle through this and I'll put some links up on the Slack channel afterwards. So the one, don't repeat yourself, is just a general thing. Tremendous amounts of copy pasta code I've seen over my years. Of just remove. Don't do that. It causes lots of problems, especially around maintenance and tech debt. The second is around solid principles. If you've not come across this, Robert C. Martin has a fantastic book on this. But really, single responsibility is a fantastic principle. Each class, each function has a single responsibility and only one reason to change. The open-close principle, Liskov, interface segregation, and dependency inversion. And then the final, which I really love, is Yagni. It sounds like a great idea. You write some code and you put it in the code base, but you're never going to use it. It's just an idea. And what you've just added is huge amount of technical debt and confusion down the road for maintenance. So given that you have all these Lego blocks and now you focused on building very reusable type pipelines, is there a way to actually discover this? And this is really where you're going to have to pay a little bit of attention to, like, how do my teams discover what Lego blocks exist, like these reusable pipelines? So one, I would recommend looking at some kind of knowledge repo or wiki. We internally at Quantum Black, we have our own product called Bricks that we use internally, and we've got 4,000 of our own practitioners that use that. Airbnb has one, an open source one, which is also fantastic, called Knowledge Repo, surprisingly enough. I would check that out. The other thing, also sharing source code via Git and via some kind of snippets and put it into Git. And then finally, sharing the components via some kind of artifactory or repository internally, so you could do a simple pip install. So just going to quickly recap this and end this. I think we're going to hit our time soon. What did we cover? We covered the challenge of machine learning. So briefly, we talked about lack of reuse, duplication, inconsistency, maintenance, and tech debt. And then we talked about an approach to reusability. I introduced Kedro, which is an open source framework that we at Quantum Black use, and a lot of our clients and out there use that too. Kedro has a fantastic part of it called reusable pipeline, which allows you to kind of break up these different concerns within inside the code base and treat them as Lego blocks, and really, really focus on having a way of actually just assembling pipelines together and models. Focus on good software engineering practices and principles to actually build those pipelines. And I mentioned Dry, Solid, Yagni. There are many, many others. I do encourage looking at that. And then fourth, have a sense of kind of discoverability, have some kind of tool in place so you could actually discover what Lego blocks have been built already inside your organization that you can leverage. I'll put the links in the Slack channel for Kedro. There's also a demo. I'll put the link in the Slack channel, which just shows the nice visualizations that Kedro can do in terms of these complex pipelines. And finally, before handing it over back to Demetrius, I'll ask just a general question. What is the end goal here? And again, on the Slack channel, there's lots of activity talking about this. Is it to build a one-off on the left-hand side type of insight, type of model? You've handcrafted it. You've spent a lot of time on it, and it serves a purpose. It kind of works. Or does your organization that you work in want to really scale this out and really try to industrialize this whole process and try and really, really build reusable pipelines? I go back to the clients I work with. They really are trying to not just do one model. They've gone past the experimentation stage. They really, really want to do multiple tens, hundreds, maybe even thousands of models in production. And that really, really, really needs to a good software engineering practices and processes really need to be put in place. And with that, I will hand back to Demetrius.
Awesome,
thank you,
man. Super interesting. And I know you didn't have enough time to go through Kedro here, but maybe I can convince you to come on to the MLOps meetup and talk about it more in depth.
I would be happy to, dude. I would be happy to.
Excellent. Well, we'll talk offline. That sounds very cool. Now, next up, we've got my man, Carl. We are coming at you, and Carl is one of those people that is, it's apparent as soon as you talk to him, he is super smart. We have had him on the MLOps community podcast, and it was just he was the first person to open my mind to so many different themes. Now, so you know who he is. He's a senior staff software engineer at LinkedIn, and he's going to be introducing Dali, a unified database abstraction layer for offline and nearline systems that enables data engineers to benefit from processes and infrastructure already used by LinkedIn's software engineers. All right, Carl, paging you to the stage. Come on up. I think the only thing is I can't see or hear you. I think you're on mute and your video is off. Yeah, you got to go back. I see your screen though. I definitely see all that good stuff. So now we gotta. There he is.
Hey, here I am. Okay, sorry about that.
That happens.
That's embarrassing. Okay, so let's see if you can see my slides now.
Oh yeah, looks good. I'll let you take it from here, man.
Okay,
Good to see
cool.
you again.
So that was a really nice introduction, but also it sets high expectations. So I hope I can deliver on that. As Demetrius said, my name is Carl Steinbach. Quick correction, I actually left LinkedIn at the beginning of March, and I'm working on something new now, which hopefully I'll be able to share with everyone in a couple of weeks. But I'm here today to talk about work that I did at LinkedIn and work that still very much influences the way that I view the data ecosystem and the future really of this platform. So the title of the talk is Exploiting the Data Code Duality with Dali, and Dali is the name of the project. I wanted to start by talking about a paper that I read a couple of years ago, and this was during a period where I thought it would be interesting to track down the origins of all of these laws that we know about. Moore's law, Conway's law, there's a long list. And part of the reason I wanted to do this was a belief that my understanding of what these laws are meant to convey might actually be quite different from what the original author's intent was. And that turned out to be, I think, the case in terms of Conway's law. So Conway's law, is written up here. So organizations which design systems are constrained to produce systems which are copies of the communication structures of these organizations. So Conway's basically postulating that in a large design organization where you have many different teams that are collaborating to try to build a giant system, it's natural for there then to be created basically an isomorphic relationship between the components of the system and the components of the organization. And I first heard this law, I think, when I was in college, and it seemed like a pretty depressing observation to me. I thought, this is just saying that design basically is heavily influenced by the broken organization of large companies. At least that's how I interpreted it at the time. When I went back to read the original paper, though, I found out that it wasn't meant as a cynical observation. Rather, it was meant as an observation, as a statement of facts. And then based on this fact, how can we actually improve the situation? So the title of the paper is kind of funny. How do committees invent? And these days, design by committee, of course, is sort of a pejorative, right? We typically don't think that committees are capable of designing something. They lack sort of like an ethereal voice, if you will. But in this paper, Conway begins by sort of talking about how the software industry is changing. And in fact, he mentions that the software industry is this new thing. He describes how for the first time we're seeing computer companies, in other words, hardware companies, there are actually companies coming out of them which specialize just in software, and that's a big difference. And the sorts of systems that he talks about designing, like missile defense and other things, very much products of their time. So I think one reason I would recommend reading this paper is just because it gives a very interesting historical perspective on what the computer industry was like in the late 1960s. But back to Conway's law itself. So we have this observation, right? And the rest of the paper really is about what can we do based on this fact. So Conway draws a couple of corollaries. So one is that in light of this fact, a design effort should be organized according to the need for communication. So Conway sees this issue where if you have 100 people who are collaborating on the design of a complex system, you can't have each person talk with the other 99 people, because very quickly you'll just bog down in communication. And we see actually the same thing in distributed systems, right? It's important to route information in an efficient manner in order to prevent saturating your network fabric, and for that matter also bogging down your nodes with just needless communication traffic. So the second corollary is that because the design which occurs first is almost never the best possible, the prevailing system concept may need to change. Therefore, flexibility of organization is important to effective design. So Conway's saying that at the beginning of the design process, we don't know what the eventual system is going to look like, and that we just need to accept the fact that any organization that we start with will need to change over time. So you may also interpret this as kind of depressing, because it's almost like he's postulating that a healthy organization is one that's constantly reorganizing itself. And certainly like corporate reorganizations get a pretty bad rap for many legitimate reasons. But I think in this case, he's really advocating more that the things that people work on be somewhat more fluid than they are, and that ownership be spread across the organization. So at the end of the paper, Conway makes an important prediction, and that's really sort of the theme of this talk. So his prediction is that it becomes necessary to restrict communication so that people can get work done. And research which leads to techniques permitting more efficient communication among designers will play an extremely important role in the technology of system management. So I want you to stop for a second and think about some of the tools that software engineers use today that were not available in the late 1960s. Things that we really take for granted. Things like version control, things like code review, be it Review Board or Fabricator or GitHub, and other tools like that. And that Jira, for example, also, or bug tracking systems. And when you get down to it, like each of these tools is really a mechanism for communication. So version control in many ways is a mechanism for communicating with the past. You're able to see the history of how something evolved. You're able to look at commit messages and understand why a change was made. And with Jira, you're also able to understand how different pieces of the project connect together. Timelines, you're able to ask questions of other developers, leave comments. And all of these things, right, are able to streamline communication. Like in particular, things like Git, using Git blame, or Jira using search functionality, you're able to quickly find basically the person that you need to talk to. And that's huge. Without these tools, right, in a 1960s era organization, you would really have to talk to a bunch of people maybe before you would be able to find the engineer who's working on that specific piece of code that you're looking for. So I want everyone to just sort of think about how, in my opinion, Conway's predictions really are quite accurate. And I think it's important to appreciate that. So let's take it as a fact that a lot of tools have improved the communication between engineers for the task of developing software, and that this has allowed us to build ever larger systems and to get around the problem that Conway formulated in Conway's law. The unfortunate thing is, though, that these same practices have lagged in terms of being adopted for data engineering. And in data engineering, we see many of the same problems. At LinkedIn, we see a problem over and over again where the people who are producing data sets, the people who work on online teams, they are generating events based on user interactions with the system. And for them, in many ways, it's like they're putting a message in the bottle and throwing it in the sea. They have no idea who's going to pick it up. They have no idea what is built on top of it, the offline data processes that depend on different aspects of that message. And when they make changes, it often has very disruptive effects on people on the other side of the company. So, this picture then really is meant to illustrate the fact that there's this haze, right, a mist that exists between producers and consumers. And there's no easy way for a data consumer to communicate with the person who's producing a data set they depend on. And similarly, the reverse is true. Producers really have no idea who's depending on their data sets. And even if they did, I'd argue that it is still very disruptive for a data producer to make a change, in particular to a schema. There are many types of changes, in fact, that are prohibitively expensive to make, such as removing a field, right? Until you can get everyone migrated off of that field and over to a new field, it's really impossible to do. And as a result, at LinkedIn, we have many tracking data sets that have lots of vestigial tails, columns and fields, which everyone knows they shouldn't use. There was one incident where we had 2 columns in a data set that represented time, one in milliseconds and one in seconds. Someone got confused about which column was the right one to use, and it caused metrics to go, haywire for a week. So that was a very, simple problem, but it simple cause of a big problem. And it's that sort of thing that we would really like to try to avoid. So going back to software, let's take a look at how change of interfaces in particular, the change of contracts between the implementer of functionality and the consumers of functionality is handled. So another sort of interesting thing to note is that Conway's law and Conway's paper are frequently brought up by people who are talking about microservices, because they say, microservices are a great example of how we get around Conway's law by breaking everything down into small pieces, and that makes things much more dynamic and easy to change. So in a service, of course, a microservice, it's easy to introduce a new API because you can support both the old API and the new API on top of the same service at the same time. Unlike data sets, right? In a data set, unless you're willing to maintain 2 different copies of the data set, you have this point where you at some point need to flip over and begin publishing the new version. And that's like an atomic force push upgrade, right? If people aren't ready for that upgrade, it's going to break everyone at the same time. And that's really why these backward compatible changes in practice just don't happen, because people know that the cost is way too high. But like I said, for services, there is a way of making these changes, even backward compatible changes. You simply introduce the new version of the API. You watch as people migrate during a window of time from the old API to the new API, and then you gradually turn off the old API. So we would really like to have this same functionality, this same ability for data sets. And that's what Dali provides in the form of views. So many of you probably are familiar with SQL views. A view is basically a query that looks like a table. So when you query the view, if it's a virtual view, the database goes and basically rewrites the view query on top of your query and executes the whole thing. If it's a materialized view, you can basically tell the database that you want it to materialize that view. The database goes and runs the query and then saves the results. So in Dali, the views are virtual. And that means that, in effect, the people who own data sets are able, using the view, to manage or to decouple the implementation of their data set, which is basically the data on disk in distributed storage, from the interface of the data that they expose to clients. So they are able to also support multiple interfaces, APIs, on top of that data set at the same time. And this gives data set owners and data producers the same power and flexibility to manage the API of their data set that people who build microservices today have. So how did we do this? We basically did it by originally embedding a database engine inside of the reader layer of Spark and Hive and Pig and Presto. More recently, we've actually started doing this through code translation. So we're able to translate from different flavors of SQL into an intermediate relational representation, and then from there to the target language using calcite. We've also introduced a tool or a framework called Transport, which allows users to write transportable UDFs, which covers the other sort of half of this equation. So sort of digging down a little bit more into the abstraction that Dali Views provides. A table, of course, is an abstraction that wraps over physical information like the path on distributed storage of a data set, the format, schema, partitioning team indexes. The view really is a function expressed in SQL, described in terms of other tables and views. And a Dali view in this case is a view plus a table plus UDF dependencies. So we give you the ability to manage a view like you would any other software artifact. You check it into Git, you declare dependencies that the view has on UDF artifacts, basically jar files and specific versions, and you're able to version the view as well. So sort of in recap, what are views good for? So at a high level, they're good for giving data producers the ability to manage the contract that they expose to data consumers. But if we dig down a level, they're also good for a variety of other sort of like concrete use cases. Going through the list, so one is flattening highly nested data without storing two copies. At LinkedIn, there is a profile data set for member information. It has 8 levels of nesting, and in SQL and Pig, it's really inconvenient to deal with that many levels of nesting. So it's convenient to store a flattened copy of that. We're able to do this, basically offer a nested and a flattened version without actually making 2 copies. And that ensures also that the flattened version never falls out of sync with the nested version. Another useful thing is to be able to demultiplex a generic table into 2 specific tables. So this is a case where, in effect, we've unioned 2 different event types together. And rather than having people in their business logic always filter on the event that they're looking for, it's a lot easier if that filtering is already sort of encoded in a view. And the reverse is also true. So we've seen cases where people create these synthetic union views on top of a bunch of different specific page view types. I also mentioned managing backward incompatible changes without materializing 2 copies. So it gives consumers the ability to remove fields without disrupting downstream users. We've also used it to bridge the gap over different storage formats. And code reuse is a major thing also that I wanted to talk about. So in the past, there were many cases where we might see something that people were doing in a bunch of different queries or Spark jobs. They were basically writing the same logic. And the solution at the time was to say, well, let's write a UDF, and everyone should use this UDF instead of writing their own code. The problem, though, then became actually versioning and managing that UDF and making sure that everyone was using the same copy. We would often see cases where people were using old copies of the UDF, or another issue was that we'd have to write different UDFs for the different compute platforms that we were using. By pushing that logic that everyone needs into a view, we're able to make it accessible and reusable by everyone. We're also able to hide the complexity of the implementation, and we're able to version it and make sure that everyone is on the same version at the same time. So code reuse, just like we see in software, is a huge use case and motivation for views. And really, the larger theme here is taking all of the nice tools that we have for software engineering and applying them really to the problem of data engineering. Eventually, what we want to do with this is really take advantage of the notion of, instead of thinking about a graph of workflows, we'd like to think more about a graph of views. And if we have the ability to introspect into what those views are, it opens the possibility of really modeling your graph of views as one giant common table expression and asking your SQL query optimizer to go and figure out the different opportunities for scan sharing, predicate pushdown, and things like that. So just to summarize quickly, why Dali gives our users the ability to move seamlessly between physical and virtual data sets. That has had a huge impact on productivity. Code reuse is another major issue. So we've been able to eliminate a lot of boilerplate logic that users were managing in thousands of different pieces of business logic. And dependency management has been huge. So it allows data producers to understand which downstream pieces of logic depend on the schema of their data set, and to do impact analysis. And also in the rare cases where something does break, it allows data consumers to easily trace back upstream and figure out what changed most recently, and then use that to narrow down the cause of their problem. So Dali is also format and storage agnostic, which these days I think people are increasingly taking for granted, which is a really good thing. But in 2009, when I joined LinkedIn in 2012. In 2012, when I joined LinkedIn, things were still, not storage and format agnostic, and this was a big problem. And then finally, it decouples data producers from data consumers, and this is really I think the main point of Conway's law, right? Like, given the fact that people are connected, how can we decouple changes as much as possible? And in cases where they are coupled, streamline the communication between individuals who need to know about each other. So that's the end of my talk. There's actually a longer version of this talk that you can find on YouTube if you're curious for more information. And anyone who wants to follow up with me, I'd be happy to answer questions either over LinkedIn or on Twitter. Thank you very much.
Amazing. Carl, you do not let us down at all, man. I think you exceeded my expectations. That was excellent. And what a reference. I'm wondering how many papers you went through and you went and reread to see what they actually were talking about.
Well, I don't know. I think it's pretty fun. Especially, I don't know, there's old papers, especially old CS papers, get to the point fast. The information content is way higher, right, than it is today, where a lot of CS papers, it's like one paragraph really is the original part, and the rest is just boilerplate. So yeah, I highly recommend reading old papers. There's a lot of bang for the buck there.
Incredible, man. Thanks for coming on here, and thanks for talking to us about this. And if anyone wants to reach out, yeah, hit him up on Twitter or LinkedIn. That's awesome. So now we've got a few minutes that we are going to do a little swag giveaway. You guessed it, because I haven't been giving away any swag today, really. And people are starting to ask, they're starting to get mad at me in Slack, and they're saying, we got all this swag, we need to give it away. What can we do? How can we do it? So we've got a trivia game. I'm going to ask 2 trivia questions right now, and whoever can get the answers to these questions, they're not easily Googleable, and so you win some swag. All right. First one is, what was the first company to use the term MLOps? Go ahead and throw it in Slack. It is in the Apply Conference channel. What was the first company to use the term MLOps? Everybody's saying Google. I do not think it was. I do not think it was. Gartner, Netflix. I don't think so. Uber, no. Microsoft, Spotify, no. All right, you guys are just saying all the no. This is just ridiculous. No, I don't think anybody knows this one. It is, I believe, and this is my Quantum Black. Now you're just being shameless. So this is, yes, it was a weird company, David. The company, at least in my research, was called Parallel M. Parallel M. Oh, David almost got it. Oh, so close. Yes, Parallel M. And they were the first ones to coin that term. So now the next question is, and some people may know this because we talked about it in the MLOps community, who has the copyright for the term MLOps? Who's got that? Who owns the term? Google. No. Oh, David, man, this is blast from the past. It was not Google. No. CDF. No. Who was it? Netflix. No. I won't give you any clues. Eldo, come on, what is that? Tecton, no. Algorithmia, no. What Parallel M? No, because Parallel M got bought by someone and they ended up using that. And Kubeflow, no. Nobody's got this, huh? These are some, I didn't realize these were so tricky. All right, so Parallel M got bought by somebody. Yes, there it is. Data Robot. Cheater. I'm glad you pointed out that you were cheating, though. Data Robot owns that term. And someone put into the MLOps community Slack one time that, so Parallel M got bought by Data Robot, David. That's what I'm trying to say, is they got bought. And so now Data Robot owns it. Now, yeah, Richard Stallman was the most entertaining answer. Exactly. Now, let's keep it moving because I was expecting to have given away some swag by now, but apparently nobody got it yet. All right. How many people did we say registered for this conference? How many people are registered for Apply? Yeah, oh my God. Yes. No, over 7K. All right, Michael, there it is. Boom. Michael wins some swag. It's over. Stefan, you're just putting random numbers in there. All right. It's over 7K. We got a winner right there. Michael, reach out to me. Bravo. Over 7,001. Nice try. All right. So we got one swag giveaway. Next up, here I see David Aponte is still in here. So you better get this swag bag, because when was the first MLOps community meetup? When was the first MLOps community meetup held? Yeah, but what month? What month? Not the year. Yes, a little over a year ago. What month? Give me a month. And the year. Month plus year, and you win some swag. March 2020. There it is. Daniel wins some swag. David, dude, what's going on? Manish, 2021. Wow, you all are almost there. You're close. All right. So no, Daniel's a winner there. All right, next one. I got so much swag that I'm trying to give away. You're making it really hard for me, everyone. Please make my job easier. How many partners are here at Apply? How many partners are here at Apply? Actually, I have no idea to the answer. Somebody else has to come in and count the answer to this one. Oh no. So yeah, we'll figure out that answer. We'll figure that one out later. I'm not going to give away any swag for that because I don't know the answer to it. Somebody has to give me a little help on that. Actually go and count them from the website. Next up, oh my God, I realized that these all sounded good when I was making them up in my head, and now they don't sound that good anymore because I can't remember the answer and I don't know. All right, looks like we got we got our swag that we're giving away, and we're over on time. So I'm going to ask the next speaker to come to the stage. We've got David, who's been participating in the Slack, who is one of the co-creators of Kubeflow. Let me just give him a little intro. He's a partner and program manager at Microsoft Azure. He'll now discuss the self-assembling machine learning environment project, aka SAME. It's a Kubernetes and Kubeflow project and community to create tooling that allows for quick ramp up, seamless collaboration, and efficient scaling. All right, David, I'm going to pass it over to you. Nice try on the swag. If the talk's good enough, maybe we'll give you some swag for that. All right, here we go. Take it away.
Hi, I'm Dave Ronchek, and I'm extremely pleased to present the SAME project, a cloud-native approach to reproducible machine learning. The SAME project came about because we took a look at the machine learning industry and realized that there was this huge gap between the magical AI goodness we promised everyone and where most folks are. What we really need to do is figure out how to bring those two together and make it easy to reproduce and deploy machine learning to any environment. The way we solved this when it came to containers and Kubernetes was through the advent of something called cloud native apps, where you had a way to describe a complex application in a really simple and straightforward way. And so I think what we need to do is establish the concept of cloud native ML. Now for me, this represents basically down to three key components. One, is your platform composable, so your data scientists can pick and choose whatever makes sense to them? Two, is it portable? Can it move from place to place and respond to configurations that each environment provides? And three, is it scalable? Can you scale processors, disk, resources necessary? Can you scale the number of experiments you run simultaneously or with other folks? And can you scale the number of teams and people actually collaborate? Now, Kubernetes is great at this for composability, portability, and scalability, but unfortunately, way too many of the abstractions end up leaking through, making it very complicated for data scientists to adopt something like cloud native ML. So what we should do is introduce cloud native ML for everyone. And that's the core of the SAME project, which stands for Self-Assembling Machine Learning Environments. The L is silent. With SAME, you start with a Kubernetes as your base layer, and then you declare on top of that your SAME manifest. And you can use that same manifest over and over again in your different environments, deploying just what you need to each environment and picking up any configuration settings by these different environments as necessary. This makes deployment and reproduction of machine learning pipelines much easier. So how might it work? And I do say might because we are very early in this overall process. By downloading a single binary and using that same manifest, you should be able to start from anywhere, your local laptop, a VM, or a cluster in the cloud, and deploy everything necessary, including services, pipeline, UI, and associated resources necessary to execute and reproduce that pipeline. But that's enough hand-waving. Let's get to a sample demo. First thing we're going to do is clone the existing repo with that information and the code inside it. After that, we will install Kubeflow using a single command, same init. After a few minutes, that installation is complete, running against our local machine, and we simply execute it using same program run. At this point, it deploys the pipeline and execute it according to the parameters in that file and anything we add to the command line. Just to show you what this looks like, we'll pop over to the UI, open up Kubeflow's UI, and look at the existing run here with the graph of the execution workflow and the parameters from that file. Next, we'll go back to the command line, and instead of executing from that file, we'll overwrite it with a command line flag, and this time setting the number of epochs for this particular run. We execute that again, go over to the UI, and check that out. All of the right parameters are now pushed into that particular execution. Finally, best practices say you should always update your code and run from that rather than using command line flags when you're ready. In this case, we'll go over to that same file and change the number of epochs in that file and go back to the command line and re-execute. I've mentioned the command line several times here. It certainly doesn't have to be driven from the command line. You could do it from the UI, but we're starting here just to make it easy to demo. When I go back to the UI, you can see that even though the command line execution did not change, the parameters did change because we changed that underlying same file, which drives everything. Now that's the starting point. One of the things that makes this so powerful is you can take this deployment and run it anywhere. If I go forward, check this code in, and push it to a GitHub repo, I can now also execute using the exact same commands during a CI/CD pipeline. I'll be using GitHub Actions here to do that. So when I go here and I cut a brand new release, in this case 0.010 and execute that release, the GitHub action pipeline automatically goes forward and using the code and same file in this repo will execute it against that same cluster that I had earlier. And in addition to going through the entire execution, it's going to go back and attach the commit SHA. Now this is extremely powerful because this means that far into the future, if I want to go back and look at exactly what was used to generate this particular model, I'll be able to do it as long as this commit SHA is attached. And just to show you how this flows through, let's go over to that same Kubeflow UI and look at that model execute again. In this case, you can see that we have release 0.0.10 as the name of that file execution. And when I go and look at the configuration settings, you can see that the commit SHA has been attached as part of the run parameter. This is now up to me to take this forward, but as you can see, we've now tied together two independent steps that previously were fairly hard to do. The checking in of code and the execution of a training run are now able to be coupled and recorded for the future. So that is the same project. A straightforward way to define your workflow applications and deploy them on local laptops against VMs in the cloud and against your production clusters, even as part of a CI/CD system. Now, make no mistake, we have a long way to go in order to get to our eventual vision. We would like to ultimately work towards a simple UI and UX that works anywhere, whether or not you're engaging with the tool of your choice or the UI that you saw here or a command line interface. And our hope is that it gets to be as simple as the three things you see here. One line to install, one line to run, including running with different parameters, and one line to export. And if we can get there, we think we can make real progress against the problem of reproducibility and make it much easier for data scientists to change the world in a positive way. I mentioned the same file several times, and you might think that it's incredibly complicated, but it's not. Our hope is that with just a few annotations in your Python script or notebook, you'll be able to drop that into the same file, just like you see here, and have a clean manifest for deploying anywhere you have a Kubernetes. Our hope is that we can come together as a project and nail the center of the Venn diagram of these three circles. One, that something is completely open source governed, that it's tied to no commercial entity whatsoever. Two, it's completely declarative in nature so that you can take and deploy it anywhere. And if everything is already installed, it understands that and can be reproduced. And third, it's based on a universal platform like Kubernetes that is available for free on your local laptop or a VM, or can be installed on any managed cloud platform with just a credit card swipe. The same project aims to merge all three of these and make huge efforts at improving reproducibility and portability of workflows and machine learning everywhere. So that's it. That's the same project. Obviously, we are just getting started, and we would love to hear from you what we can do to help you and make your life working with ML better. Going beyond just the use and deployment of ML, we really hope to make authoring of these workflows much, much easier. And we have a big vision for going even more broadly than that. You can see all our information on how to get in touch and engage and give us your feedback. Thank you so much.
Excellent. So, in case you want to see that video not blurry, David put a link to the video again in Slack. We don't know what's going on with the streaming, but sometimes it happens. This is how we're doing it. Next up, we've got the team from Provectus and Stefan Pushkarev. All right. He is going to be coming. He is the CEO, Stefan Pushkarev. Sorry, man, I'm butchering his name.
Thanks, Dimitrios.
You're going to cover the vision, the current state, and the roadmap for bringing Feast 0.10 to AWS. Is that correct?
Thank you so much. Yes, I'm Stefan from Provectus. And the talk is about bringing Feast 0.10 to AWS. Sharing my screen. Here we go. A separate kudos for my team, Pavel and Leah, who actually contributed the actual pull requests to Feast repository and helped me to prepare the demo for this talk. Agenda-wise, we'll start with introductions. Then we look at the Feast roadmap on AWS. And we're going to do some dangerous things. It's going to be a live demo, so keep fingers crossed. 90 seconds, 60 seconds, even 40 seconds Provectus overview. So we are AI first consultancy and solutions provider. We help enterprises to ship end-to-end AI solutions for different use cases you can imagine. And also work with enterprises to build end-to-end data platforms and machine learning platforms, including all things MLOps and machine learning lifecycle as a whole. Headquartered in Palo Alto, I'm in San Francisco, and the team is scattered across the globe with the main locations here in Silicon Valley, Canada, Europe, and Latin America. So a little bit of context of this talk and this presentation. So we started sharing our vision and thoughts and collaborating with the community back in 2020. And one of our idea and the vision was is outlined in this blog post back in December. Long story short, the vision was that feature stores as a whole should not bring a heavy infrastructure to the existing enterprises because they already have a lot of silos, and feature stores API should represent a tiny library, a tiny service that can be nicely integrated with everything that enterprises has already built. For instance, if you have most of your data, let's say in Redshift, and you would like to reuse Redshift in infrastructure, it does not make sense for you to bring yet another data silo with a feature store. So, and you should be, and the feature store design should be done in a way that it could be easily deployed on top of your existing data infrastructure with small modifications, but that's doable. Also, things like Kafka, Flink, Apache Hudi, very opinionated. So every company has its own vision how to build data lake, Delta Lake, and all that stuff. So talking about the Feast roadmap on AWS, we started collaborating with Tecton team from that time, since we had the very similar vision on that roadmap. Here you go. S3 registry and DynamoDB integration is on its way. The pull request is there. The issues are open. Encourage everybody to chime in and collaborate. Redshift data source for offline feature store is also underway. AWS glue source with Athena integration is something that we're see as the next step. And the Hudi table is one of the most compelling use cases in terms of the functionality and the features is going to be prioritized afterwards. So we start with the low-hanging fruits and then expand the scope with the new features and integrations. So it's going to be really cloud native, AWS native Feast deployment. So demo time. Here is a AWS account with the it's a DynamoDB console, empty console, S3 folder, also empty one. And what I'm going to do, I'm going to run through the default default, FIST, demo, and boilerplate. With the one modification, it's gonna use AWS DynamoDB provider, and it's gonna use S3 as a registry. Here we go. So we create the baseline FIST objects. We call apply. So basically, it's applying that config to the AWS and provisions the following info. Let's see. Okay, so we have created the schema in a DynamoDB. We have created a registry here just to store the registry information for the FIST in a S3 folder under the hood. You see there. So, and what we're gonna do next, we're gonna call materialize incremental, which actually aims to synchronize and materialize the offline store with the online view. Offline store is implemented as just a Parquet file stored locally in this notebook, but that's enough for them. So we call materialize. Let's see what happened. So we see the materialized view in Dynamo. Here we go. So that's our online. Those are our online features. Now we can query them through the same API, get online features on the FIST. So you see it works. Simple demo, but big plans and a roadmap to collaborate on. Back to my slide deck. That's a lightning talk. I'm happy this demo went through. The next step, watch and contribute. The list of issues that I have mentioned before. Happy to follow up in Apply Conference channel for further discussion. And feel free to message me in Slack and LinkedIn if you need help in bringing Feature Store to your organization, especially FIST on AWS. Thank you so much. This is Stefan from Probectus.
Awesome, Stefan. Appreciate that. It looks super cool. So next up, we have got the team from Cookpad. And I know it is late in the UK, so I appreciate them coming through. And the late night, we're going to be hearing from Eti Irie, the platform engineering lead at Cookpad, and then Nadine. So I will call them up to the stage just as a reminder, or in case anyone is wondering who or what Cookpad is. They're the world's largest recipe sharing app. In 2018, the company began to add machine learning to ranking algorithms on the app's social feed. So we can watch Eti, the platform engineering lead, followed by Nadine, a machine learning engineer, discuss why a feature store is essential for serving machine learning at scale. And one thing that I think is super cool about what they've got going on there is the company was originally from Japan, I think, and now they have their satellite office in the UK. So we're gonna get this rolling, and you're gonna hear from Eti first. Here we go.
Hi there, my name's Eti, and I work for a company called Cookpad. And I'm going to talk with my colleague Nadine today about scaling a machine learning social feed with feature pipelines. So this is Cookpad. We're the world's largest recipe sharing app, and we have an office in Tokyo, which looks after the Japan platform, and an office in Bristol in the UK, where we look after the global platform. So I'm going to go back and tell a story about when we tried to introduce machine learning into the social feed for the app in 2019. So at this time, the feed service for the application was a Ruby on Rails application backed by Redis and Postgres. And we wanted to introduce machine learning ranked feed for a very small percentage of our users. And to do this, we went through the standard process that we use in the company to test new functionality. And at the end of this experiment, we would decide whether to roll out to our full user base, or to drop the functionality because the experiment wasn't a success. So at the time, most of our machine learning had been for research. So we introduced a very simple architecture to be able to extend this to serve production traffic. On the offline side, we were running jobs on Heroku 2, which is a workflow engine, to ingest data from Amazon Redshift and store that in S3. Then the machine learning researcher would fetch that data from S3, calculate a number of features. So these typically were embeddings for different bits of data that had been fetched from the data warehouse. And then they would use these embeddings to train a model to rank recipes to be personalized for these users. And then calculate these ranked recipes and store them back to S3. On the online side, when a customer would come in and make a request to the machine learning feed, so this is users who are in the experiment, we were just serving this through a very simple Python application, which was storing pre-ranked recipes for users in the experiment in memory. So when we looked at the results of this experiment, and we were measuring metrics by an aggregate of interactions that users were making on the feed, so whether they were clicking on recipes, liking them, saving them to come back to later. When we looked at these metrics, we got an over 30% increase on the interactions that we cared about on the ML ranked feed. So naturally, the product managers were very pleased about this result, and they asked us when we could roll this out to 100 million users. So obviously we had to say no, because this was a very simplistic architecture and it wasn't going to scale to that, that user base. So where are the bottlenecks? So on the serving side, we were storing ranked recipes in memory. As this data grows, the service would have really long startup times. You have to replicate the data every time you want to replicate your service. So when you want to scale out horizontally, and you have to calculate and store ranks even for silent users. So a large proportion of our users never log into the app, and we don't want to be calculating data for them. On the training side, there was a lot of manual repetition. So the researcher would have to recalculate their feature data every time they wanted to run an experiment. And because of the way we were storing data, it was sometimes hard to share this feature data between team members. So we've rethought how we want to do this, and Nadine is going to talk about the solution that we are using today.
Hi, everyone. I'm Nadine, and I will be taking you through how we scaled our social feed to 20 million users. So at first, the main functionality of the social feed is to recommend recipes that our users might interact with. Therefore, it's a read-heavy application and also requires the fastest response time possible in milliseconds. In addition, the number of requests vary for example, in time of day and the most popular events of the year. Hence, we have chosen to store our ML feature in DynamoDB with DAX, which made our application fast and responsive, even when a popular event occurs like now during Ramadan. To populate machine learning features, we started with cron jobs through Argo workflows that are ingesting data in batches into our feature store. Unfortunately, these jobs are using the recipes published the day before, since they are consuming data from Redshift. In order to use fresh content as soon as they are added to our platform, we are recently gradually shifting the streaming ingestion system that will produce and store machine learning feature in nearly real time, so we can make sure we are using them as soon as possible. And these cron jobs are using also, as we can see here, feature extraction services. Like for example, in our case, mainly, there are recipe embeddings and user embeddings. Finally, to address disaster recovery that might occur for our feature store, we are using point-in-time recovery, which will automatically back up the data with per-second granularity, so that we can restore it to any given second in the previous 35 days. We can say that the main advantage of the point-in-time recovery for the DynamoDB is that it doesn't affect the read capacity or the availability of our production table. So we can say that we are still using it with no problem. So basically, what Feature Store has enabled us to is first rolling out to 20 million reliably versus 10,000 users during our first experiment in 2019. We can also now say that our service is retrieving pre-calculated features, rather than, as Ati said, we had before need to calculate all this feature every time we are using the service. Using DAX, we can say that we increase data retrieval performance, which, as said, has enabled us to run faster. And finally, we can say that Feature Store has enabled us to have a stable service even when we get a bump of traffic now during Ramadan, which is 2.5. On the other hand, it also had a very positive impact internally, as it has enabled the research team to collaboratively develop new models faster by reusing shared features. So recently, we have been able to test 4 new experiments due to our feature store. For example, we can see here that during Ramadan, and even during a traffic spike, our system was reliable. We can see that no failed responses. And also, our DAX cluster is being highly used. Thank you for all listening, and hope that this lightning talk had give you some idea how you can use your feature store to make an application that has ML inside more faster and reliable. If you are interested in Cookpad, please, we have always new openings, and this is our website, and hope your talk find you well. Thank you.
Awesome, Nadine. We appreciate that. Very cool to see. And shout out to anyone out there who has been using Cookpad. If you have tried Cookpad, let us know in the chat because it's a pretty awesome app. All right. Next, we've got Alex Ratner. He is the CEO and founder of Snorkel AI. Going to be talking to us today about programmatic supervision for software 2.0. Alex, good to have you on here. I appreciate you joining us.
Great to have you as well. Thank you so much. Thank you so much for having me.
Take it over.
Awesome. So I'm going to, let me just pull up my slides, and thank you all again for the time. I'm going to give a quick overview of, at a pretty high level, not just a particular product that we work on called Snorkel Flow, but also just, and mainly just this kind of idea and research focus that we've had over the last 5.5 years, first at Stanford, now at Snorkel AI, the company that spun out. So I'm going to go ahead and share my screen. And hopefully you can now see my slides. Yes?
Yep. Yeah, we see him.
Awesome. Okay. So I'm going to give the high level overview because I only have 10 minutes, right? I have till 2:46, correct?
Yep.
Awesome. Okay. So really, I'm going to just actually center on the motivation a bunch of why we have worked on this this problem that we've worked on of programmatic data and programmatic training data for machine learning over the last really 5.5 years, and now with a bunch of other researchers and work out in the open along with what the company at Snorkel AI is doing. So this all kind of gets grounded in looking at the pipeline for actually building and developing and deploying machine learning models. And in particular, I'm going to focus on a type of machine learning model called supervised learning. So we're trying to, let's say, classify chest X-rays or contracts or route customer support tickets or extract information from a document, all things where you're trying to get a machine learning model to predict or label something automatically by showing it a whole bunch of examples that have already been labeled correctly that it learns from. And that collection of examples or data points that have been labeled is called a training set. So at a very high level, this supervised learning approach, which is kind of the workhorse type of machine learning out in practice today, has three main ingredients. We have the training data that I just talked about. We have the actual machine learning model that learns from this training data to make new predictions on new data points. And then we have the hardware, or more broadly, I would just say kind of the infrastructure. And one of the really interesting sea changes that's happened over the last 5+ years is that it used to be that 99% of your effort, if you were looking at an average machine learning deployment, would go into the model and the infrastructure, building bespoke models, model architectures, doing what's called feature engineering, and picking out the right attributes to look at, and then building all the infrastructure to train and serve this in production. And while that's still a huge focus of activity, and sometimes it is the majority depending on the use case, when you look at data types that are that we focus on and many folks are interested in, often unstructured data types like text, image, video, time series, all this stuff where it's really messy, difficult data. We have never had more powerful models. We have these new deep learning or representation learning approaches that learn to do all of those steps kind of on their own. But we also have never had them more accessible out in the open source. And so this is a little bit glib, but the models and the hardware and the infrastructure are increasingly commoditized and accessible. And that's only meant in the most positive way. It's a real testament to the field that if you want to classify a document or classify a chest X-ray, you can now do so with less time and less custom development than at any other time in the last or ever. But what's the trade-off? The trade-off is that these models that are so much more powerful, so much more available in the open source and supported by all these amazing projects, many of which you've heard of today, are also much more data hungry. And to learn to do what they do, they need much more of this labeled training data. So let me give an example. And again, I'm going to spend most of my 10 minutes just kind of talking about the problem and just mostly as a kind of pitch for why you should care about data and machine learning. I know most people at this conference, it's a biased sample of will already care about this, but just for what it's worth, why you should care about the bottleneck of labeling training data, and then just a little sketch of what Snorkel is about and the solution types that we've worked on. So let me just give an example though with hard numbers. This is a publication or a set of, it's a project most recently published about in Cell Patterns and also in Radiology, the journal, with the Stanford Hospital, the VA healthcare system. Here we were trying with collaborators to train a machine learning model to triage medical images or tests coming in, chest X-rays, head CTs, knee X-rays, the list goes on. Basic idea is to do assist. So basically determine whether a doctor needs to urgently read something in the queue or whether it can kind of sit and wait. And this is especially motivated by under-resourced hospital systems where there's way too many images to read for too few doctors. So here, actually our collaborators were able to train a human level, a model that was performing at human levels in under 2 days, just by trying out all the open source image classification models that are all very accessible and nicely supported frameworks. And there was actually under a point of variance in terms of the performance of the fanciest new model and the fifth fanciest new model. Conversely, it had taken them 8 to 14 person months of just labeling chest X-rays, head CTs, et cetera. And the difference between a little bit of that labeling and the full 8 to 14 person months was over 10x, over an order of magnitude more impactful than the choice of model architecture. So again, it's worth emphasizing that it's an incredible testament that these models perform so well. But the biggest relative leverage point in many machine learning pipelines today, especially over these complex unstructured data types like images or text, is the data, how much of it you have, how it's collected, etc. And this is what blocks many, many use cases and enterprises and organizations from actually using machine learning. It's this training data. And just to briefly note, a lot of what gets glossed over in, on the academic side of things, where a lot of the training data that people use is just these nicely packaged benchmark data sets that are great for the field, but mask a lot of the collection difficulties. A lot of the pain points come because you, in the real world, have data that's private, so often just can't be easily shipped out to be labeled. You have data that requires rich subject matter expertise. You need a doctor or a lawyer or a cyber analyst or a network technician or et cetera to do the labeling, not just anyone. And you have to be able to iterate when input distributions change, when upstream pre-processing pipelines change, when output goals change. If you want to, if you shift patient population, or you want to now do 3 levels of triage rather than just good or bad, if you're relying on hand labeled training data, you need to just kind of start all over again. And this is a huge impediment to progress. So at a high level, what the Snorkel project for many years, and now the Snorkel company, and we really like the name Snorkel, so the Snorkel Flow platform is about, or what it's anchored on, is this kind of pivot point from labeling by hand to labeling programmatically as a way to drive the process. And the key idea there is, rather than just, or another way of phrasing is, rather than having the user just sit there and click this X-ray is bad, this X-ray is good, et cetera, for hundreds of thousands of data points over, say, person months, have them just say what they know, express as a function. Look for these blobs in the image, look for these keywords in the nurse's report, look for these metadata signals, and use this to kind of train or bootstrap the model. And by doing so, really raise the whole abstraction level at which you program and drive and build machine learning models. So this was a project back at Stanford for many years. Did some great collaborations, deployments, co-development with a lot of the big tech companies, government agencies, others, and led to this platform that now we're building over at the Snorkel company today called Snorkel Flow. And really, it's a platform that supports this whole vision of how you, in a nutshell, take machine learning development from this process where, again, not in all settings, but in many of these unstructured data, complex to label settings, take machine learning development from this very bottom-heavy process that's 80–90% by volume and time, just labeling data by hand, one by one, and turn it into something that looks like any other mature, sane software development process that's fast and iterative, and where you write some code or push some buttons, compile something, see where it makes mistakes, and then go back and turn the crank. And so that's the idea in Snorkel. And so let me just give a quick glimpse of what this looks like. So let's hop examples and imagine we're trying to classify some contracts. And I know I have about a minute and a half left, so I'll just breeze through this, and then happy to chat if anyone wants to connect afterwards. Basic idea, rather than, or in addition to having say a legal analyst sit there and label contracts, this one's a credit document, this one's a loan document, et cetera, have them express their domain expertise. Look for this word in the title, match this list of this dictionary of financial terms, run it by our legacy system, anything that can be expressed functionally, and have them write this as what we call a labeling function. And this labeling function can be expressed in Python, it could be expressed in no-code UI. And in a nutshell, the advantage here is that you can write these labeling functions and label massive quantities of data and then train extremely complex high-performance models in minutes or hours rather than person months or longer. The challenge, of course, though, is that these labeling functions are in general going to be not perfectly accurate for what we call noisy or weak supervision. So a lot of the work that we did in the academic side was about how, using theoretically grounded techniques that build on very old intuitions and very old theory, how you can kind of take these functional signals, clean, reweight, denoise, and combine them, and use them to train modern machine learning models. So let me pause there because I think I'm right about at 10 minutes. I don't know if I have time to take a question or two. Otherwise, thank you so much to the Apply conference team and to Tecton and everyone else here for letting me rant about programmatic supervision and Snorkel for a bit.
That's awesome, man. I appreciate that, Alex. Questions in Slack, preferably, because it's starting to get super late where I'm at and we want to finish on time. So you're in there though, right? Just to confirm, Alex, you're in Slack, and everyone that is asking you questions, you're going to be around for a minute to answer them.
I'm not actually in Slack, but I can try to get in.
There we go. All right. Or we can tweet at you if that's easier. But Slack will be the best. It will be the most direct in case anyone has something to ask you about this. This was super informative and I appreciate it. Next up.
Awesome. Thank you so much.
Yeah. Cheers, Alex. Take care, man. So I believe we have some amigos from down south. My friends at Mercado Libre. Where are you at? Emiliano, Martin. There he is. All right. So
Hello.
let me just, hola, amigo. What's happening? Emiliano is the senior software engineer at Mercado Libre, and it's commonly accepted that having a feature store is crucial for any organization that wants to improve its time to market. In this talk, we're going to watch Emiliano Martin, the senior software engineer at Mercado Libre, propose a solution of feature store and explain the benefits the organization has gained by implementing it. So the stage is all yours, Emiliano. Muchas gracias.
Thank you, Demetrios. Hello, everyone. My name is Emiliano Martin. I'm Argentinian. I'm married and have a daughter. I'm a software engineer working in Mercado Libre. For the one who don't know, it's a technology company of e-commerce leading in Latin America. And our aims is to democratize commerce and money to have an impact on the region development. I have worked here for 6 years. A new problem in the industry. Within the world of software development, and especially in the area of machine learning, times assigned to analysis, development, and deployment are key to success of an organization. At Mercado Libre, we are not exempt.
1 second, man. I don't think we can see your screen. Are you sharing something? You might have to
Okay.
Yeah, cool.
Sorry
about that. No, it's all good. I know it's a little confusing. There we go. Now we can see it. Cool.
Okay. I share my screen?
Yep, we see it perfect.
Okay. Sorry. That's why on Mercado Libre's backend, there are many entities that are consulted by mouse developers from different teams. An example of an entity is item. We call item to the publication that seller makes in our marketplace, and it has a title, price, picture that you can see in front end, a category that lets user find the product, for example. And on this entity that we call item, different business needs arise, and they are solved using machine learning solution. For example, we may need to make a binary classification to determine whether an item is breaking a rule and should be moderated. We may need to make an automatic product classification by category, or we may search for similar items to the fit recommendation. Whether to do classification, regression, or search for close neighbors, all these initiatives have to through a similar feature engineering process in order to generate representations of the item that allows the training of models. So if we have to solve a new problem using the entity item, we need to apply a feature engineering process again, and this means repeated effort across teams. The feature engineering process can take time and is key to model development. Apart from that, not all teams have a machine learning expert or developer with significant experience in a tool or business area. And even if they have, there may be no simple mechanisms from other teams to take advantage of their know-how. To face all these problems is that we propose Feature Store. But what is Feature Store? Shortly, it's a centralized place where teams can consult the feature of an entity. There are several approaches to implement this solution. If we think of feature in the traditional sense, as a characteristic of the entity understood by a human. The feature store could be an API on a database engine that allows tracking specific information. For example, the number of publications visited by some user in the last 10 days. Another option is to think of feature as an intermediate level of abstraction by creating models that generate embeddings like representations that success and dimensional vectors from any entity we are interested in, for example, items or shipment. The meaning of these vectors may not be clear to a human, but they can have interesting and useful properties for a model. For instance, the vector representing items corresponding to the same type of product can be closed in the n-dimensional space, or the vectors that represent payments might be largely grouped so that we can set aside and review those whose representation is far from that group. This allows to find fraudulent transaction. With Mercado, there exists different solutions of feature store. I talk about just one of them. One way of solving this could be by creating service that transform an entity into a vector through API, but we found some drawbacks. Therefore, we opted for the TensorFlow strategy, which comprises a repository or hub of model and API to download them. After downloading, the developer becomes the owner of that object and is totally independent from our hub. Thus, the application that uses it is only dependent of the feature store in the training stage. And afterward, it can work in completely self-contained way. So we decided that these models that transform entities into embeddings would be shared in Python libraries with a scikit-learn interface. They can be installed with pip and are object with fit and transform methods. This helps their adoption by our machine learning developers, not only to integrate them into scikit-learn pipeline, but also to use in combination with other tools. For example, we have PyTorch models using these representations. We also thought about this, taking into account that we call create version of these models. The same model could be used to represent different data sets, like publication in Spanish, English, or Portuguese. And there can also be models trained with different hyperparameters, for example, to generate vectors of different dimensions. On the slide, you can see an example. Okay, what we achieve by doing this? First, fast MVP. Since the feature engineering process is already solved, we only have to concentrate on solving business problems. Thus, you can have an MVP or proof of concept in a few days or even hours. Less duplicated effort, because we allow entity to feature transformation to be shared across teams. Widespread expert knowledge. Due to knowledge and expertise of machine learning experts can be available to all teams. Improvement of existing models. Embeddings can be combined with the features of models that are already in production, which can render improved metrics with very little effort. And resource optimization, as reducing redundant work not only saves developer hours, but also model training hours and infrastructure cost. So, as to sum up, we are convinced, like other great reference in our industry, that when working on a large scale, it's vital to take a more global look and devise a platform that fosters cooperation among teams and speed up delivery times to production. That's why having a feature store is key to our case goal. Well, that's all. For further information, you can visit the link on screen. See you at the Slack chat. Thank you.
Excellent. Emiliano, thank you so much.
Thank you.
I appreciate that. I appreciate that so much. All right, man. So Mercado Libre, doing some cool stuff with feature stores. I love it. And we're going to keep rolling. This is the lightning talk, so we got to keep going quickly. You know how it goes. I got 1 minute of transition, and then we're jumping in to the next talk, which is with Aman Khan, the product manager at Spotify. Ooh, I got so many questions I want to ask you, Mr. Aman, but you only have 10 minutes to give your talk. So, Aman, over 345 million people use Spotify, and they rely on Spotify's personalized recommendations in 170 markets. Guess how Spotify builds great recommendations? With data and machine learning, of course. That was a given. And the Spotify product manager, Man Khan, who is right with me now. What's happening? I see you there.
Hey, how's it going?
Good, man. Happy to have you here. And I'm excited for you to talk to us about the central machine learning platform that you all got at Spotify. So without further ado, I'm just going to kick it over to you and we'll let you get started.
Awesome. Thank you so much for having me. So, hey, everyone. My name is Aman, and I'm a product manager at Spotify working on Jukebox, our feature management product, which is a part of the ML platform. I know this is the last talk of the conference, so I'm going to try and end this on a high note. No pressure here, by diving straight into how we manage features at Spotify. Cool. I think you can all see my screen.
Yep, looking good.
Great. Awesome. So we're going to be talking about Spotify scale. We're going to be talking about some of the unique challenges that presents to Spotify when it comes to doing machine learning. From that, we're going to talk about a little bit about where we were about 1 year ago today, where we are right now with our feature platform, where we're going, and some of the lessons we've learned that you can hopefully apply at your own companies. So let's dive right into that. So let's talk a little bit about Spotify scale. Spotify as a product is used all over the world by hundreds of millions of people every month who are constantly accessing and interacting with billions of catalog items. This slide has some big numbers, but really the main takeaway is we have a lot of data and it's growing constantly. And all of that data is meaningful to continue to provide a better experience to our users with the number of use cases that leverage ML increasing. The ML platform is the infrastructure that really ties all of these pieces together and helps us level up the rate of ML at Spotify. And while Spotify's scale affords some really amazing opportunities to build a great experience, it also presents unique challenges that come with scale. So at Spotify, we largely think about features as representations of data, which generally take the form of key value pairs. For example, how much a user likes a certain artist, and that's constantly undergoing changes across different ML use cases. So from a technical perspective, we perform online inference for a variety of use cases. For example, showing you a new release from an artist you love on your home screen when you open up the app. And a number of these use cases utilize near real-time, low latency features. That means when users interact with the product, we can dynamically update model predictions about what to present next. On top of that, when ML engineers are creating and managing features, we have an inherent challenge around offline-online consistency of features, like needing to backfill data for a feature to evaluate its impact on model performance. Furthermore, because of the highly autonomous nature of our engineering function, to move fast, often engineers have to unblock themselves and may not realize that some features are common across use cases. So they end up recreating features themselves, which is costly from both an engineering time and data duplication perspective. Needless to say, features are a huge problem across the company. So where were we 1 year ago today? Well, effectively, we had a collection of disparate data libraries to kind of help with data utility tasks. We didn't really have a central feature registry. We didn't really have support for dynamic features. In fact, we didn't really have a central feature strategy either. We didn't really have integration with model serving or the rest of the platform. features weren't really treated as a first-class citizen in the ML workflow, and users often dealt with data endpoints, which is sort of our notion of where data lives rather than features themselves. This overall kind of led to low adoption of these tools and kind of led to a sort of Swiss Army knife approach where engineers took some initial libraries and built on top of them. Overall, there wasn't an opinionated workflow on how to create or use features. And you can kind of think of this as sort of like the New Hope version of the feature journey, where engineers are really on their own, sort of out trying to figure out how to do ML with features. So where are we now? Enter Jukebox. Jukebox is a collection of Python and JVM components that help manage data throughout the ML user journey. They can be scheduled using a data scheduler to execute on their own, sort of leading to a decentralized management of features. Jukebox helps with collecting, loading, and reading features during feature training, during model training and serving. And the starting point for that is the feature registry, which is a single source of truth for features and helps maintain a single concept of a feature that spans both offline and online. Users can explore the registry via our feature gallery UI component in ML Home, where users can search, discover, and understand features they might consider reusing in their model. Users first create and register features that they're experimenting with, perhaps using the converter component to convert to our current standard format of TF records. Registered features, no matter how they're stored underneath the hood, whether they're Avro or TF example on GCS or BigQuery, can be retrieved by a collector component, which selects and joins features from upstream data endpoints. When joined with labels, these features can be used to create a training data set. The loader then ingests those TF records from GCS into Bigtable using a specified schema, and each team is responsible for their own Bigtable cluster, while we provide the tools to easily spin up a feature store. The reader is a Java library that makes features available at scale for low latency read from an online service. It also reads data from Bigtable to be used as an input to the model by the TF records produced at the previous stage. The reader then looks up the latest date partition for each table and provides optional in-memory caching for the feature. And ultimately, all of that gets sent forward and joined with the model to kind of serve a prediction online. So this workflow made it really easy for us to address some of those early use cases with common libraries, but we ran into issues with scale as we tackle more complex use cases. Overall, you can kind of think of Jukebox at this stage as sort of like Yoda in Empire Strikes Back, where we're sort of guiding and helping with this sort of decentralized management, but I think there's a lot better we can do here. So where are we going next? And that really leads us to the Jukebox API, which is a major part of our strategy going forward. We basically take the previous functionality that I just spoke about and expose it as a service API, which kind of lets us use higher level abstractions by connecting the dots between all these internal libraries. So users only need to focus on their own workflow and not how data passes between components. Ultimately, a lot of the functionality you see here around preparing training data set, create a feature for online inference and offline inference are basically the same functionality from the libraries provided earlier, but now it's all sort of happening underneath the hood. So the service will automatically convert between formats, which is similar to that sort of format agnosticism you heard previously in the LinkedIn platform. Register Bigtable and GCS locations and feature registry, join those data sets, and then compute statistics on those features as well. This has some inherent benefits to our users. For instance, this kind of allows for us to kind of have centralized management of features, meaning that we have decentralized operation of online stores with sort of central management through this workflow. That means that users no longer have to worry about multi-tenancy. And for example, we don't have to worry about latency from other teams' feature stores because we now have a centralized access pattern. On top of that, we can now make improvements underneath the hood. For instance, we can now start adding storage layer abstractions or in-memory storage for low latency underneath the hood without even users really having to worry about that. We can also start unlocking some capabilities like point-in-time joins, like time travel. And as we move forward towards versioning and maintaining feature transformations, we can expand and adapt the API to conform to those needs as well. This also gives us some more options as a platform. It allows us to change implementation details with no user involvement. So we can update internal logic about how data is passed without requiring users to update their workflows. So for instance, if we need to conform to new privacy preserving requirements, we can just add that underneath the hood. On top of that, this also helps us avoid version conflicts with user pipelines and avoids having users having to migrate over to new versions. And it makes tying in with other tools and integrations and the rest of the ML platform a lot easier because we can now provide a simple interface for them to build on top of. ultimately, this is sort of helping us zoom out and become more of like the sort of Return of the Jedi version of feature tooling, where users now feel empowered to actually kind of take this workflow and do the necessary tasks to ship their model in production. And ultimately, this strategy gets us to address the two main issues we highlighted earlier through a sort of building a feature marketplace by solving the organizational problem of supporting a variety of use cases and getting folks more comfortable with feature sharing and reuse. And to do that, we really need to kind of build an efficient and performant storage and scalable backend, while also kind of supporting a multitude of use cases across Spotify. And that ultimately allows these feature producers and consumers to come together using this centralized API to kind of share and reuse features across Spotify. So what are some of the lessons that we've learned? First and foremost, I would say listen to your customers. That generally applies to platform tooling, but it's extra important here. And one realization is that use cases can appear to be highly specific. So try and identify overlapping common or overlapping parts of use cases that are the most painful and don't have a great solution, and prioritize those first. And if you pick the right use cases, you'll likely have backend engineers from customer teams wanting to collaborate on solutions because they can see the most painful part of the workflow becoming easier, which is a sign of success. On top of that, the build and buy are becoming a build versus buy analysis is becoming tougher as time goes on. And our friends at Tekton have built something really awesome. So as time passes, tooling is either going to become available open source in an enterprise way, and that'll keep getting better. So if you're an early stage company, consider how far you can get with something just right off the shelf. And lastly, think about scale early on. So sort of a lesson from the data space, having a fragmented strategy in different parts of the company will lead to challenges with adoption and data management. So find opportunities for long-term partnerships and figure out ways to reduce duplicative work as well as data. And that's it. That's Jukebox in a nutshell. If you have any questions, you can drop them in Slack or reach out to me on LinkedIn. We're hiring folks across the ML platform to tackle a variety of challenges. So if working on a product that people love is exciting to you, let's stay in touch. And we hope to have some more exciting announcements later this year.
Excellent. Aman, you finished strong, man. I appreciate that. That was very cool. I love the Star Wars evolution slides.
Yeah, and live long and prosper, another Star Wars reference.
So I got a question for you as we're finishing out. I don't know if you were here earlier, but I played a little music. What do I got to do to make that go viral on Spotify?
Oh man, let's see. I guess we can probably try to promote it on Twitter and maybe get it to blow up, and post it on Instagram. We have these great integrations with Instagram, and I think sort of naturally from there, your talent is really going to shine.
There we go, man. Well, I appreciate it. I appreciate you coming on here and talking to us about this. This was super informative, and yeah. That's it, folks. That's a wrap. I guess to give away some swag now, we're going to give some best talk, most entertaining, all of that stuff. The talks, I get to give away some swag for the talks, the people who are giving their best talks. And then I also get to give away some swag to people who put some memes in. So this is it. Before we go, before you all leave, I want to mention that you have it's a survey, we could call it. There's a survey that we're asking you to fill out so that we can know what we did well, what we didn't do well, and we can make it better for the next time. And it's been awesome with you all. I hope you enjoyed it. And now let's get to some swag giveaway. The funniest meme goes to, well, we had a few really good ones, but we've got in Slack, Daniel, I think, wins the first one. Daniel, I think you're still up. So you get the funniest meme numero uno. And then we have another meme award going to Amar Asmiro. I'm butchering that name. Sorry about that. I don't know if you're still up. I haven't seen you recently, but if you're watching this tomorrow or the next day, reach out to me and let me know. We didn't have any good gifts though. I was kind of sad on that one. So most creative gift, I guess I'll take the swag on that one. No problem. We've got Slacker Award. The chatty Slacker goes to Reed Martin. I don't know how you say it. Obviously by now you've seen that I just butcher names. So Reed, reach out to me and let me know. Then we've got another Slack MVP here with Vishal. Vishal, I get the feeling it is really, really late for you, but if you are still around, reach out to me and you'll get some swag too. The last one that we're going to give, the most helpful on Slack, is Elena Goidina. Bravo. All right, now for the talks. Who wins some swag for the talks? The most entertaining talk goes to reusability in machine learning. Is that so? Reusability in machine learning. And I got to go figure out who, hold on, I'm going to stop sharing right now. I'm going to figure out whose talk was that, the reusability in machine learning. I remember introducing it, but now I don't remember who gave that talk. Oh my God, can you people, you all can tell it's getting late where I'm at. All right, I got to wrap it up before I need to go to bed. Best slides go to my man Lack for the machine learning or ML design patterns for data engineers. Lack, we're going to have to tweet at him. Everyone tweet at Lack and say congrats for winning the swag. And that is about it. I think the most, of course, most informative, how could I forget? It goes to Todd Underwood for the only truly hard problem in MLOps. Awesome. Well, this has been incredible. I would love for you all to fill out the feedback survey. It will be very helpful for us. And that's about it. Let us know if you want us to do it again. I would be happy to. Please join the MLOps community. That is where you can find me and talk to me. If you're not in the MLOps community already, highly encourage you to get there or watch our stuff on YouTube or listen to it on Spotify. Aman, if you're still around, maybe we can make that blow up too. Let us know how. All right. So this is it. There's been some incredible talks today. It was absolutely amazing with you all. Thanks again for joining us and staying here till the finish. We will see you all next time.
Want to get close? Yeah. Why? Why can't you just fall in love?
gotta know it. Spend a couple thousand just to cruise it. Shawty said she love me, but I swear she'll never prove it. I never tell her, but I put it in the music. Well, that's okay. All I wanna do is make the best of my whole day. Thank the Lord up above, get the cream on the side, make you laugh to know it. That's the stuff that I love, la, la, da, da, da. We can be friends if you wanna.